A very good morning to all of you. We had some great sessions yesterday from the hackathon finalists, couple of CEOs, our chief guest, former Minister Rajiv Chandrasekhar ji, and Professor V. Kamakoti, the director of IIT. Today's session is filled with a lot of technical talks. It's going to be super interesting. So without any further delay, let's get started. Our first talk for the day is going to be from NXP Semiconductors, Safe and Secure RISC-V Processors for Automotive Solutions by Neha Srivastava, Technical Director NXP, and Saurav Roy, Fellow at NXP. Neha is here with us and Saurav is connecting remotely. They're going to be presenting together. Introducing the speakers, Neha is a technical director at NXP with over 17 years of experience. She has led SoC verification for multiple complex SoCs like the first 16 nanometer 4D radar solution and the first 5 nanometer SDV solution from NXP. Her expertise areas include functional safety, security, and infrastructure logic like clock, reset, low power, and interconnects. She is passionate about enhancement opportunities across architecture, design, verification methodologies, and hardware-software interoperability. She is a notable inventor at NXP with 14 patents granted and 7 more in application at USPTO. Saurav Roy is a fellow and notable inventor at NXP Semiconductors. He co-leads the RISC-V processor development across NXP, focusing on architecture and verification. He has about 25 years of experience in processor architecture, design and verification, and has contributed to several architectures like RISC-V, PowerPC, and StarCore. Prior to joining NXP in 2005, he worked with Analog Devices and Texas Instruments in India. He holds 11 patents and 25 publications in reputed venues. He has a master's in VLSI design, tools, and technology from IIT Delhi, and a bachelor's in electronics and telecommunications engineering from Jadavpur University. Neha can take over now.
Hi all, a very good morning to all of you. We have a good packed technical session as Nitya mentioned, and from NXP today we'll be sharing the safe and secure RISC-V processors for automotive solutions. So going forward, the agenda for today would be, so we have divided it into two parts. One is the safety aspects, and as an automotive solution from NXP, what all are we doing as part of the functional safety around the RISC-V solutions. But in introducing that, we'll also go into a bit of details of the software-defined vehicle architecture, the new trend around the automotive field, and what does it mean in terms of the hardware-software interoperability, the partition management, and why security and safety are important there. We'll delve a bit into the details of functional safety architectures, traditionally in around cores, what we do in terms of functional safety. Then Saurav would be covering the security architecture details, so things like the CFI, secure enclaves. Recently, we have seen big companies also getting impacted by speculation-based attacks and the crypto extension. Finally, we'll end with the conclusion and future work. So a quick introduction to RISC-V and why it is important. I think all of us are here in this symposium because RISC-V is important, but to mention some of the paradigm shifts in the industry right now. So there is obviously the open adoption of the open source RISC-V ISA. And according to the MIT Technology Review, RISC-V is among the top 10 technology trends of 2023. Licensing, geopolitical tensions and situations as we are seeing, they are accelerating the RISC-V adoption, especially in embedded products, and AI/ML accelerators are utilizing RISC-V cores, further increasing the demand and the need for development, faster development, more efficient development around RISC-V. So specifically in NXP, what are we doing in terms of the RISC-V processor development? So we have a differentiation in terms of the automotive and edge computing, where we are extensively using industrial grade RISC-V core and the associated development. So we have differentiation with best-in-class safety and security. NXP has a reliability and history of good solutions around safety and security both. We have differentiation with custom ISA extensions over the open source. So we have security extensions, we have AI/ML, functional safety, vector DSP based. Further, NXP has a very rich and legacy and background of building around the RISC-V architecture. So PowerPC has been around for multiple, I'll say even a decade, more than a decade. So that expertise and experience adds to the know-how about how to develop the next generation of cores. Then we are primarily targeted to accelerating the subsystems and helper cores like security. So we are looking at the entire SoC or the entire subsystem development, not just deep dive into RISC-V. So it's a combined view of the use cases, right? What customer wants and how we can accelerate that based on the RISC-V development. So in short, now before we go into the details of functional safety and security, so functional safety, these are sort of complementary and contradictory to each other. So functional safety is protection against unintentional defects like manufacturing or laser attacks later. Security is protection against intentional malicious software and hardware attacks. So with that background, I'll move to the specific direction which automotive field is taking. So this is the software-defined vehicle architecture. So if the two pictures primarily, the picture on the left shows what was traditionally a vehicle, the cars we are driving, how they were defined, how they were implemented. So earlier it was a hardware-oriented vehicle, right? Every function was tied to a hardware, and it was tied to a static architecture. So let's say if you had a radar chip, it was customized and static with respect to the radar functionality. Similarly for braking, similarly for console management, infotainment, right? And any addition of the function led to exponential increase in the complexity. So you had so many functions and then so much of cabling and connections across the device for all these functions talking to each other. So imagine these blue things as each chip, one for one functionality like radar, braking, and then cables going all the way. So we already have hundreds of chips on the same device. So now the direction we have to go into is how do we minimize the cost, how do we minimize the area, and still improve the performance. So the direction we are going into is a software-defined vehicle. What this means is a domain or a zone-based architecture for vehicles where you do not need a separate chip for each functionality. Rather, in hardware, you put the hardware functionality needed for each of these, and then you tie the function to the software rather than the hardware. So functions can be sitting anywhere in the vehicle, and the architecture is flexibly. So hardware architecture can be flexibly configured by the software. This is leading to, so we already have a chip out, and that has been developed in collaboration with the customer as well. So we know that the ecosystem is there, people are willing to invest into this and develop further on this, in this direction. And the main advantage we see here is traditionally the hardware architecture vehicle would get obsolete in 5 years, 10 years. With the software defined, think of it like your phone, right? What we do with our phone, with a patch, with a over-the-air update. We are moving towards that direction where the car can be upgraded based on a software OTA patch. So now what this means is that functionality is existing all over the chip, right? So going a bit deeper into the technical details of how that changes. So again, on the left-hand side, let me see if I can do just give me a second. Yeah, there we go. Okay, so on the left-hand side, if you see, so this is the hardware view, right? I mean, earlier we will say there are, let's say, 6, 7 cores, and there would be a hardware index associated with that. And earlier this would be static. You'll always have a fixed core, you'll always have a fixed place for that peripheral in the chip. Now what we are saying, there is a cohort or an application ID associated with each of the hardware resource, right? So let's say now in the right side, if you see, I have shown the difference between two applications, the application 0 and the application 1. In application 0, the indexing of the hardware resource could be different from the indexing of the hardware resource in the application 1. So now the software has the onus or the responsibility of how it utilizes the resource, right? You have a pool of resources. You can allocate those hardware resources on a dynamic, on the fly basis to different applications. So in one application, your mapping of the hardware resources and how they are being used. So let's say the 0, 1, 2, 3, 4, 7, you can imagine each of these as one cohort. So anything with a cohort ID of 0 will be talking to each other. So core, the main boot core will be talking to a peripheral I2C, let's say for boot services. Further, if we take a cohort number 3, one core could be talking to another peripheral, the data could be going through the DMA, and then you could be writing it into a DRAM. So these become configurable, and we have to ensure that the hardware is designed in a way that it allows this flexible and dynamic movement of the context from one cohort to the other. The other important thing here is that since this is dynamic allocation, you need a partition manager to ensure that, one is there should be no hacking, right? If a hacker takes control of these partition management, you end up losing, right? Your car may crash eventually because the hacker has taken over. So here you need isolations. There should be no interference between these parallel applications, because the whole idea is you are running, let's say, 20 parallel applications on the same pool of hardware resources, right? So protection of the cohorts among themselves is a very big part of it, and hence in this diagram what we have shown the visual representation of the same. Consider this as one cohort. So these all things are talking to each other, and they need to be protected from the resources which are sitting outside that boundary. So now how does RISC-V come into all of this, right? So in the chip, so we also have a demo of that in the floor below, and this is a chip which is already there with the customer, and we have been developing software also in parallel with them as part of the digital twin platform also. So how RISC-V now, what all roles it is playing is, firstly, it is the main partition manager. Like I said, the whole definition, the configurable definition by the software, only the RISC-V on our chip has the default permission to program all these, to configure all, what are the cohort definitions, which hardware is allowed to talk to each other. So all the protection mechanisms, the memory protection, the peripheral protections, all that is under the purview of RISC-V and RISC-V alone. No other master, no other core in the device has that permission. By default, everything is denied by default for all other hardware resources. So only when the RISC-V comes into picture, it is out of reset, and then it does the authentication of the boot images, the firmwares, the application, only then it can allow that, okay, now I have authenticated all the content. I do not see a potential of a hackability, or there is no rogue software running anywhere. Only after that, it will allow, it can delegate the permissions to some other, let's say we have a CM7 core as well. That's more of a system core, it is doing more of the housekeeping. So after that point, it can say, okay, now I allow this CM7 to go and access these selective resources in the system, but still the overriding responsibility, the partition management, stays with the RISC-V. So these two are in tandem unless there is an authentication of all the hardware as well as the software. So let's say we should be in the right life cycle for the authentication to happen. We should be in the right, the images, let's say we are reading some binary images for booting from external devices like NFC and even DDR, right? So in that case, you should be able to authenticate that first so that we do not allow a hackability there. And then it has some tertiary activities also, like some security spaces are only and only writable by the RISC-V. So overall, we have designed our system utilizing the potential and the features we know exist in the in-house developed NXP RISC-V core. And hence, we did not want to leave those functionalities to, let's say, a ARM core or any other core, right? So we have specific things like the CFI, where we ensure that any skip, jump, return instructions are monitored and protected against hacks. And so there is always a synchronization between the system core and the RISC-V core. But like I said, the overriding permissions are always and always with the RISC-V. So moving on to details of further what all functional safety mechanisms we have taken care of. So we have traditionally, I mean, all cores we have the lock step. So similar is existing for the RISC-V also, or at least it is planned for the next generation of the same SDV devices. So if we go into the details of what that means is, you will always have a main core, and then to reach a safety certification, let's say of ASIL-D, it's an integrity grading. Any device which you mention as functionally safe, you have to provide an integrity level to it. So we have QM, we have ASIL-B, ASIL-D. So to achieve ASIL-D for core integration, you can always have a lockstep core. What this means is there is always a checker core which is running the same piece of code, and then we have a comparator which will, so the delay ensures that there is also a redundancy in terms of time. It's not just physical duplicacy, it is also a redundancy in terms of the time of the execution, and it may remove a bit of the common cause failures also. So here the comparator would keep on checking the output coming from the main and the checker core, and then it will always indicate a fault if the two do not match up in the final. So same input, if different output, then a fault would be indicated. But the disadvantage traditionally of this architecture would be low performance, because effectively you are using two cores, but you are getting the performance of one in terms of execution. And secondly, lockstep implemented this way would be fixed in hardware. So there is no flexibility. You are stuck always with the lockstep. You cannot use the other core for any other functionality. So then in industry, there are innovations around how do we solve this performance problem also. So one way is it's like a hybrid mode or a software redundancy. It's a way of implementing lockstep, but through software. So here imagine we have a core 0 and a core 1. You can have a separate checker core which can again check the outputs of these two. So rather than a hardware, like we said, the cons of the previous one was that it was fixed by design, it was fixed by hardware. Here you can still run different tasks on core 0 and core 1. At the time of software redundancy or software lockstep, let's say for a particular application task C, you want to declare it as ASIL-D. This application requires a higher safety certification. So in that case, you run the same task on both the cores and you compare it in the safety island through a separate core 3. So in this implementation, safety is still a priority over performance, and you can run two independent applications with the output checked against the golden expected, or you can check the same application on the two cores and then check it by the checker core. So these are different ways of implementing lockstep again. But the best architecture still in terms of the core redundancy as well. So best of both worlds in terms of both performance and safety. So this is the split lock or the hybrid mode. So here what it means is, this we have picked from the ARM white pages. So this is publicly available. So here if you see, this brings us both. So there are two modes. The hardware architecture is flexible in terms of there can be a split mode where the two cores could run as individual cores, each running their own application. So it is higher on performance side. Or they could be in lock mode. So when you need so like we said, we are going towards software defined. So you know that in one context, safety is more priority over performance, and in one mode maybe the performance is a higher. So based on the application, you can choose whether to have the cores in the split mode or in the lock mode. So with this flexibility, you get the advantage that you can always couple compute performance with high safety integrity. And it brings the flexibility which was missing in at least the first implementation, the hardware lockstep. and on the fly it allows the configuration by software. Additionally, it also allows fail operational mode, because once, let's say, one core goes down because of any safety event or a security event, you can still continue. The car does not have to abruptly stop. You can say, we'll continue with a degraded performance, moving all the execution to the other core. Okay, then the other type of functional safety which we implement is the cache architecture. So here, if you see, this is a traditional cache architecture. So here we have the tag space, we have the indexing, and we have the word. So we have shown a case of 32 kilobyte, 32 byte, and a two-way cache. So the way 0, way 1 are the two ways. And then based on the index we receive, we check it against the content in the DW to D3 for the way 0 and way 1. So, and then if you see, the ECC is where we are bringing in the functional safety. So with this, we even make the cache architecture functional safety aware. And every time you compare the data you are receiving by way of, you compare which is the hit, where did you hit, whether you found the content in one of the way 0 or way 1. And if there is a miss, then you can give you can invalidate and reload the line again on the tag and data. This only works for iCache and the write through Dcache. For write back, obviously you'll have to reset again and start over, because you'll have to re-execute the same instruction. Another thing we observe here is that as we implement these ECC logic, the timing becomes critical on these paths. So again, there are some innovations or implementation specific enhancements happening around this. One other way to reach a higher safety integrity is also fault injection and diagnostic coverage. So in industry, at least talking to the customer, we are seeing a higher focus on these also. What they are demanding is they need to know whether the design will detect a fault if it is there. So in these cases, we have to give evidence to the customer in terms of if there is a fault, what path it follows, and if it is detected. If it is non-detectable, then there's a coverage hole in terms of the diagnostic. So there also we have done a lot of, we have an environment in NXP to check the fault injection and the coverage coming out. So we have been running structural core self-test. So these are, again, it's a good example of how hardware and software can interact with each other. So we give this whole test suite of the core self-test to the simulation, and we provide the schematic in terms of either the RTL or the gate level netlist. There are tools like Zoix and other tools in the industry which can do the structural or the formal analysis. They do fault bucketization in terms of this structural analysis. So whether there is a fan-out, fan-in path which can detect if something changes in that path, would that get captured as a diagnostic or a status bit somewhere? So then, based on this simulation analysis and this formal analysis, and finally we inject the faults at different tapping points. Finally, the coverage report will tell whether, if, let's say, while you are driving the car on field, if a fault comes, either it should be safe fault, which means that it should be corrected by itself, or it should be at least a detectable fault. It should not go undetected, which means you can run into unexpected crashes and obviously leading to vehicle failure. So yeah, with that, at least the functional safety portion is done. Saurav, I'll move it over to you now.
Can you hear me?
Yes, Saurav, go ahead, please.
Yeah. So I will move into the security part of this presentation. So there are many things in security. It's a very vast field, but I have basically tried to capture the main points that are important for automotive and IoT chips, right? So the first thing that is very important is to secure our chips is control flow integrity. And Neha had mentioned it briefly. So this is a very classical attack where the attacker, what it does is it tries to actually override the return address of a function, and by that attack, they actually are able to take the code to their own attack code or some libc function. So if you can do next, Neha. Yeah. So in this figure, if you see, what is happening is the main function is calling a security check function through a jump command function call. And then instead of the JR returning back to the main, the attacker, by overwriting the stack, can take it to his attack code and then take over the entire software and hack your car. So how the RISC-V is actually working on some standard extension called the CFI SS, based on the concept of a shadow stack. So in the shadow stack, what is being done is the return addresses are separately stored in an architecturally protected memory region, not the regular stack, which is read-writable, but a shadow stack. And then when you are actually returning, you can compare the stack return address against the shadow stack copy. And if somebody has tried to override your regular stack and tried to take over your stuff, then this check will fail. And so the shadow stack is not read-writable by normal instructions. You basically need separate instructions that RISC-V International is defining. For example, I have shown a code snippet here, like in a function func, when you go in, the SS push X1 will push the X1 register. X1 register is your return pointer, right, in RISC-V, onto the shadow stack. And then before doing the return, the SPOP check will do a check if the X1 is equal to the stack return address or not. If it is not equal, it will take an exception and give a fault. Next slide. So that was the return address or the backward edge CFI attack. There is another type of attack called the forward edge CFI, where the attacker can actually override the function pointer.
Saurav, your video is hanging, I think.
Before you do a JLR, like if you see in the code here in the main, if before you do a JLR, you basically put a X7 register with a landing pad value of, just as an example, I have put 1, 2, 3, 4. And if it is supposed to go to function F2, it will actually, there will be another instruction with LPAD 1, 2, 3, 4 at that point, so that if an attacker has taken away the control, the CPU can give an exception. So it is very similar to the return address stack attack, but it is basically on the function call on the indirect jumps. Now, direct function calls cannot be hacked because they are read-only memory, or they are basically you cannot do read-write memory, but function pointer table is in read-write memory, and those can be hacked by the attacker. Next. So if you see here in that, yeah, so that's okay. So coming back to the, in a more general sense, what is control flow integrity? The control flow integrity is actually there to detect any modification, like even example for instruction skip or modification attacks. Now this can also be through hardware attacks. So in hardware attacks, what happens is, sometimes people can do under voltage of your chip, or do some power glitch, do some laser attacks, create some clock glitch, and what happens is then you skip an instruction. And what can actually happen is you may skip, there is a function in your code where you say, okay, I call to a security check function, and the attacker can actually skip that. And to prevent that, there are a lot of innovative ideas. There are some in NXP, we do some in-house proprietary CFI checks, which are working at instruction level and basic block level. The basic idea is that the execution of the nth instruction is dependent on the previous instruction or previous instructions. So if there is any type of attack, either by hardware or software, CFI can check it and create an exception. And moreover, you can also encrypt the binary, or you can use a raw binary. So in the demo, you would see in the XP area, there are two demos. Both of them are using CFI based on our proprietary implementation. There's a secure element demo where there is an NFC card reader which can do payments and security authentication. And there is a SDV demo that Neha also gives there where the secure boot is also using this CFI techniques. Next. Okay, so going from CFI, I want to just briefly talk about secure enclaves. And this is something I was mentioning before. Think of SDV, right? You have so many parallel applications running. Your OS is not secure. There is always a chance that some malicious software guy comes in and actually corrupts the important application that is running on the system. And for that, secure enclaves is the method to actually protect and isolate the important applications from other untrusted applications, including the OS. And this is beyond simple privilege level protection. This is itself a very big topic. I'm just giving a very brief idea how the hardware in RISC-V actually implements it. So from open source, there is a very popular secure enclave implementation from UC Berkeley called Keystone. Many of you can actually go and look at the implementation. It is also downloadable. It actually uses the physical memory protection unit PMP to provide the isolation. This is the block diagram in short, how you are seeing here. So you have the trusted hardware at the bottom. There is a new piece of software called the security monitor, which only runs in machine mode. And this software is actually part of the secure enclave implementation or Keystone. And this has the gateway to every hardware resource. So any application or OS which is running above it, either in supervisor mode or user mode, either in an enclave app or in a normal app, has to go through this security monitor to get hold of this physical memory protection unit or any hardware configuration via the machine. Next. So this is a very simple example what happens when you try to, in Keystone, what it does, how to provide the isolation. So in PMP, basically, suppose there are 16 entries in your RISC-V chip, and the top PMP entry is typically reserved for the security monitor because it is the highest priority. And the bottommost is done for the OS like Linux or any other OS. Each active enclave is assigned a PMP entry in the middle. And this Keystone uses the not a programmable of 2 mode. Each PMP entry initially has this read, write, execute permission bits RWX of 000. So nobody is executing anything right now. Next slide, please.
Yeah.
So when you have to execute a secure enclave, what Keystone does it flips the permission bits of the OS with to makes it 000 and makes the PMP2, for example, it has to run, makes it 111 so that it can use the enclave to memory, whereas all the other memory is unusable. So this is a very quick way of, and then it can destroy, there is a way how it destroys the security enclaves and so on. But this is a very short, a very quick discussion on how these Keystone and the secure enclaves work. Next slide, please. Okay, now going to the another very important topic, and many of you have heard about it. Processors, typically high-end, they are designed for high performance. There's a lot of speculation and out of order execution going on into the extent of hundreds of instructions within the microprocessor, right? And the big problem that you have here is the non-committed instructions. Suppose something happens, the non-committed instructions typically they discard the register and memory updates, but the cached memory contents are retained. And due to this, there are many attacks that the attackers have devised. The very two famous one are Meltdown and Spectre. So there was few years back when they tried to hack a huge amount of processors from various companies, and they were able to successfully demonstrate how, due to the speculation in the processor hardware, these two can be actually, these two attacks can actually take over your chip. And in meltdown, what it does, it is actually accesses the kernel memory from the user space, and so that creates an exception, right? But before the exception is actually issued, the instructions that follow the exception leak the contents of the accessed memory, and then the attacker uses a cache covert channel to basically expose the contents. Spectre, instead of using a exception, uses a branch predictor which is strict to thinking that the branch will actually be taken, and then using some user input X, as I have shown here example, it can go to any place in the array too. Very recently this year, there have been two new attacks called flop and slap. These are based on the load value and load address speculation, and they have been actually proven on a very famous microprocessor that is there in the market. So bottom line is large out-of-order processors are being used in latest generation automotive products. So it is very important to evaluate and mitigate speculation-based security risks as and when it is required. Next slide, please. So this is just on what RISC-V provides as crypto instructions. You can just go through the thing. I will not spend much time here. Bit manipulation instructions, carry-less multiply, you have AES decryption and encryption instructions, hash functions, SM3 and SM4 cipher functions, entropy source extensions. So you can actually go and look at these. These are standard crypto extensions RISC-V provide that your processor can support and provide security. Next slide, please. So coming to it, this is the conclusion that functional safety and security are key differentiators in automotive products. As RISC-V products adopt these features, they would be adopted in various automotive solutions. And companies in India are uniquely poised to actually benefit from this. And there's a large market of RISC-V in Asia. And if you can provide these security and functional safety features, these are the main differentiators why some big vendor would actually select your chip and put it into there. So it's very important that we actually focus on functional safety and security. Current and future trends, we are seeing a lot of work on post-quantum crypto due to this coming of quantum computers. You have to make your crypto algorithms quantum safe. There are customized safety solutions being devised beyond split lock and the hybrid solutions Neha mentioned. There is also this new trend of trying to leverage AI ML, say maybe a neural network type of training model to see if your chip is really in a functional safe zone or it has gone into some unsafe zone. These are some of the future trends. So that's it. I think that's, and we can take some questions if there are any.
Yeah, so we are open for questions now.
So this is for Saurav. Given the crypto computations and all being presented as one of the solutions to have speculation and also mitigate those, right? Like of late we've been seeing a lot of papers on these in the last few years. Do you really think that is the way forward, or should we drop speculation completely? Like this is a big, every month there is this huge new, within quotes, speculation attack. So what should out-of-order processor designers really aim for? Should they try to go the crypto way, or should they do less speculation as was done maybe in the early 90s? Like I'm just interested in hearing your thoughts.
Yeah, so my personal opinion would be no, we should not drop speculation, because that's the backbone of how the processors work. Many of these attacks are academic, to be real, right? So there is not so much benefit in doing so much effort and getting the hack out of it. So speculation will always be there in microprocessors, and it is not going to, I mean, it may not be as exponentially increasing as we have seen over the last few years, but I wouldn't bet that it would decrease. What will happen is more some microarchitecture features. For example, you always have options like serialization instructions, or you options have guarded memory, or in ARM language we call non-device memory, where your speculation stops. So you can put in all these micro architecture features that you have some sort of very secret data. So you would only load that data through a guarded access. For example, you will put a serialization instruction before it so that no speculation is done on that access only. That is a much lesser penalty than saying that I will stop speculation on the entire program. So these are typically the trends that will happen, that the software and hardware will work together and make sure the speculation is limited only in places where it is required. But I wouldn't bet my thing that the entire processor architecture would change.
Okay, thank you.
Okay, thanks all. Thanks for the patient hearing. Thanks, Saurabh.
Thank you. Thanks. Bye. I'll drop off.
Sure.
Our next speaker is Rabin Sugumar, CEO, co-founder, Akeana USA. He's going to be talking about RISC-V cores as multivariable, almost continuous functions. Rabin Sugumar was Distinguished Engineer and Chief Architect at Marvell KVM and built and led the architecture group for ThunderX ARM server processor line. Most recently, he led the architecture of the ThunderX3 processor, which had industry-leading single-thread performance and socket-level performance at the time of silicon. Prior to Marvell and KVM, he was at Broadcom, where he was one of the lead architects on the server processor that became ThunderX2. ThunderX2 was the first ARM server to achieve single-thread and socket-level performance comparable to high-end Intel Xeon servers and paved the way for ARM servers in the data center. During Rabin's career, he has also worked on architecture and design of vector processors at Cray Research, early multi-threaded and out-of-order Spark processors at Sun Microsystems, and InfiniBand adapters at the Sun Microsystems Oracle. Rabin obtained his PhD in computer science and engineering from the University of Michigan. The cache simulator he wrote during his PhD is still widely used in academia. Rabin has over 25 years of experience in CPU architecture and design and 28 granted patents. Over to you, Rabin.
Thanks, very nice to be here. Very nice to see you all, especially the students. You are the future leaders of India and global leaders, and I'm sure there are many CEOs and billionaires of the future here. So honored to be with you all at this time. So just in way of introduction, Akeana is about a 4-year-old startup. We do high-end RISC-V cores reflecting our background in high-end server design. We do high-end RISC-V cores, but we also do mid-range and low-end cores. We do interconnects. We do interrupt controllers, so the whole compute IP space. This particular talk is on how we do our RISC-V cores. With a relatively small team, we cover the entire range of ARM, for instance, core IP, and we do it in a somewhat innovative fashion, and we will talk here about how we do it. So just to start off, let's see if this works. It's not moving. Oh, okay, good. I know I'm preaching to the choir here, but you know, the modern digital world runs on CPUs. CPUs are everywhere. All software runs on CPUs, you know. So I mean, a few examples here. So let's see if the pointer works. Okay. So there are like sensors where you may have a small CPU that manages sensor functions. You have surveillance cameras all over the place. There are CPUs there that handle the acquisition of video and the storage of video. There are robots with many CPUs that control a lot of intelligent functions. There are obviously CPUs in data centers and supercomputers that run Gmail, you know, our webmail, our searches. There are many, many CPUs in cars, like the previous talk they shared. CPUs do the actuator function, sensors. They also, you know, do the autonomous driving and the higher level intelligent functions. So CPUs come in a vast range of sizes, right? So you can have a small microcontroller core in a sensor that is less than like 0.01 millimeters squared in, let's say, 16 FFC, which is a relatively modern processor node, about 10 years old. And also there are CPUs in like supercomputers that are really big. So a CPU in a high-end mobile phone or a supercomputer could be greater than 10 millimeters squared in 16 FFC. And that is a huge range, right? That's a 3 orders of magnitude range of sizes. It is unusual. If you look at cars, maybe there is a 10x range of sizes, maybe a little bit higher for ships. But here there is a 3 orders magnitude range in area. The performance range, interestingly, is lower, right? Maybe there is a 20x range. And so there's a question of why are we spending so much area to get so little additional performance? But the CPU is a small part of a larger system, and the CPU performance determines the performance of the larger system. So it does make sense to spend superlinear area for a certain performance increase in CPUs. Let's see if this works. Okay, let's go back. Okay. Across this vast range, right, we talked about 3 orders of magnitude range of sizes. The basic pipeline architecture of CPUs is remarkably fixed, right? You fetch instructions that tell the CPU what to do. You decode the instructions to figure out what the instruction is saying. Then you execute the instructions, arithmetic, logical, or load or store to get data or store data, and then you write it back, right? So the basic pipeline is very fixed. So in Akeana, we exploit the fact that the basic pipeline is fixed to design CPUs out of the single database, which we'll talk about in future slides. CPUs also differ in several dimensions. The previous talk talked about some of these aspects. So just to kind of go through the list, right, there are lots of privilege levels. You may have just a single privilege level for a very simple CPU. Then there is user mode, supervisor mode if you want to run Linux, and then also hypervisor mode if you want to run a hypervisor. There is address translation, right? Is there no address translation, or is there a virtual address and a physical address? There are various security features that the previous talk covered really well. There is protection. How do you protect different parts of the CPU from different parts of the address space from other parts of the address space, which is also covered in the previous talk. There is address width. How wide is your address? 32 bits, 56 bits, 48 bits. Data width, is it 32 bits wide, 64 bits wide? Various arithmetic operations. Do you do floating point computation? Do you do crypto? Ordering rules on how loads and stores are ordered. How do we detect errors? Debug support, how do we interface into the CPU and debug if there is a problem, trace support to see what software is doing, and many others actually. So those are all behavior related. And then on the performance front, there are features that we all know and love, like caches, levels and sizes. They have huge impact on performance. Again, branch predictors also have huge impact on performance. Lots of new ideas there, lots of types and sizes. Pipeline depth has a huge impact on frequency. We talked about those 5 stages in the previous slide. But to get higher frequency, you have to break up each of those stages into many smaller stages in modern CPUs. In order, out of order, again, whether instructions are executed in order or out of order. The various widths about how wide the pipeline is. How many instructions can you fetch, decode, dispatch, retire? How many key instructions can you issue? Depth of various queues and buffers. SIMD, whether we have vector or not. Number of load store pipes, translation tables, TLBs, how do you do it? Is there 1 level, is there 2 level? How large are those TLBs? Multi-threading, where you execute multiple contexts in a pipeline. So there are all these different features that we can add on to that basic pipeline that we saw to create these different types of CPUs. So in Akeana, the way we do it is we build the basic pipeline, right? So this executes the basic RVI instruction set. And then all these other features that we talked about, like caches and branch predictors and in order, out of order, all these are features that can be configurably added on. So all of this is done in System Verilog. It's not like there is a different language that is generating all this code. It is just highly configurable System Verilog. And so from a single database, right, if you look at we specify our configuration as a YAML file. So there's a YAML file on the left there. This defines a small microcontroller. So this is less than 0.05 millimeters squared, pretty small chip. And then we have another YAML file on the right, which defines a higher end core, not our highest end core, but pretty higher end. And this is greater than 5 millimeters squared, all coming from the same Verilog database, right? So super small microcontrollers on the left and very large cores on the right. So just to go a little bit more into that, right? So we have, as I said, a very rich portfolio of cores. There is a picture later on that shows a little bit more here. So our portfolio is comparable to ARM from their Cortex-M line, their Cortex-A line, their Neoverse Cortex-X lines, built by a pretty small team of less than 100 engineers, very experienced team, but a pretty small team. This allows extreme flexibility in mixing and matching features, right? I mean, as we go forward, especially the process improvements are tapering off. So the way to get more performance, better PPA, is to optimize more specifically for specific application verticals. And what we need is this flexibility to do that, which is what this approach provides. There is also the fact that, let's say that, we want to develop a new feature, hypervisor, let's say, right? So we develop hypervisor as part of this one database, and that is available for all these different configurations. In many other companies, right, ARM, for instance, there are specific teams for each of these CPUs. And so something like a hypervisor would have to be redeveloped for each of these cores, which is where the explosion in team size and bugs and other issues come up. Also, bugs, timing, power, all of these you fix once and they are available across a range of configurations. Since they're all coming from the same database, you fix a bug in one instance in the database, then it is available across all those configurations. We talked about the ability to customize cores for a specific vertical. We can, because all of these are configurable features, by dialing up these features, we can go to even higher performance levels. So it's a way to build up performance. Obviously, they're all coming from the same database with similar designs, so the firmware compatibility is there, very important. If in ARM, for instance, there is not even ISA compatibility between the different lines. So it's a completely different code to run on the different CPUs. And then also SoC level design compatibility. What are the interfaces? How does debug interface into the core? How do trace work? All of these are exactly the same across all these configurations. So this pictorially shows how our RISC-V cores compare against ARM cores, right? So the little bit on the y-axis we have performance, roughly based on Rystone, and on the x-axis these are different types of cores. So each of those blue dots is one of ARM's cores, right? So you have M0, M1. So at the left, you have all ARM microcontroller cores. And corresponding to them, you have the Akeana 100 line. So we put in 4 Akeana 100 points. But because all of this comes from a single database, it's actually a cloud, right? We can move up and down the space. Similarly, in the middle, we have the Cortex-A line. This is ARM's mid-range cores, both in order and out of order. And again, we have the Akeana 1000 series that maps against this. Again, we do these specific dots, but we can move performance and features across the range here. And we actually show one example where we went from one core and the customer wanted higher performance, and we are able to tweak that configuration to get higher performance. And then at the very top, we have the high-end Akeana 5000 line. So this maps against ARM's high-end Neoverse and V1, V2 cores, N1, N2, V1, V2 cores. And we have cores that map against all of those as well. And as I said, all of these come from a single database by creating different YAML files to define all these different configurations. A couple of examples in the next 2 slides, right? So this shows how this is an in-order core design can be repurposed for many different purposes, right? So the Akeana 1200 can have full RV823 compatibility. So RV823 is a profile that RISC-V defined last year. So any core that complies with RV823 can run a set of software that complies with RV823. It's a way to standardize RISC-V designs. So when we have full RVA23 compatibility, it can be a little core in a big little Android cluster. It can run a hypervisor. It can run all the normal applications. In the middle, the same 1200 can also be used as an accelerator in an AI implementation, where it is used to run activation functions fast. So here, obviously, you don't need a hypervisor. You may not even need an MMU, so you take that all out. You add wide vector, right, because that's really where the activation functions kick in. And now this becomes a CPU and an AI accelerator for activation functions. And then a little bit more extreme on the far right, we may need a CPU for just data movement, right? It's not executing any code. All it's doing is its data movement, somewhat flexibly, right? So here we can defeature again the hypervisor and MMU. We don't even need the wide vector compute, but we do need the wide vector load and store. So we just have a register file. We support vector load and store, and that becomes a data movement engine. So it's an example of how using this methodology we can transition our designs across many use cases. So this is one more example of how this can be used, right? So you can think of all the feature options of Akeana as like, dimensions, right? So let's say that you take issue queue depth, right? You can have an issue queue depth of 8. You can have an issue queue depth of 9, right? Think of it, each of these as dimensions in an n-dimensional space. As the issue queue depth increases, then the performance, for instance, will increase. The area will also increase. So similarly for other dimensions, right? Maybe reorder buffer depth, maybe fetch width. These are all like dimensions in this n-dimensional space. And changing each of these will change area or performance or power, right? So then if you look at the area of cores across this n-dimensional space, they will form a surface in the space, right? Similarly, if you take a specific application and run it for performance and power, the application performance and power also forms a surface in this n-dimensional space. It's not continuous. These are discrete functions. But because of the very fine-grained nature of some of these parameters, it looks almost continuous. And now we can apply optimization algorithms to pick the core with the best PPA for an application, right? So there are lots of optimization algorithms that can be applied across such surfaces. So we can apply any of these optimization algorithms. So given a specific application vertical, we can go through this space and find the core that is best in terms of area, power, and performance. This we think is going to be very important going forward, right? We are right now at 2 nanometer. Maybe we'll get to 1 nanometer, but things are beginning to dwindle. And so architecture is going to become more and more important to eke out additional PPA and performance gains. And this kind of flexibility and this kind of vertical specific optimization is going to be important going forward. A couple of notes on validation and physical design. There are pros and cons, right? So the pros we talked about. There is much commonality between the designs. So you fix a bug in the database, it is applicable to all the configurations. You do a timing fix, it is applicable to all the configurations. Power fixes, again, applicable to all the configurations. Also, right, in validation, there are all these corner cases, and certain configurations is easier to hit, right? Let's say your queue size is very short, then it makes certain kinds of bugs easier to hit, right? And so because we have all these configurations, our coverage is better in certain ways, right? But the cons are, there are all these different configurations, and while there is a lot of commonality, each configuration has its own coverage corners, And so there is more validation to be done across all these configurations to hit all the configuration-specific corners. So we have created methodologies to deal with this. That is a big part of what we do. But yeah, the validation space is obviously broader. The other thing, right, and this is something we are still trying to figure out, is there is a certain approach that is needed in the design to make it this configurable. And are we losing timing at the very highest end because we are making it so configurable is an interesting question that we are still trying to figure out. If that is the case, we do feel that at some point we may have to create a custom branch in Git, for instance, right? So if a customer says that I want the very highest frequency, we may have to branch it off in Git and do special purpose work for just that specific configuration. And though we have not had to do it so far, it's possible that we may have to do it. A few pictures, right, of like, higher end cores and lower end cores. This is not to scale. So the core on the left and that core on that far right down corner is probably like 100x difference in area. This is not to scale, but it just shows the different PD. And you can see though the sizes are very different, you can see that generally they are similar, in terms of like how the different blocks are laid out in the floor plan. A little bit on what we provide at Akeana. So it's a very comprehensive processor IP portfolio. So on the top left, we have the processor cores. We already talked about the Akeana 100 series, the microcontrollers, the Akeana 1000 series, the mid-range cores, and then the 5000 series, which are the high-end cores. And then on the bottom left, it's our interconnect fabric IP. So we do scalable, non-coherent, and coherent meshes, all based on the AMBA protocol. So this one shows a highly scalable mesh. It could be coherent or non-coherent with HBM and PCIe Gen 7, more like an AI application. And then on the bottom right, we have all the neglected IP that is super important in a system. That is IO MMUs, that is interrupt controllers, that is PCIe write caches. All of these are important for actually building a compute subsystem. And then on the top right, we have our AI accelerator hardware. So we have MATMUL engines, data movement engines, and other such to build high-end AI chips. Everything that we do is IP, right? So we do some reference chips, but our business model is to sell IP. Couple of system solution examples that are popular. So on the left, we show a small cluster. So this is a big little core configuration potentially in an Android deployment. There are a few cores that is like L3 cache with coherence framework, and this forms a self-sufficient with an interrupt controller, and this forms a self-sufficient compute subsystem. And then on the right, it's the same picture as the previous slide. Each of those CMUs has a CPU for accelerating activation functions. It has a MATMUL engine. And then those tiles are then duplicated many, many times to create very high performance AI chiplets, right? So this could be as high as the highest end of NVIDIA's GPUs. And that's it, thanks. Any questions? Thanks.
So we'll have one more talk, and after that, we'll take a very short break of about 10 minutes, and then we'll come back for the panel discussion and a talk from Voma Systems. Before we break for lunch, we are running a little late behind schedule, but we'll take a shorter break, 10 to 15 minutes. The next talk is Startup Support and Incubation for Semiconductor Companies by M.J. Shankar Raman, CEO, IITM Pravatak Technologies Foundation. Shankar Raman holds a BE in Computer Science and Engineering from Sri Venkateshwara College of Engineering and an MSc Engineering from the Indian Institute of Science, Bangalore, PhD from IIT Madras. He began his career at Wipro Infotech and later worked at HCL, HP, R&D, and Cisco Systems, specializing in network management and security, where he published a patent for DDoS attack deflection. In 2004, he co-founded Sahasra Solutions, focusing on embedded systems and storage technologies. Shankar Raman joined IIT Madras in 2009 as a PhD candidate. And since 2021, he has been the CEO of IITM Pravatak Technologies Foundation. He has published works in networking, VLSI, and software testing.
Thank you, Dr. Nitya. I don't have any slides because what I'm going to do is partly a sales pitch and partly I'm going to explain about how you can use our incubation ecosystem to get startup companies which can later go and start using DLI, PLI and other things of the government of India. We are a seed incubator. We are formed under the National Mission for Interdisciplinary Cyber Physical Systems, in the areas of sensors, networking, actuators, and control systems. And one of our seed-funded companies is MindGrow, which is one of the sponsors for this event. So what was our aim and goal when this mission was established? We started functioning in 2019, but at that time the COVID struck, so 2020 was gone. And at that time we never had any of this DLI, PLI, and there were a lot of semiconductor companies which wanted to start doing in India, startups especially. So we tied up with some major EDA vendors, and we told these companies that we'll give you these tools free of cost. We also will give you some money. Then you return back to us all these things when you go to the market. I think this is the best scheme you can have. And we'll also give you space in our location. Okay, so what else do you need to start a EFAB? Okay, and the number of applications we received were 1 or 2. Okay, that's the problem. Okay, so I want these young engineers to start thinking big. Life is not about AI/ML. Okay, it is about processes that make AI/ML work. Okay, so yesterday I was in this meeting on AI/ML, Chintan Shivir, and I was telling that today the greatest problem we are facing at AI/ML is not because we don't have process, but processes are not getting utilized properly, where we are not getting one instruction done at 1 clock cycle, which is going to be the ultimate limit, right? Then you can talk about superscalar and all that. First get 1 instruction per clock cycle, then we'll talk about 5 instructions per clock cycle. Okay, and we have been talking about, and the major problem that we have seen after analysis of all these AI/ML models is just L1 cache. Okay, so the fundamental problem, von Neumann's bottleneck, still remains. We are talking a lot of big things about, so capturing the world with AI/ML, but if your process don't come up to that speed, because otherwise the power that your process are going to consume is going to be massive if you really want to do those kind of operations. Now, I would request many of the young engineers, because we are concentrating in 4 areas. One is technology development, entrepreneurship development, skilling, as well as international collaboration. We promise you that if you have good architectures, we can even take you internationally. Okay, so what else do you need for an ecosystem where you get free tools, money, and I'll also tell you, we have some designs also with us. If you can come and implement those designs and start the company, I'm fine with it. Okay, I don't think you can get a better ecosystem than this. And still, if you search for AI/ML, there is a problem. Okay. Now, coming back to what we do with technology development. So our idea is to get something fundamental for this country, okay? And our goal is Atmanirbhar solutions, okay? Even though we have made processors, I know MindGrow, okay, they are struggling with IPs. Okay, these IPs are very expensive, because the previous speaker will tell you how much of effort they have put in to get one IP going, and they will charge you so much. Okay, so one way we could look at is, can we bring our own IPs? Because we still have got a long way to go. Our manufacturing is still not in place. How did MindGrow come up with the chip? They had to tie up with TSMC. Who is going to do the back end? Yes, we have to get TSMC engineers or someone from Bangalore to do it, okay, who are closely tied up with TSMC. So the other things that we are working on, we are trying to get a fab at IIT Madras for academic purposes, okay, where you could try out your designs, we could help you tape out those designs and things like that. So this is the kind of ecosystem we are trying to bring in. And how is it easy for you to apply? We have a website, or you can even contact Lavanya, who is organizing the Voma systems, who is also part of our seed-funded startups. Okay, you could approach them and they will give you a guidance on how to approach us for doing this kind of design and starting your startup. If you are not interested in a startup, please come and work technically. We will share the IP. Okay, I'm willing to share the IP with you. And we will take it to market, don't worry. Okay, so this is what kind of ecosystems that IITM Pravartak provides. Okay, if you want, you can visit us. We are in the B block, first floor. So that's one part to it. The second part, how much money do we give? Okay, so there are 2 or 3 options that we have. You can join us after your BE as entrepreneur in residence, where if you have an idea that you come up with, we'll be glad to support the idea. Or if you are willing to implement our idea, we are glad to support you. Here we pay about 30,000 rupees per month and also give you about 3 lakhs for purchasing some tools which you might need. Okay, other than the facility that we give. Now, if you can get something out in 1 year, then we can give you up to 50 lakhs. Okay, there you have to get a patent. Okay, so you could work on you can use it up to 2 years. That status, what we call it as Prayas. Nidhi Prayas is similar to Nidhi Prayas that is being announced by DST. And the third stage is we will give you another 50 lakhs so that you can have your startup. Okay, so you could, get up to 1 crore for this activity other than 1 year. So the whole process takes about 5 years and you get incubated at IIT. For the whole process, we take about 5% equity in your company. Okay, so we value you somewhere around 10 crores in the beginning itself so that when you go for negotiations with the VC, you can get a much better valuation. Okay, and if you want to know the stories on those things, talk to people in MindGrow. They will tell you a lot of stories, or Incore. Okay, Incore is not incubated by us, but they will tell you stories on how to talk to VCs and get money out of it. Okay. Now, so this is the stage that we handhold you through. Okay, so I hope after this we'll have more applications that are coming to us. Now, the good thing is that we might even tie up with the government to get you the DLI and PLI also. So we could be like sort of one-stop shop for you to come up with the complete design and productization of RISC-V. By the way, it's a RISC-V. Okay. So this is in short what as Pravartak we do. So any questions? I know I want to make it short, but I want more questions from you because rather than me telling, because the whole idea is I will show you companies which you have groomed. I'll show you companies demonstrate, but how many of you are willing to come back if you are interested? Please ask me questions. It's a very short speech. Any questions? Yes, sir, but if you have a mic, it will be good. I think after listening to the 3 sessions, this is the first question I am hearing, so thanks.
Okay. My name is Achyutan. I would like to introduce this AI for agriculture purposes because I have some beautiful idea. Of course, I'm not a youngster. We got a 13-year-old company, and where we would like to introduce AI using Shakti. Yesterday I had a talk with one of your research scholars. So how will I get into it?
Okay, sir. There are 2 parts. See, under the National Mission for Interdisciplinary Cyber-Physical Systems, there are 25 hubs that have been established all over India. And the hub for agriculture is IIT Ropar. Okay. Now the point is, where is going to be your application? If you are looking at developing an embedded box which can be used in agriculture, okay, then you could ask for support to us. But if your application is completely agriculture, then they are the hub who could support you financially, but the work can be done with us if you want. So this is the, because it depends on where you want to apply. See, you can apply Shaktiman, that's fine.
Yeah.
Okay. But the point is, if the application is, agriculture, then the hub has to fund that.
No, it is not agriculture. It's a product for agriculture to add value to the customer, villages. So it's a product development. Already product is developed. So I would
then let me know the details because
I'll approach you. Definitely.
Let me know the details, then we'll be able to tell. Because now I am not very clear whether you are going to work on
I will.
Chip design or the system design part.
No, chip design is, microcontroller is working. So one other thing, I would like to introduce AI into it so that the product will become much more acceptable. And it will be more useful to the, well, I'll have a one-to-one talk.
Yeah, sure, so you clarify it offline. Okay. Yeah, sure. Any other questions? Yes, sir. So there is.
Sir, my name is Keshav. I am from Chennai Institute of Technology. So, sir, we are now currently working on a Cube satellite project. CubeSat.
Okay.
For that, we need to design a processor. And can you just give us a list of tools available with you?
See, if you are looking at any of Shakti is open source, right? You can take up Shakti and start working with Shakti. Okay, and
Yeah, okay.
sorry.
Yeah, tell me.
So you can start working with Shakti, and if you come to a certain stage, because the initial design can be done with Shakti. Later, when you want to make it as a chip, is where you need a lot of support, right? So you can use BlueSpec, get the Shakti design up, okay, for your use, and then you can come and approach us that we have gone up to this stage. What is the help that we can do? Yes, we can definitely do at that point.
Sure, sir. Sure, sir.
Okay. Yes. So in the front row.
Hi. You mentioned you have an IP support. What kind of IP are we talking about? Is it interface or is it like compute or, would appreciate if you can elaborate on that.
Sure. So currently what is happening is that, the people design the process and especially Shakti and then the other interfaces such as USB and other things. We really don't, they really want to get it done immediately, okay? They don't get it. So what they do is, when they come to us, we have tied up with a company which gives them those IPs and then we take it to the fab. Okay, so that is the kind of IPs that I talk about. And if these people want to have their RISC-V process along with some other company's IP, okay, they are welcome to use us and use our ecosystem to get this done. Yes.
Okay. Thank you.
Okay. So we are open. Actually, we were talking with the Saracen chips also, whether we can have a tie-up with them because they have their office in the US and they have some IPs for RISC-V. We are in talks with them. We haven't just opened up completely with them. But then at the end of the day, the IPs is the company's business because I do not know what product they are going to come up with. So it depends on what IPs they want to include.
Yeah, but irrespective, there is a possibility of having standard interfaces.
Yes.
Like, DDR4, PCI Express, USB 3, and
yes, so we are very open. You could have a MOU with us. Okay, and you could tell the companies to use those IPs, and we can open up our environment for usage of your IPs also. So we are very flexible because we are not tied to one vendor.
Okay.
Okay.
Excuse me, sir.
Yeah.
My name is Vineet. I'm a third-year EC student from SSN College of Engineering.
I am very old, so just.
My name is Vineet. I'm a third-year EC student from SSN College of Engineering in Chennai. So I noticed in the talk that you mentioned that directly from finishing BE, we could either create our own startup or join existing products. My question is that, especially in college, many students aren't really aware of what's going on in the industry. We just hear things and we don't know exactly how it works. So I was wondering, is there any process of guiding us or what you're expecting from BE students in general?
Okay, see, my very frank opinions, I've given talk with a lot of industries, in a lot of institutions, we have a tie-up with many of the institutions. I don't want to name the institution. The problem that I face is, yes, we go and talk to them. The students are very enthusiastic, but then after that, nothing moves. Okay? So what we have done is we have opened up our website. Okay? In our website, you can go ahead and apply. We do a technical evaluation of whatever ideas you provide. Okay? At any of the 3 stages, even entrepreneur in residence or SSS, or this year we have just closed the website. We'll open it again in April. Okay, because we have about 600 or 700 applications which we are evaluating. So it takes some time for us to evaluate. But let me tell you, less than 5% is in VLSI. So you might get your priority if you apply in the space of chip design. Okay? Yes, this is open to anyone. The website is open to anyone. It's a question of whether we don't have sign up with MOUs because our aim has been that we have signed MOUs with lot of universities and colleges and they have been used, those MOUs have been used by many of those institutions to increase their rating in NARF rather than really working on chip design. Okay, so this is the problem we have been facing. So as students, you can directly approach. If you have your guide who is interested, he can also approach. We have approached many institutions but have not got much of response from them back because they say that, look, we have tools that the government already gives, but none of, unless you make a product out of it or at least an IP out of it, it's only a exercise in futility. Okay, so probably if interested students can approach us, we'll be able to help you out.
Okay, thank you so much, sir.
Thank you. Yeah, so on that side.
Good morning. My name is Suri Sharma. I'm the founder of a company called Vedya Technologies in Bangalore. So I started this company about 3 years back, and we are a DPIIT recognized company based on 3 problem statements, out of which one we have solved right now after 3 years. So we have other 2, which are hardware-based real-time scheduling system, which is primarily being used in avionics and advanced aerospace engineering, which we want to start building because we just completed one. And similarly, we have similar products which are there, which today we are importing at under very heavy license fees, which we get to understand from DRDO. I have had this initial discussion with them, and I wanted to explore if this is possible for us to work with Pravartak.
Yeah, absolutely. Even companies which have good technology can work with us, but the way we operate could be slightly different from the way I'm helping the incubators or the startups. Yes, we can even have a tie-up and work with other companies also. Especially we are planning to concentrate on aerospace because aerospace and semiconductors are 2 areas that we are planning to concentrate on, and we have welcome any collaboration with any of the companies that wants to work in that space. So there was one person on that side.
Yes, sir. So I'm Abhinav. I'm a second year student doing my BTech in electronics, and I kind of wanted to know, I was introduced to RISC-V in my year 1, and so I've slowly started learning about the field. And so you mentioned how students kind of drop off after the initial hype of startups, right? They have, so my personal opinion on that is, once you get an idea as a student, we have this kind of lack of confidence that we have the skills to implement it, or we have this particular idea, but to approach you, we need to also know the tools associated with it and all the other things. So one student may be like, oh, I have this idea, but then how will I implement it? So why should I approach you guys? Because I don't know how to do the tools or anything related to it. So I learn it first and then approach it. But by the time I do that, it's already a bit too late to come up and...
Yeah, absolutely. It's a chicken and egg story, right? I mean, at the end of the day, but you have to plunge into this. This is exactly the reason these technology innovation hubs have been established, okay? They have been established, even if they fail, it's okay. That's what the government has come up today and said. Because they have said that one of the goals for us is we have to make money on our own within 5 years, otherwise we are out of the business. Okay, this is what strictly the government has told. So yes, you have to do experiments, but the whole idea is, remember, skill comes based on failures, okay? So, and failures to happen, you have to spend a lot of time, because when a failure happens, giving up is one. On the same day, I want to get this up, you have to spend extra hours. I have seen in many of the colleges, at 4 o'clock, the professor sits inside the bus, after that the students follow them. If this is the kind of thing, you really cannot achieve anything, noteworthy, okay? So you have to start spending extra hours, okay, because I know your syllabus and everything is there. That is only 5 hours of work every day. But what happens to the next 3 hours? Okay, and what happens to the next 4 hours? Because I'm not like Narayan Murthy, but at least I can tell you that at your age, you are supposed to work for at least 10 to 12 hours and get these skills. And later, your intelligence can come in. Because if you don't have the skills, see, for example, I have seen electronic engineers who doesn't know how to solder. And what's the point? I mean, they come out of this without knowing how to solder. And the good point of that we conduct course in a place called Swayam Plus. Okay? And there we make money out of it, teaching them how to solder some chips. Okay? But at the end of the day, I'm making money out of these things. But you should know to work on the board hands-on first and then move on as an electronic engineer.
So working on chip interior is similar. You have to get your skills straight. Okay, you have to work on the tools. Where is the option? Yes, you can look at these kind of hubs, get these options, work with them, and then do it.
So one last thing is like, let's say we have the basic skills, as in like we have a basic implementation of what we have. But then when like coming to like a product based, like to release it as a product, obviously there'll be higher level of rules, restrictions that we have to follow, right? So when it comes to implementing that, will we be giving any lenience on learning during the...
Absolutely. See, nothing is basic, nothing is advanced. That's my viewpoint, okay? See, at the end of the day, you start implementing, you start facing problems, then you start learning. Okay? What is basic? So, you have tools in your college. How many, all the colleges are part of that scheme, right? Some government scheme. What is the kind of chips you are designing? Okay, that's, you are taking it as a fourth year project. And after that project report is done, everything is forgotten. This is where exactly the hubs come in. After you finish the project, do you want to work with us? Or you want to find a job in a service company? These are the two choices you have. Okay, because the entrepreneur in residence course is especially designed for people who don't want to go for a job, but who want to go for a startup. So if you are clear in that, I think your path will also be clear. So this has been our experience. There have been people with us who have joined companies, they have resigned from those companies, became entrepreneur and residents, and today they are working on certain areas, which I mean, now they are working on what we call as preventive maintenance and other areas. Yes, sir. Yeah. Okay, is that okay?
Yes, sir. Thank you.
Please approach Pravartak. That's it. Short answer. And this kind of ecosystem never existed in India before, for your information.
So I would like to add to what Sir has been saying. It's a very fantastic presentation, what he is making here. So as students, right, so in second year, third year, you will be learning digital electronics, you will learn analog electronics, you will start learning how to use tools like SPICE, you know what is VHDL, Verilog, and other things, right? So IIT has already built the core Shakti, right? And like similarly, CDAC has built the core Vega. But as everybody was asking about like, okay, IPs, right? IPs are nothing but a set of protocols, standard protocols that you want to implement. So one of the things is like, as a school, as your college project or something, you can take up one of the IPs like I2C or SPI, or you can take UART, or you can take something like simple IPs, and then like start building them as a project. Rather than I see many of the times people take Arduino and then connect 3 or 4 sensors and then like write some application and see I am capturing this, capturing that. That is well and good. Okay, you are learning another software, how to coordinate and work with various microcontrollers and various software, that integration. But at the end of the day, if you have the ability to build your own microcontroller, if you have the ability to build your own IPs, what is IPs? It's nothing but an RFP. It's an RFC where you have the protocol is very clearly defined. And that if you take it as a project and work with the Shakti team or work with Incore or work with MindGrow or work with Vega, you can have your own IPs also integrated. And in less than a year or 2 years, we can have a plethora of IPs which can be used. And Pravartak will be more than happy to support you. And you have to think differently. What I can do is different is a question, but there are so many things that you can do, but you have to think very differently. And you can make it happen.
See, two things. Last one, if you build a beautiful IP, companies will buy it also. One. Second, open challenge. I have got a network processor design based on RISC-V. How many of you are willing to come and contribute and get it into chip? I stop my talk here. Okay. Thank you very much.
Thank you, Shankar Raman. We'll be taking a short 10-minute break, and we'll be starting our panel exactly at 11:05. So if you want to take a break, step out, there's tea and coffee. Otherwise, you can just stay back here. It's a very interesting panel on navigating Indian startups, and we'll be starting around 11:05. So please be back soon if you decide to take a break. Thanks. Welcome back. We'll now have the panel, Navigating Indian Startups in the Semiconductor Ecosystem. The panel moderator is Preet Yadav, Head, India Innovation Ecosystem, NXP Semiconductors. Panelists are TR Shashwat, CEO, co-founder, Mindgrove Technologies. GS Madhusudan, CEO, co-founder, Incore Semiconductors. Rabin Sugamar, CEO, co-founder, Akeana USA. Vishesh Rajaram, Managing Partner, Special Invest Advisors. Bios for people who have not presented earlier. Preet Yadav is going to be the moderator. He's head India Innovation Ecosystem at NXP Semiconductors. Prior to rejoining NXP in his second stint, he was working with Wipro at Analog Practice Head, distinguished member of technical staff, Wipro senior member leading analog and mixed signal practice globally in VLSI Technology Group. He has more than 2 decades of enriched research and development experience in the diversified semiconductor industry. His expertise includes analog and mixed signal design and verification, core technology development of process design kits, and electronic design automation. He received his B.Tech degree in ECE from Kurukshetra University, an M.Tech degree in VLSI design and CAD from Thapar Institute of Engineering and Technology. Vishesh Rajaram is the founding partner of Special Invest, a venture fund focused on deep tech, specifically space, semiconductors, manufacturing, health, energy, and AI. He has over 18 years of experience investing in India and venture capital and founded Special Invest in 2016, which has since invested in over 30 startups, including notable companies like Agnikul Cosmos, Mindgrove Semiconductors, Morphing Machines, E-Plane Company, Galaxy I Space, and Firmbox Bio. GS Madhusudan is the CEO and co-founder of Incore Semiconductors, India's first processor IP company. He was also one of the co-founders of the IIT Madras Shakti processor project. He is a veteran of the electronics and computing technology industry with nearly 4 decades of experience in tech startups and R&D organizations across the world. He is an advisor to various government departments and was a member of the GOI AI task force. Over to the panelists.
Okay, thank you. Thanks for the kind words. And we are just delayed by 20 minutes, and I'm being asked to, speed up fast, accelerate fast, and one of my colleagues has a meeting already, so we'll try to, go as fast as we could and as minute as like 1 or 2 nanometers. So I come from a product-based company, but I'm being surrounded by, venture capitalists to my extreme right, and on my left and right, Indian startups, and on my extreme left, US, based startup. I think I put together more than 100-year experience on these 5 chairs here, and let's try, extract all those 100 years in next, all those good experience of 100 years in next 35, 40 minutes. So as India, we are sitting on a $5 trillion ESDM thing which we can in cash. But if we typically, go and see any shift in economy, so that goes into 3 stages, Primary, most of the times, agriculture, same goes for us in India, and then people move to the secondary economy, which is largely manufacturing. And when I say manufacturing, that doesn't mean manufacturing of chips, okay? So if we take our own example, it's like typically a steam engine, water power, and, textile manufacturing, and gradually, going up in the swing. And then the dominant territory of any country. So some countries who have really come up are dominant of packaging house. There are few countries in the APAC region who have made that that big flagship in terms of manufacturing of semiconductors. And we as a country, we become a hub for the services. So IT services is something we really made a global mark as a country. And now we are, bounding back to the other things, and the recent one over the semiconductor side of it. But if you see in terms of manufacturing, and I'm particularly talking about manufacturing here because many of the forums I visit, I get many questions about semiconductor manufacturing, and thanks to the supply chain crunch a couple of years back during COVID, and that's what made us, famous. But we as a country, we are around, our whole contribution of the GDP is about 3.3%, and it's largely the more or less same, in the last few years. So, but we see, that's a good chunk of further growth we can get to. And at the same time, in the recent past, there were quite a good push from the different government agencies. I myself, I've used one of the tools sponsored by SMDP1 at that time, which started with, I think, 5 regional institute as the hubs, and then gradually, building up, and now it's about, if I'm not wrong, 200 plus institutions who are taking benefit of C2S. And then there are many other schemes, many DLI coming up, and thanks to India Semiconductor Mission, which has come up with many other, I would say, beautiful offerings. So with this quick about manufacturing part of it, that is a one story. We as a design, I would say, have really earmarked the global semicon system, and there was this figure which our ministry quotes about 20% of the global, design workforce comes from the Indian origin. So I think we have that well proven. You name any big, MNCs, they'll have their presence of design, and bigger or smaller way. Like the company I represent, NXP, almost 1/4 of the global R&D is based out of India in different sites. But now it's a time where we get the same kind of, I would say, at least that 20% kind of share in terms of startups, the homegrown startups, when we talk about the global numbers. Okay, so with that, what I would do is how we want to base this panel today is I would request each of the panel members to give a quick 2 to 3 minutes opening remark, the domain they come from or the organization they are coming from. And post that, I'm going to put them in a hard spot, asking a couple of round of questions. And thereafter, we'll, walk in as the room gets filled in to the audience question and answers. Okay. So I would like to, start from my extreme corners on left and right. And let me get to my extreme left, Ruben. So if you can share your opening remarks about, today's panel, which is navigating Indian startups in the semicon, particularly because I think, as I said, design as a multinational companies, we are done, tech marked well, and manufacturing we are really, packaging offset manufacturing we are stepping into. But from the startup perspective, because you are from Indian origin, based out of Bay Area, how you oversee, opening remark from you.
Okay, let's see if this works. Yeah. So as I just said, right, if people listen to my presentation, so we are a 4-year-old startup based in the Bay Area that does RISC-V core IP. The team is extremely experienced, more than 25 years of working together on really high-end chips. So we have a very complete portfolio of RISC-V compute IP, interconnects, interrupt controllers, IOMMUs, accelerators, so everything that you need to build a chip of any sort, really. So what we are looking for is silicon partners in India. So the team is experienced. We can help with a lot of the know-how that you would need to build a chip. Building a chip is actually, as many speakers have mentioned in this symposium, quite hard. Our team has done it many times, and we are actually very interested in helping the Indian ecosystem develop, build silicon. We do believe, the future silicon vendors of the world, like the Qualcomms of the world, will come from India in the future. So we would like to encourage and make that possible. So I would say we are looking for startups we can engage with. We are also increasing our presence in India. So a plug if you are interested in exciting opportunities in this area of RISC-V compute, do send us your resumes. Yeah.
Thanks, Robin. And now the only, richest person on the stage, I would say, who has enough money to invest.
Only person managing other people's money.
Okay, thank you. So Vishesh, a quick opening remark from your side, the background you were into and, the domain you work for the DPEC startups from the venture capitalist perspective.
Sure, of course. Yeah. Hi, good afternoon. My name is Vishesh Rajaram. I represent a fund called Special Invest. We're a pre-product investor. We invest in science and tech. We've been doing this now for almost the last 8 years in about 30 plus companies in very exciting early partners with Shashwat at Mindgrove, among other exciting things we've done. Thank you.
Thanks. And then let me get to my left, Madhu. If you can share your opening remarks, that would be great.
Yeah, some of you might know about Incore. I and Professor Kamakoti basically started the Shakti program. Incore is a kind of a spin-off from that and is India's first and as of now only private sector processor company. So we are focused significantly on the embedded segment, both the very low end and going a little way up that. But we also have a new tool called SoC generator. So what we are trying to do is not just get people build SoCs out of our products, but also trying to figure out how to solve the problem of getting Indian startups, especially get to product faster. Because unless the product life cycle is reduced, just supplying a core is not sufficient. So that is where the focus of Incore is.
Thank you. Thanks, Madhu. Okay, last but not the least, Shashwat, knowingly I kept you because you guys did magic last year, seeing the first silicon. So if you can, briefly share your opening remarks.
Yeah, hi guys. So I'm Shashwat from Mindgrove. So Preet, before I talk about silicon, there's something very interesting over here. We have 3 startups and you, who decidedly anything but. But then we have 2 IP companies and 2 product companies. And then we have Vishesh who straddles all of this, right? So it's an interesting panel we have here today. The journey of getting silicon out as a new team, my team's average age is, when we got the silicon out, was about 24, maybe 26 now. And that is because I'm there. If I go out, it'll still be 24. Getting a chip is not all that difficult. It's a lot of hard work, I know, but I mean, it's not difficult in the sense of it doesn't require special knowledge that nobody else has. Getting the right chip to solve a market problem, now that is where the magic actually lies. And I still don't know whether that particular magic has worked from the way that Mindgrove has done it. We are going into the market this year, so we will see what happens.
Thank you. So, sis, good luck to you. And it's like, I'm a bad guy when it comes to kitchen. And the other day, my kids asked me, okay, can you, cook a dish for us? I said, well, I can do that, but you need to promise you will end up eating it, okay? So I agree with your comment. Generating a silicon is, you have a ventureless friend, you can go and give a GDS and get something out. But whether it kicks on the day one, whether it powers on, you clock the right frequency, really matters. So good luck to you. So let's get started since you're the, one who ended up. What do you think? So, role of, from the non-technical perspective. One is certainly, we keep on getting this question from many of the folks. So, well, I'm in, bachelor's or master's. How do I, get to a job? What skills I should have to go and, join NXP or Mindgroup, any company? But what kind of skills or what kind of things you look from the non-technical perspective when you have to, hire someone, say, for your own organization?
So we do a lot of fresher hiring. We do a lot of hiring of older folks also. But when it comes to a fresher, right, the first thing that I always look for, I do not look for specific VLSI skills because A, that's non-existent right now. I don't consider it VLSI skill unless you've actually been through a tape out. And B, that really doesn't decide whether you will be able to tape out or not in the future. What we really look for is, one is enthusiasm, and the other is basic electronic skills. What is a transistor? What is a CMOS? What does it mean to have a chip in this particular, you have a problem between 2 transistors. What does it mean? How does it impact? We look for the ability to think beyond just the electronics. Think about how the user is going to use it. When I put these 2 things together and I get only this much out of it, I have a huge, very high fan out, for example. I have too many things connected out. That means that I will have drop in the voltage, which means that the voltage supply has to be particular type. And then, so are you able to follow that kind of a logical thinking back to how the user is going to interact with it? If I write an instruction, if I write a new instruction, being RISC-V, one of the promises is that you can add custom instructions. But if I add a custom instruction, how is the user going to interact with that custom instruction? Do I have to write a assembler? Who's going to maintain the assembler? Who's going to write the compiler? Who's going to verify that the damn thing works second, third time out? So are you able to engage with these kind of questions? That is important for me. And as far as experienced folks is concerned, we hire them and we do not allow them to lead teams. I'd rather, so the market is in such a way that typically the people who leave a large company and come to a startup are people who don't want to go up the management chain. So dragging them into a small startup and saying manage doesn't work. So what we try to do is we try to give them individual responsibilities, maybe training responsibilities, those kind of things, and bring up younger folks as the people who are leading teams.
That's just really important because if you put them in the same sport, the reason why they came and joined you, certainly the same thing is going to happen. And I like your stuff. It's like you need to see, putting your feet in the other shoe and see how it feels. Is it really hard or is it really comfortable? It gives you that bump to walk. That's what one need to visualize. So now let me get to my extreme left to Ruben. Ruben, my question to you is that. We keep getting this question, okay, people know how to run a tool or people know how to, set up a timing or a partition. But when it comes to, architecture perspective, when it comes to visualize the whole big chip, and that's where at times I see that, it becomes challenging, it becomes difficult to have that skilled person working for a startup, first of all, really making them join a startup and then not as Shasha said that not letting them go. So how you see, do you really see being in Bay Area, which is competitive, costly place to be in, and getting such kind of talent? So what is your perspective? Do you really see such kind of architecture kind of people getting into a startup and then retaining them for long?
So yeah, so there is.
It's not still. Press and then right.
Does it work now? Does it work now? Okay.
Yeah.
So there are, I would say, two types of people. People who are happy in like larger companies working there, and but larger companies can be suffocating. The teams are very big. Just to pick a few names, or maybe not. Some of these hyperscalers have like 200-300 person CPU teams. And so if as an architect you go and join there, getting like any interesting work there is challenging. So you are constantly trying to figure out what your role is, what you can do, and that gets really frustrating after a few years. So there is a lot of interest in joining startups among senior architects in the US, I would say. And we have been able to hire and retain a lot of senior folks in Akeana. The other aspect is, you always need more folks with the broader vertical perspective where, they can solve problems at the architecture level, at the design level, at the software level, and cut across and debug performance issues, debug functional issues, do design, do verification. So that skill set is hard to find all over the world. We do look for that skill anywhere we can find it. In India, I would say, the talent does exist quite a lot. It could be bigger. I think the tech population of India, the tech-savvy population of India is very big. And given that, I think there is opportunity for much more leaders to emerge here. So, as somebody else said, I think failure is very important. So, trying things, failing, and being able to try again is important. So that does require opportunities to be presented, so that does require more funding. So, but things are moving in the right direction, and I do expect more and more talent emerge here.
Thanks, Robin. And I like your point. Failure itself is learning, and it's okay to fail. Certainly, when you're sending some GDS to fab, we don't want to fail. But at the same time, fail, learn, and make sure you don't repeat it. I know a few of the organizations who celebrate their failures, and the reason is they just want to make sure that everyone in the organization knows what went wrong, so that everyone learns it and nothing gets repeated in another department or other wing or in another tape out. So I think that's just very important. I'll give you a personal example that once I was in Sri Pilani and my scientist gave me a research task to work on, and I was not able to achieve that gain for that amplifier. And I was really worried for my next interaction with him that what would happen, because I'm not able to achieve he asked me to achieve some gain using for a variable gain amplifier. And when I had a word with him and I was like, okay, he said, okay, Preet, explain me what happens. And I said, sir, I tried a lot, but using this particular architecture, it's not possible to hit this kind of gain which you're looking for. And he said, wonderful. And I said, oh, that gives me a sigh of relief. And he said, okay, so you have at least now walked to the path and proven, okay, this architecture, this is the limitation, we can't go beyond this particular gain. So although I failed to achieve the gain, but that was a learning. And he said, okay, please document it, present it to the team so that no one else repeat the same thing and, then hitting the wall and then say, oh, well, we need to rework or restart. So I think failure itself is a learning, provided we take it positively, and certainly we learn out of it. We make sure we don't repeat it ever. Okay, so let me now move again to my left to Madhu. Madhu, we talked about, what kind of attributes are required from the non-technical perspective by Shashwat, and then Robin mentioning about, what kind of qualities, typical architect level of chip level folks will look for. I want you to talk about, because we have a lot of, budding engineers and probably entrepreneurs for tomorrow. I want you to talk about, other than the talent and other than the money, which can come from the extreme right, what do you think is required to get to a startup, especially when it comes to semicon, because in software and other domains, it's relatively, I feel, easy to be, to get to a startup, but to be a semicon startup, other than the money, and let's assume talent is given, what all are the other core things which are required to form a startup?
You're asking from the employee's perspective, or what the company?
In general, you need tooling or you need skilling.
See, ultimately a semicon startup, whether it's an IP or a product company, is all about products. IP is also a product, correct? So what is lacking in India is product marketing. One of the reasons product companies don't come in India, most of the MNCs that came here came from the engineering side. There are very few senior folks in India who are to take a product gamble, saying for this segment, this market, right? So typically the product decision gets done elsewhere. And the team that's here tends to be the sales team. So even friends I know who want to do it say that, look, I'm just given a quota, I'm given these parts, go sell. Only now I'm starting to see where MNCs are saying, okay, ideation will come from India for appropriate, right? So the problem that all product companies face is that it's very tough to get a VP of marketing. It's very tough to get people who will take a gamble saying this is the segment that is there. They don't know how to read the market, price points, product strategies, distribution channels. That whole thing is missing. The number is actually higher, 35% or so design gets done in India. More than that, if you see the latest announcements from Intel and other people, the R&D heads and the architecture positions are being hired in India. Intel actually had a job opening and I saw where the architect is in India and the product marketing guy is in the US. It's flipped, right? So there's no shortage of talent in India. But when it comes to products, which product sells? For example, he's doing an IP camera, correct? Now, if you take an IP camera, the Chinese sell it at between $1.50 to $2.50. No name and all that, right? You have very low-end camera. Now, do you go for H.264 or 265? 265 licensing cost is higher. But the problem also is that the software protocols, WRTP, I think, don't support 265. A lot of people want 264. I did a 265 codec back in 2002, like as an IP, sold it very successful. It's still hanging on, correct? Then there are patent royalties. So where is the patent litigation happening? Are you safe at 264? Or do you go to AV9 and stuff? So even to design an IP camera chip, there are like about 40 different considerations that needs to happen. Do you put AI/ML acceleration? So I need people who are curious. So it's an odd combination, right? I need people with solid basic strengths. It doesn't matter, even if you come from metallurgy, you need to be good in metallurgy, right? The problem is we don't churn out engineers with good basics. We churn out engineers with a lot of knowledge, but we don't teach them systems engineering, how to build systems, how to craft systems, right? So we suffer when it takes taking a product to market. Mm-hmm. We suffer when it takes to build a complex system.
That's right, and that's what exactly our minister yesterday was, the past minister was talking about, that we first create a product and then we say, okay, where I can sell it off, okay, do you want to buy? But I think the other way around, which, as you said, that let's identify a problem and then see, what kind of market we can, solve using that problem, or using the same product, how we can, put 3 different solutions, or we can put 3 different applications to,
It's not easy. You can't wake up one day and decide to do it.
Certainly.
I spend 15 minutes talking to at least one distributor every day, and I've been doing that for the past 30 years. Mm-hmm. So I know exactly what NXP's sales figures are. I know where you're selling. I know where you're not selling. I know who's doing smart cards. I know who's selling, right? That is, you need to build a network of people so that you have market intelligence. Market intelligence doesn't come in a day.
Yeah, certainly you can't just buy it out. You need to, put time and again efforts to get to that market intelligence. That's great. Thanks Madhu. So let me again get to Vishesh. So Vishesh, who's the, what is the first thing you look into? To me, typically as an Indian, even if I want to spend $1, I'll think through twice whether should I do it or not, or is it really worth of buying that piece of cake or not. So what is the first thing you look for when it comes to investing in a startup, typically for a Semcom perspective? Press it, yeah. No,
so to give you a little more context, we come in very early, right? We're a pre-product. So many times there's not a lot of evidence out there that this is something that's already working. And therefore our investment decision is largely anchored around the team and their ability to envision something 5-7 years from now that will be relevant. Not necessarily in the next 1 or 2 years, but carry out a vision with 5-7 years to build something very large, very meaningful, that competitively stands out. So our focus then ends up being on the team and a competitive vision, a vision that has a moat in how they want to implement it. Of course, dime a dozen things can go wrong between day 1 and day 1200, or day 1 and year 5. But a lot of our confidence comes from just the team's experience, what they've learned historically, and what insights they have that allow them to come and build something uniquely. Sometimes it's a timing insight, sometimes it's a customer insight, sometimes it's coming together a platform insight, right? You're building onto something that's become more relevant now. That wasn't relevant before, that didn't exist before, or a market didn't exist before, it showed up now. So we look for those insights that the founders carry to sort of build upon and go build a meaningful company.
Thanks for the insight tip. That would probably help the future entrepreneurs sitting in the room. So it's like as you said, the right timing. Something which was not relevant yesterday might be making sense today, because we saw that disruption by one of our neighboring country. That AI company who really changed the world overnight. You slept thinking something, and you woke up, the world is quite a different place. Okay, so certainly go ahead. Good luck.
Shashwat competes with NXP. I compete with him. He's like 1 million times larger than him.
Of course.
I got funded for 3 million, he got funded 100 million. So if you have to invest in him or me, when he's the competitor for Shashwat and he's the competitor for me, why would you take a bet on an Indian company when biggies
so
like
we'll
this
keep
exist?
the Indian company part for a second. I think this question applies anywhere, right? Why would you bet on the David when there's a Goliath? It's always the case. You got to look for a catapult, right? You got to look whether the David has a catapult. Otherwise, this is not a game worth playing.
Yeah.
So I think the David here has a catapult because he's operating. At the time when we invested a few dollars in the company, their ability to leverage that and tape out a chip was quite high when compared to anybody else we saw. And sometimes it's about being in business and being relevant there, right? So if you have a chip that you've productized, like you said, and you found a way to get to market, then it doesn't matter so much whether you have an 800-pound gorilla in the room or not. What it matters if you can keep chipping away the market and then build a meaningful business. Thankfully, we're not here to make $1 billion overnight, right? We understand this is a long-haul game. We understand it's about being relevant in the market and being meaningful. So we're looking for the catapult at the David, if that helps. Yeah.
I would say we are David too. The Goliath is on.
There's always a Goliath for every David.
No, that's true.
And Arm would say that the Goliath is Intel. So, well, not anymore, but Goliath did fall.
Yeah, so I don't want to name any company. I want to stay neutral here on the stage, at least on the public forum. But let me ask this one question to Shashwat, you, and then I'll open it for audience for any question and answers. Since you have a chip taped out, okay, and doing a chip, designing a chip, you need a internet connection, a laptop, a idiot tool, and a smart guy to do it.
Yeah.
But when it comes to actual physical real world silicon, how you see that whole Indian ecosystem in terms of getting the wafer level testing done, and then getting whole of the packaging part of it indigenously done, and then after packaged part, testing for a startup, okay? I'm not talking about, as I said, the big techs who might have a good lab established like for ourselves in India. So how you see, the challenge part of it post-silicon when the real thing is in your hands?
That's actually the biggest challenge I'm dealing with today. I'm dealing with it on a daily basis. So the first thing is the expertise. So it's easy. I would say, I don't know if you've seen, one of my favorite books is The Mythical Man Month, written in the 1960s and still very, very, very relevant. Building something is easy. He has a quadrant. Building a simple thing, building a system, and system of systems, and then the final thing is actually building a product. So, for all the complexity of building a processor, it's actually the easy part. And it is only, I feel that there is definitely a paucity of experience within the country for doing things like package, for doing things where you have board, package, wafer, all sitting together. And can you actually figure out what's going on in between? Is your signal dying in between in some line? All of that kind of analysis is hard. And I can teach that analysis. Now I need somebody who can think through that. It's not about just teaching the analysis. It's about thinking through, is that even the right analysis to do over here? But on the other hand, there are 1.4 billion people here. There is always an expert. We just have to find that person. And the one thing that we can leverage is the fact that the EMS ecosystem has grown. And there are, so just a couple of weeks ago, I was talking to somebody who said, we were saying that we needed something to do some power measurements on the chip. And he said, come, I have a lab. So there is a lab somewhere. It just so happens that we don't know who has what. And we got a lot of boards assembled inside IIT. It was very fast. And that helped us actually reduce the time. Had we gone to a Chinese vendor, for example, or a European vendor for the same thing, it would have taken us 3 weeks. They would have been cheaper, but it would have taken us 3 weeks. I needed that validation now so that I could go tell my customer, look, I got it validated. So building up that, again, like Madhu says, it's not just about having the ability, it's having the intelligence that the ability exists and who to go to, who has what. And who can I partner with? That is something that we're still building.
So that network really helps. That awareness about the network really helps. And at times it's easy to buy a pizza over the shelf rather than using your own hands and baking it out, because its time is money. So and that is something not everyone is able to figure out. You need to take a right decision whether it makes sense to have your own every time, or is it good to use someone else on and go forward. Okay, so in the interest of time, I'm gonna pause here and we'll make this forum open. We have experts sitting on the stage today. Any questions from the audience side to any of the panel members? I see your hand raised already. Can I ask one of the volunteers to get a mic to this gentleman? Do we have any mic, or I can pass on this? Can I get a volunteer who can get this mic to the... Thanks, Lavanya. She's the de facto volunteer for everyone.
Good afternoon, sir. My question is, most of the electronic companies still choose Chinese manufacturers to get their products manufactured. I'm asking you, as an Indian semiconductor company, how can you change that mindset of those companies to choose an Indian company to get their products manufactured, and how can you bring that paradigm shift? I know it's a slow process, it's going to take time.
Look, I've been tracking the EMS industry for about 35 years now, and in fact, I helped bring Sanmina to this country. The Chinese have an amazing ecosystem that is second to none. It's just not the assembly lines and so on, okay? All the high-end assembly happens in Chennai too. Chennai is the EMS capital of the country. But it's all just like Tirupur has an ecosystem, the Chinese have an ecosystem. So if you want to do a camera module, you'll find 10 people who can do a lens. You'll find 10 labs which can align the lens properly. You'll find 20 other companies which can do that wafer scale packaging that sensors need. The Chinese have built that ecosystem over decades. And far more importantly, tooling. All of electronic assembly involves significant tooling. There's a lot of mechanical stuff involved. And the Chinese are second to none. The reason Apple goes to China is because of the ecosystem and the supply chain. Tim Cook is one of the world's leading experts on supply chain. He's not a product guy, he's a supply chain guy. He can get you the best supply chain that Apple wants, and that is why Apple succeeds, significantly because of the supply chain. And that currently exists only in China, to some degree in Taiwan and Korea. So when we started shifting the supply chain to here, the Chinese simply stopped sending their engineers over and the tooling companies. So we literally had to kind of make amends with China, so that otherwise you can't shift production. We can shift production from China to India only with a little bit of Chinese concurrence. It'll take some time. So it is that ecosystem that exists in China. It'll take us about 15 years to catch up. There's no shortcut to it. They've done the hard work. They've done the hard work for 30 years. It'll come here. That's not a problem. It'll take time.
Yes, sir, because in future, if you want to become economic superpower, we need to gain that market share in semiconductor industry as a country.
If you take fabs, we have one fab, the Tata fab, that is coming. Last year, the Chinese commissioned 25 fabs. Currently, they control 25 to 33% of the 22 nanometer and older nodes. That is projected to go to 40% in 2028-30. My gut feel is by 2035, they'll control between 60 to 70% of older node fabs. 70% of all common semiconductors will be manufactured out of China potentially. Let's not keep saying superpower. We need to get at least 5 fabs up and running. There is enough demand locally. I'm not worried about the Chinese. We can match the China and all that, right? But to get to where China is, that is step number 2. It's like climbing Everest, right? We need to do the base camp first, which is what we are building. Attacking the summit can come 5 years down the line.
Thank you, sir.
If I may, just while we're looking for the other one, just to add one point to what Madhu just said, a lot of people are actually happy to talk to an Indian company if you're building something, one part of this bigger ecosystem. And rather than try to say that I will do everything in India this minute, it makes sense to say, what is your problem? What is your problem with this Chinese vendor? Why are you even talking to me? And understand. And you can't just, Rajivji said yesterday, you can't be a solution looking for a problem. So you have to listen to the problems, and they are coming to you because you are the expert in some domain. In our case, we are semiconductor experts. So when you're coming to somebody and saying, when they come and ask for a solution and they explain their problem, it's important that we don't take their solution, we ideate on the solution and you propose something. You have to build these relationships. And that is, the relationships and the network will lead to the kind of ecosystem that Madhu is talking about.
Certainly, certainly. Yeah.
Thank you,
So
sir.
it is, the fastest who can deliver and the cheapest who can deliver. You can get the same kind of product, say, in country A and country B, but there's a cost distance of, say, 20x delta on a single part, then see the whole system cost. So that would come. And as he said, the base camp is done, will be at summit, but it's going to take its own time. What they invested 2 decades back, they are reaping the fruits now. And what we are investing now, certainly, your generation would reap those benefits. Any next questions here?
My name is Achyutan. I would like to know, my question is to Madhu. The thing is, how do we get a lot of students who are just not even, ask us telling, so the students just come out without theoretical knowledge and practical knowledge. Most of them want to get into IT type of companies. So how do you think that kind of thing is going to help us in translating our future? What is your opinion?
No, you want to know how to skill yourself so that you can enter the industry.
See, nowadays, you can. I was told there are companies who make. Sorry, I suffered a stroke, so that way while talking I have some problem. So thing is, we get a lot of out of some 100, maybe 1%, 2% are good in theory and practice. But most of the students coming out of the colleges are not the good quality. So how do you tackle that?
Look, I was giving a talk at a college, and I started the talk by telling the students, like, this side is the trustee, that side is the principal. It is the job of these two gentlemen to ensure that you don't get an education. I will tell you how to get an education in spite of the best efforts. I've never called that again, of course, right? Yeah. I've told enough parents that they should ask for a refund from engineering colleges. No. The problem is we never get taught engineering. I was lucky. I'm a third generation engineer. I'm the 15th.
We are all lucky. We are all lucky people.
No, but we are not taught. Engineering is about curiosity. It's about a thirst to learn. It's not like about 20 different subjects, correct? So if you take an electronics engineer today, he cannot design a simple amplifier. He can't design a simple SMPS power supply. And he can't do a simple precision amplifier for an oscilloscope. If I were to change curriculum, I will just take 4 products for an electronics engineer and put 1 project per year and then build the theory around that. Yeah. See, human beings, you need to understand human nature. Human beings are curious creatures. We are storytellers. Mahabharata, Ramayana, these are all stories, right? So you need to give a product to a kid and the kid plays with it and then you construct the theory around that, right? You lead with practice, not with theory. Look, a 2-year-old plays with a toy. Do you teach him the theory of what the toy is? No, it's inherent curiosity. A cat, a puppy, human being, everybody plays. We are creatures who love to play. You need to take human nature into account when you create engineering curriculum, and we miserably fail to do so.
So just in answer to your... The majority of the engineers in Akeana are of Indian origin. They all got their degrees from Indian schools, and they are among the best engineers I worked with. And it's not just Akeana, right? If you look at the Bay Area, a significant fraction of engineers in all the big companies, we are talking the Googles, the NVIDIAs of the world, are engineers of Indian origin who went to Indian schools through the same curriculum. So they are essentially holding the tech industry up across the world. So whatever we are doing, I think it's not too bad. I mean, I feel like, you take a student who has just finished his bachelor's and you ask him some basic questions, maybe they struggle. But after 10 years, they are contributing and they are pretty good engineers. So I don't think it's all bad.
Question here. Guys, before we just move to that quickly, whosoever is on the stage, did we ever thought of FinFET when we did our bachelor's or master's? But it was not in curriculum, okay? When I did my bachelor's, VHDL was not part of my curriculum. I did my final year project in VHDL because I did an internship at SCL Mohali, luckily. And I bought up a book and did a project. Even the person who was, correcting my project, who was, invigilating that project, This guy was not having idea about the VHDL. So it is, curiosity, that thirst, that hunger to learn. And I feel, with this couple of decades of experience, it is, you need to learn, unlearn, and then relearn. Okay. So if you master this skill, then you can survive, because whatsoever you are learning today and with this fast changing world might be outdated after a week or after a month or after a year. But if you have that curiosity, as Madhu said rightly, then certainly you'll be survive. And to all my engineering friends here who are in, say, second, third or fourth year of engineering, you did a mistake 3 years back, signing up for an engineering course. Now for the rest of your life, you need to learn, unlearn and relearn. And if you keep on repeating that, you will be never outdated. Yep.
See, we are talking semiconductors here. What does a chip like a high-end Qualcomm chip do? You're literally taking fundamental particles, electrons, right? Which don't really exist in nature if you look at quantum mechanics. So you're essentially taking virtual particles in the trillions of numbers, and you're creating this entire virtual universe. I cannot think of anything more magical. So if you hold a chip in your hand, and if you don't get a buzz, correct? And you feel grateful that you live in an era where these things happen, you're not fit to be an engineer. Every kid has that curiosity, and we somehow, with our education, all of that, remove that curiosity from the kid. So the job of every CEO here is to inject that curiosity back into that engineer, if that engineer has to be successful.
Okay, so just for the sake of the audience, let's assume we are talking to good engineers who have very high curiosity. The question I want to ask is, when they apply to you, Indian companies in general, and you mentioned earlier that, Shashwat, you mentioned that hopefully they know how to tape out, but obviously there aren't many companies who have done that. And I think maybe somebody else mentioned that maybe they should come with product marketing knowledge. It feels like a little bit of a chicken and egg, right? The students who have graduated, who have done well, they have not had that opportunity to learn this, but maybe you need that already. So what can they do in the next 6 months to 1 year to be useful to you very quickly? Does that question make sense?
Yeah, let me take a short thing in this. 3 days ago, my answer would have been different. It would have been get into Tiny Tape Out or eFabulous or something. But unfortunately, eFabulous has folded. So, but still, there should be some replacement coming up, I hope. I really hope. I would encourage anybody in the policy side who's paying any attention, please let us do something on that front. But really, just do electronic projects. You don't need to tape out per se. Just do electronic projects. Build an amplifier. The favorite project when we were in college was to build a guitar amplifier. Do it. It'll give you at least that idea of how to build something which you actually use. When I was in the 12th, I built a game. And that is where everything for me actually started clicking, and I decided I want to do engineering. So just do those kind of things. Those are enough. If you're able to engage with the problem and you're able to play with it, that's all you need.
If I can. I am Subramanian MK. MKS. A question from somebody more experienced. This question once again addressed to Mr. Madhu. Mr. Madhu, you mentioned about one of the challenges being how to identify the right product. Okay, so the technical part with all its complexities is relatively easy. What should be the feature list, so on and so forth, right? So what should be the product specification, engineering specification, system specification, so on and so forth. So can you please list top 3 things we have to do to get this right? How do you solve this problem?
The answer is simple. It actually is empathy. See, we all are egocentric. We create a product, we think it's a great product. Very few people listen to customers. You don't understand his pain point. You don't understand his business. So we go in there with a brochure saying, this is great, that is great, that is great. By the time he has lost interest. So you want to know whether you're a good producting guy or not? Go ask your wife if you listen to her. If she says that you're a good listener, yeah, you got the good makings of a good product guy. Because if you don't have empathy, if you're not willing to listen to customers, if you don't want to understand what their pain points are, you will never create a great product. Yes, you can posit a product, right? Steve Jobs used to say, look, yeah, the customer, they don't know what they want. That is fine for the top 10%. But by and large, your product has to satisfy a need. And the customer may not be aware of what product he needs, but you need to understand the customer. That can happen only if you talk to people. So that is everything from price point. It could even be supply chain, right? For example, some of the parts that he does, you can be successful because you're giving MOQ. Like if I want to get a Qualcomm part, I can order only in 100,000 pieces, which means a certain segment of the market which is going to order in 1,000, 10,000, 20,000 pieces cannot get from Qualcomm, right? So if your product has got an MOQ of 10 pieces or even one piece that you can go to Ritchie Street and order, you may be successful. So there are various reasons why a product can be successful, right? It's got to be the right fit for that right market at price point, at supply or packaging. There's like a variety of factors. You will not discover those factors unless you keep talking to people.
Thank you.
Okay, so in the interest of time, we'll call it off.
Maybe one question?
Okay, there's one last question.
All right. So this is Karthik, IIT Madras, and also Gindi Alumni Angels. So this question I will ask for Vishesh. As the investor there is a bunch of techies. Okay, but please, everybody I would love for everybody to chime in. RISC-V is a baby in comparison to Intel's and ARM's instruction set. And among babies, we have a few startups which are again babies in the economic ecosystem. If India needs to compete, and if RISC-V should have a hope of competing against these behemoths, we have to learn to collaborate among ourselves first. So what can Speciale or from the investment side or from technology side, how can startups in this space collaborate? And any comments that any of the, first to Vishesh, but everyone. How can we collaborate?
I think I'll leave enough space for the others to answer because quite honestly, sitting in the seat of an investor, it would not be fair for me to dictate how startups should collaborate. It's for them to decide. But I think the real nuance is oftentimes they don't collaborate enough simply because each one's already working on this very long journey which has enough pitfalls in what they're doing, right? And oftentimes if you're a startup, you want to be working with someone who's got certain parts more stably figured out than the other. So that's one of the reasons why we haven't seen that enough, but maybe I'll let Shashwat also take a shot at it.
Yeah, so there is a certain truth that, when you collaborate as startups, and if someone is, each one is working on a very deep vertical problem and one is delayed, then everybody gets delayed in the ecosystem. So what you will often see is startups trying to collaborate with big whales. And that's fine. I don't think that there is anything wrong in that. That's why that's why you see even here in the research park, you see a lot of like Boeing or Saint-Gobain, a lot of other people creating collaborative environments, startup challenges and things like that. So that's, I think, fine. But if you want to talk about startups collaborating, I think the most important thing that we all need to do is to stick together, and there is a certain startup push in terms of common go-to-market or collaborating in terms of intelligence. Those kind of things are probably more important than trying to collaborate on technology or trying to build our product as 5 startups together. I find that on the other hand, there are some cases where I can only afford startup rates, so I might go to a startup to get something done. That is also true. So I don't know if there is a one-size-fits-all answer to the question that you asked.
Okay, thank you.
Okay,
so with this, we'll close this panel. Thank you so much again, being almost houseful here, and can we have a quick round of applause to all the gentlemen here on the stage? Okay, so I think as a quick closing summary, you know, I see most of the young faces in the audience today. I think if you get the right attitude and right aptitude, I think you're done. You know, rest all is, whatever stream it is, whatever subject it is, you know, things would fall in place for you. And as our PMS said, you know, yahi waqt hai, sahi waqt hai, and I see it's the right it's the right time for we as a country to really leap forward. And, you know, there was a question, to be example for, you know, next couple of decades for rest of the world. So with this, thank you so much, and I'll over to the MC for the next in line plan for the day. Thank you.
Thank you, panelists and moderator. Our next talk will be by Lavanya Jagadishwaran, CEO, founder, Voma Systems. She'll be talking on Uptick Pro, your DevSecOps partner. Lavanya is the founder and CEO of Voma Systems. She has over 14 years of experience across various processor teams and has been part of IBM, ARM processor verification teams and led the RISC-V processor verification efforts at Rambus Chip and Shakti Group at IIT Madras. She is also a RISC-V ambassador for India. Lavanya has done her MS from IIT Madras with Professor Kamakoti as her supervisor. Over to Lavanya. After this talk, we'll take a break for lunch and come back for the next round of talks in the afternoon. So we'll be resuming our afternoon session at 1:15.
Thanks, Nitya. At the outset, I just want to tell this, the slides here are not intentionally made after this panel, but we'll see how it goes, right? I'm Lavanya. I hope you have been seeing me from yesterday morning. I'm the CEO of Voma Systems. Bit of introduction of Voma. We are a startup, three-year-old startup incubated at IIT Madras Pravartak. And we are a company that came out of the same Shakti group at the CSE department. Our vision is to bring in self-reliance in the RISC-V ecosystem, and through a product that we call it as an ecosystem as a service platform. How and what it does, we will be going over in this talk. But more importantly, we handle one pain point that some of the design companies who have talked till now face. So that's why we call ourselves ecosystem partner for these companies. So this is a slide that we borrowed from the RISC-V summit that happened in the US, where we see the RISC-V collaboration growing. There are a great number of memberships that is increasing, the growing number of companies, academics, and individuals who are becoming RISC-V members. Along with that, there is also a collaboration in different verticals, be it only core ISA specification ratification or software bring up and things. So the hype is that RISC-V is everywhere. Its openness and the collaborative nature helps a lot of businesses make it as a solution for their product roadmap. But they are in a race, as you have seen the pain points that has been discussed till now. They are in a race to bring in their secret sauce, that is the customization that they want to bring in to stay relevant in the market and bring in the competitive differentiation. They are in a race to maintain the quality because their business outcome and the reputation of that is dependent on that. They are in a race to have the software bring up so solid that the users of their products are seamlessly integrated into the ecosystem. And the race is against time. So this is the challenge that is there and the opportunity. So can one company achieve it, right? So that is the question. So there are several startups that are coming up. There are big semiconductor companies who are bringing up their own RISC-V groups within their things. So can one company achieve it? Of course, we have seen it achieve. It has happened over the past history in the semiconductor history. But the question is, can one company achieve it with the kind of time or the kind of race that they are trying to go over? So that is the question that is getting asked, and a lot of answers are converging towards building a partner ecosystem, right? So the main challenges that we have seen in having such a startup or a RISC-V group building their own solutions in RISC-V is that there are quality issues that are coming up, which has been represented in the yearly survey from Wilson Research Group, and the shorter delivery time that we have seen for the race to bring the competitive differentiation. Along with that, being a non-standard software stack, which has it has its own challenges to mature and be of use to their customers. So this is the challenges that they face, and the solutions have been till now or historically to build in-house ecosystems for delivery of their product to market. But the one thing that we forget is that the RISC-V itself is an open standard ISA with high amount of collaboration that we have seen. When an ISA is itself open and has collaborative nature, it makes us think, why are we not making each of the rest of the steps to make that specification, to go to market, to have such partnerships, meaningful partnerships that we have discussed in the panel or previously in the talks too. So the question is, why are we not bringing that collaborative nature from the spec to market flow also? So in that regard, what we are trying to achieve is provide a partnership role from Voma Systems as a startup for a specific need in the development process. It's not that we are going to solve all the problems of a startup that is going to go to market with a RISC-V product, but we will solve one. We have taken one, which our team is expertise in, and we are building that vision to help them solve their product market faster. So what we have is an ecosystem of pre-silicon verification and an enhanced debug for FPGA acceleration. Basically, anything that comes after design. A company that designs their chip, after that, before going to a physical design flow, they will have an optimum number of steps to make sure that the quality is maintained properly. And the performance improvements or the performance target that they need are met. So in that regard, we provide the ecosystem solution for having a simulation flow. We are going to cover that. So verification IPs as part of Voma that can be made as a plug and play for an open ISA standard. So those can be used readily. And along with that, there will be an ecosystem where you can deploy those in a Python-based environment. This, along with an FPGA accelerated environment, which also has the debug capabilities, will also be one of our solutions to the current challenges. Along with that, we also have an environment where the software bring up is taken care from day one, and the solutions for that is also available in the cloud platform. A bit more deep dive into the solution of a simulation-based verification. We can take it as a use case for Shakti C-class. This is the benefit for the student community where how we attack a certain problem, let's say a design, which has to be verified and has to be taped out. We take that design and provide the test generators, the test templates already available if you are following a standard RISC-V ISA specification. And we also provide a scalable reference model which can check how your design performs when compared to an instruction set simulator. Once that comparison is done, then you are a bit more confident that your design has gone through the ISA level checks. There is always the challenges with bringing up the verification or maintaining the quality for customization as well as micro-architectural details of this whole design. So those are also some things that can be worked out, but the one that can be repeatable and can be used across different companies is the common ISA solutions. So once that is done, we then have the ops framework, where I think there is a lot of fun that is happening in the software world, and we wanted to bring it into the hardware development ecosystem also, where we build and generate the tests parallelly. Along with that, the amount of verification space that is needed for simulating a design and making it reach a coverage closure, we have a scalable cloud infrastructure that builds, generates, and simulates these tests on the design parallelly to achieve the quality. And this is one thread of the solution that we feel can be utilized and made use of in a collaborative manner for other design companies to use. So this is the overall picture of our offerings, where we provide the pre-silicon verification IPs and enhanced debug for FPGA acceleration. Along with that, we have a standardized software ecosystem for companies to adopt. How will this help in for a student community or for engineers who are trying to learn something in RISC-V or adopt such a standard? So that is where we give an IDE in the cloud, where all these infrastructure and tools required for skill development, as well as to get a real feel of how an industry works in these domains, are made available to the general public. And we call it as Uptick Pro, Uptick the productivity of any design company, or also you can call yourself in the skill development. Thank you. I will announce that we have, we will break for lunch now. Oh, yeah. Any questions?
Lavanya?
Yeah.
I just want to know whether you consider taking the average requirement of the markets before taking up a chip design. For example, there is an average requirement of this, or you just consider.
We discuss with the design companies to understand their requirements. Is that the question?
No. Suppose you take up a design, chip design.
Right.
So then, how do you assess? These are the requirement of the country, or these are the requirement of the basic.
Through our general customer interactions, we understand if we are concentrating on a very specific market segment who are developing RISC-V solutions, RISC-V based solutions. So we have customer interactions with them to understand their requirements and their pain points. Through that only, this value system through the startup has come up.
Okay.
Through our direct customer interactions, basically talking to people of the caliber of MindGrow or NXP, all established companies and things like that.
No, I don't think they will be that much experienced. But are you taking the average requirement of the country, or?
Not the country at this moment. We are still a small startup.
There are railways, there are so many organizations.
Yes.
Where there is a specific demand.
Yes.
Are you designing the chip to cater to that?
We are not designing any chip. We are not a semiconductor IP company or an SoC company. We are a verification and validation partner to those companies.
Okay. Okay, fine.
Yeah.
Thank you.
Thank you. Just a quick announcement for lunch. We'll be back by 1:20, and the next sessions will start post-lunch. Yeah, question.
Ma'am, my name is Lakshmi Narayan. I'm a second-year student, electronics student. And my question is, if I have an idea, should I directly approach the incubation, startup, and tell my idea and directly start the startup, or should I work any other startup and gain more knowledge?
It's up to you personally. There is generally a thing that you can't do anything alone. Even startup companies are advocating collaboration. So an individual trying to solve world problem will not work, but you have to build the expertise yourself, but you also, it has to go together.
Okay. And after starting a startup also, I'll have some, like I'll face some problems. Or should I gain more knowledge to have a startup?
Even if you have the startup, there will be problems.
Okay.
You have to make your startup a success. You have to gain customers. You have to, there are up team number of, you don't call it problems, you call it challenges. And you try to enable yourself to face those and handle those over the experience. In that regard, the partner, an incubator or an ecosystem where you can interact with other startups or building a network around your problem domain helps.
Okay. Thank you.
Thank you. If that is the thing, thanks a lot. Bye.
Good afternoon, everybody. We'll now do the afternoon sessions. Our first talk is on SOC Gen, Automating RISC-V Solutions by Arjun Menon, co-founder and chief engineer, Incore Semiconductors. Arjun is the co-founder and chief engineer of Incore. He was one of the key architects of the Shakti processor program at IIT Madras. He was instrumental in designing India's first indigenously developed RISC-V processor. While working at IIT Madras, he was the lead architect of a 64-bit out-of-order processor based on a custom ISA designed for one of India's strategic agencies. He was also the tech lead of an SoC for ISRO, which was booted successfully recently at IIT Madras. He received a BTech in ECE from Amrita School of Engineering and an MS in Computer Science and Engineering from IIT Madras, where he was advised by Professor Kamakoti. Over to Arjun.
Thank you. So, how many of you have heard the Turing Award lecture of Hennessy and Patterson? Have you guys heard the name Hennessy and Patterson? Yes? Okay. So, in their lecture, right, they mention how Moore's law has ended and how people are moving towards custom silicon, right, where you try to make a chip that is pretty much tailor-made for one particular application, and that is the way to go forward. Second, you would have heard a lot of stories about how India is trying to become a semiconductor hub for the world, right? And that can happen only when you have a lot of designs, people building a lot of chips out of India. So what we are trying to do here is that the way people design SoCs today are pretty outdated, right? There are a couple of issues with the way it's done today. Here we have proposed a new methodology that people can adopt. So I'll talk a bit about the methodology and how it solves the problem for different people operating on different aspects of SoC design, from hardware to software to FPGA. Before I begin, I would like to give a quick introduction about us, about the company. We are a semicon design startup based out of IIT Madras Research Park, where that's our headquarters. We also have a smaller office in Bangalore and in Gurgaon. We are providers of world-class RISC-V solutions, mostly targeted towards the embedded domain. We are also the designers of RISC-V Compliance Suite. RISC-V Compliance Suite is basically the test of suites, basically a suite of tests which you have to run to call yourself RISC-V compliant. That particular framework was designed by Incore. In fact, we have been working on RISC-V even before RISC-V became an actual standard. Professor Kamakoti was in touch with people at Berkeley, and when we started working on the Shakti project, three of us who are co-founders were part of the Shakti project ever since it started. Madhu, whom you would have heard in the morning, who is our CEO, he was the program manager at Shakti. Neil joined as a project associate and then ended up finishing his PhD at IIT Madras. I joined as an intern and then finished my master's and then joined Incore. So all of us have been working on RISC-V since 2012, right? That's when we first got in touch with them. So we have been at this for a long time. The current strength of the company is about 35 to 40 people, and we raised our seed round back in 2023 from peak 15. All right. So I'm sure you have heard a lot about RISC-V, right? RISC-V is a set of instructions. It basically tells you that if you are able to execute these 50 or 100 instructions, you can call yourself RISC-V compliant. But RISC-V is still just a standard. It just tells you that there are these instructions that you're supposed to execute. At the end, you have to still go ahead and implement a processor that realizes all of these instructions, right? But just the processor is not sufficient. Think about an application. Let's say you're trying to build an IoT device, right? You will have some sensors, you will have to collect data, you will have to talk to a Bluetooth module or a Wi-Fi module, right? So processor along with all of these blocks together form what is called as a system on chip or an SoC. So let's have a quick look at how do you build a simple SoC, right? There are a couple of choices that you have to make. The first and the most important one is what is the number of cores or the type of cores that you choose? Do you want a small low power core or do you want a big, high performance core? Do you want one core, two cores? Do you want a mixture of high performance and low performance cores? What do you want? And that really depends on the kind of application that you're targeting. So the second is accelerators. If you're designing a chip for a particular application, you would want to design custom hardware for that application. It may be AI/ML, right? Or it can be as simple as an FFT module. You can add an accelerator for FFT. In some cases, you may also want accelerators for security, like for encryption algorithms, right? And these accelerators can either be tightly or loosely coupled. What I mean by that is, when you have a core, you can connect the accelerator directly into the core pipeline, or it can sit further away where the latency is more, but can be shared across multiple different people, right? What about memories? How many levels of caches do you have? What sizes of caches? Do you have an on-chip RAM? Do you have an on-chip flash memory, a persistent storage, or do you put DDR controllers in there, or do you just use some low-speed peripherals like Octal SPI to connect an external memory? And a bunch of other peripherals like I2C, UART, and a plethora of other options that you can choose from. Finally, when you have all of these components, how do you connect them together, right? At the end of the day, the processor has to talk to each of these components. How do you do that? There are standard fabric protocols that are defined like AXI4, APB, TileLink, and so on. You have to choose one of these protocols and make sure that everybody talks the same language, right? Finally, you decide how do you clock? Does everything run on the same clock? Do you have the capability to turn off clocks for different parts of the design? Can you shut down some cores when they're not in use? How does resets work? Is it just one reset, or can multiple people reset your system? And when you have multiple devices or peripherals that are connected, you may want to support interrupts so that, as soon as a peripheral is done doing what it is supposed to do, it can notify the core, and then the core can go ahead and do something else, right? Those are sideband connections. And finally, you have I/O pad assignments, where for your chip, you decide how many I/O pads would I put. Do I put 50? Do I put 100? If I can afford only 50 I/O pads, because my board has to be really small, how do I make sure that all of my peripherals fit and are able to communicate with each other with just these 50 pins, right? So and all of this really depends on the type of application that you're trying to build, right? But let's say you figure that out and you have all of these specs that you have jotted down. you would go ahead and try to design the RTL, right? And once you have designed the RTL, which may be in any language, right? Verilog or System Verilog, VHDL, BlueSpec. You first go ahead and do an FPGA prototyping where you make sure that what you have designed actually does work. And then once you have verified and run a couple of test cases on the FPGA and in simulation, you go ahead and tape it out. That's, you go from RTL to GDS and then you send it out to the fab. So what is the problem that we're solving? Well, it's 2025 and building this SoC is still hard, right? If you consider a new chip design, it takes anywhere between 12 to 24 months. And it takes between $5 to $250 million to develop this entire thing. And 30 to 60% of this cost is just spent on design and verif, right? If you look at how SoCs are built, the programming languages that are used, the methodologies that are used have been existent for a very long time, right? Almost from the 70s, nothing has materialistically changed in the way people design SoCs. And moreover, think about how do you, if you want to design a new chip, you wouldn't really go ahead and develop every single IP that is there, right? Take an example of a simple IoT chip that will have 20 plus IP blocks. You will not go ahead and develop every single IP block on yourself. It does not make sense to do that because you will take way too long to develop this, and somebody else will go ahead and manufacture this chip much before you. And let's say you want to buy these IPs from third-party vendors, right? How do you choose a vendor? How do you know that this guy's IP really matches your requirements? So you have to select a person, you have to qualify their IP, you have to then talk to them about how do you license it, how do you price it, you have to negotiate on that, and then you will finally come back, integrate, and then verify if it works with your system, right? And all of this is pretty time consuming, right? What if you could design SoCs in an automated way which is correct by construction, right? And that is the thought that we had, and that's precisely what we are developing here at Incore. There are 4 different components to this solution, right? The very first thing is that because we are generalizing this, we need to have a portfolio of IPs that can cater from lowest power to, let's say, highest performance in the embedded domain itself, right? And how do we achieve that? We understood that RISC-V is the right bet to make. It is a configurable ISA. You can choose if you want a 32-bit, a 64-bit, do you want a multiplier, do you want a floating point unit? All of that is something that you can choose, right? Moreover, it gives you the ability to add new instructions if you want to. Second, we wanted to design these processor cores which are really programmable or configurable. In order to do that, we used a language called BlueSpec System Verilog. This allows you to write RTL code in a very highly parameterized manner, which is close to impossible using Verilog or VHDL. We also have developed novel design methodologies, specifically on the verification side and also on automating some of the BlueSpec generation itself. I'll talk more about that in the subsequent slides. Finally, we have partnered up with certain IP vendors so that we onboard these IPs onto our platform so that when new people are trying to design these SoCs, you do not have to worry about a lot of sourcing or any IP related issues. So all of these components again translate to various different IPs that we are developing at Incore. Today, we are shipping 2 different core hub generators. So I call them core hub generators because it is not just a single core. There are hundreds of parameters that you can choose from, and you can actually get a very PPA optimal, power performance area optimal code. Today we are shipping 2 of our series, which is the Azurite and Calcite series, for which the data sheets are available. The Azurite series is something that we are really proud of what we achieved. We have published these numbers, and we are comparable or even better than ARM in some of these SKUs. The Calcite is a much more higher performant version of the core. Later this year, we will also be releasing a dual issue version of the processor. Along with the processor, we also develop fabrics, which is the protocols like Axie4, Axie4 Lite, plus a bunch of other things like a debug module that allows you to connect GDB, a trace, triggers, and so on. Next is doc generator. I have never seen people talk about documentation enough, right? But documentation is really important. For those of you who have built things, you will know that if the documentation is bad, it is really difficult to build something with that, right? So we have a document generator which automatically generates the document for both the core and also for the entire SoC. We also have a wide portfolio of accelerators and other IPs. Accelerators specifically like Vector, which you can use for AI/ML, and almost all commonly used security algorithms. The core being configurable is just a small part of the story, right? If you have a configurable core, how do you make sure that every single configuration output that this generator generates is actually verified? For that, we have a verification generator, which basically generates test cases for that particular instance of the core. In order to do this, we have used a language called EUVM, which is embedded UVM. This is a domain-specific language written in D. And this basically enables us to come up with this verification generator that ensures that you get good coverage numbers for every single instance of the core that comes out. Of course, it is not 100% there. Once you get out a version, there will be some part of it which you will have to hand-tune to make sure that you get pretty high coverage numbers, but this gets you up and running and gets you to, let's say, 80 to 90% right on day one. Finally, software, right? Software is a big important point. The hardware is useful only as much as the software is able to utilize this. Today, when you're generating a new SOC, people take time to develop the software on top of it. We are trying to automate it and give you at least basic board support packages and operating system support so that you can get started on day one. But how does all of this work, right? The input to this tool is a set of specifications. You will have a core specification, you will have a hub specification, and a SOC specification, plus a bunch of other things, right? All of these are captured in YAML, and this is fed into our automation tool, which generates various collateral for RTL, verification, software, and documentation. So once you give this input, the output would look something like this. You have your SOC subsystem RTL, which consists of RISC-V cores, the accelerators, other components like the peripherals, the debugger, and so on. On the other IP collateral on software, we provide a GCC and an LLVM toolchain for that particular instance of the core. There is OpenOCD so that you can connect GDB to it. There are ISA models so that you can start simulating your software. There is also an SDK, IDE, and standard operating systems that we support, which are FreeRTOS, Zephyr, and a basic Linux port. On verification, we provide you with unit-level knock tests. There are assembly tests for cores. There are SOC integration tests. And the last one, which is an industry standard, almost everybody who works in the industry use all of these standards called RDL, UVM, and IPExact to be able to generate and verify certain IPs. We provide all of that as collateral. Finally, we also provide some support so that you can go to FPGA and ASIC pretty quickly. At least for the FPGA front, for SOCs, we do have a simple flow that can take you from RTL to an actual FPGA prototype. For ASIC, today we provide constraints and synthesis scripts, which basically let you go from RTL to, let's say, the synthesized netlist. Beyond that is something which we have not looked at currently. So how does this help? Well, first of all, it reduces the cost, time, and risk to develop this new SoC. I had mentioned that it takes about 12 to 24 months to develop a new SoC. Our aim is to reduce that 12 to 4, right? That's our golden goal. Now, I spoke to somebody here who said they wanted to do a startup. Some people on the fab side, some people on, design. I think a tool like this would really help you guys out because, when you start off to build, there are a lot of things that you do not know. You may not know how to design the entire SoC. There might be components that you might not completely be aware of. I think tools like these will really help people who are starting off, startups who want to do SOCs and get up and running really fast. Also for people who are looking to transition to RISC-V, it is not as simple as just picking out an ARM core and just dropping in a RISC-V core. It doesn't work like that, right? This acts as a platform so that you can transition from ARM to RISC-V in a much more easy manner because we give you all the required collaterals that help you get started and running. Finally, streamlining IP management. For those of you who have worked on maybe complex softwares, you know that IP management or software versioning management is also a task, right? What happens is different people work on different parts of the SoC. There'll be somebody working on RTL, somebody working on documentation, somebody writing software, and it is very easy for all of them to go out of sync, right? The R framework ensures that because it is automated, everything has the same view of the world, right? The YAML file is the ground truth, and every single component of the SoC always are consistent with each other. Finally, it acts as a wingman for front-end engineers. It removes most of the mundane tasks that you would have to do or debug these issues. Especially if you take a pretty complex, even a simple SoC for that matter, there will be people who are designing software, there will be people who are designing hardware, somebody designing FPGA prototypes, somebody writing software test cases. What happens when there is a bug, right? People don't really know which part of the SoC actually has the bug. There'll be somebody trying to see if it is a problem in the IP, right? And then they have to prove that it is not a problem in the IP, and then it moves on to the next person. And so on, and it just gets passed on. And there is a delay in all of these communication, and that in turn results in higher development time. And that is primarily the reason why it takes so long to, develop these chips. The fix might be a simple one-line change, but then to figure out that one line, you will end up spending 2 to 3 weeks. And that is what we want to remove, right? Where we provide a correct by construction methodology so that such bugs are not there to begin with. So double-clicking on the impact, it helps various teams, the hardware team, because it removes the headache of solving mundane tasks. The verification team, because it gives you an environment to work with, it gives you some test cases for the course and even for the SoC that it can get you started. It helps the software development team because you have a board support package to get started, and then you can develop on top of that to write more test cases. The FPGA prototyping team, the project management team, because now the process is more streamlined. You can make better predictions of how long a particular project would take. The system architecture team, if you want to do SOC exploration, if you want to remove a peripheral, you want to put in a new peripheral, it is very easy to do it because all you have to do is edit a YAML file rather than go ahead and change every single part of the FPGA, right? So that really helps you to go ahead and iterate on the FPGA rather than some model and simulation and run your actual application and see what makes the best sense for you. And finally, the documentation team. All right. That is it. We are hiring. If you are a curious person who wants to build cool but hard things, please join us in our journey where we are trying to build the best semiconductor IP out of India for the world. Thank you. Any questions? Can we have a mic?
Hi, Arjun. Really good presentation. So I just had a couple of questions to ask. So I'm an engineer at Intel, right? And the way we design SoCs is entirely dependent on the market requirement. So I just wanted to ask, how flexible is this SOC generator? Let's say, for example, I'll give a recent example from Intel. They designed a Luna Lake SOC, and in that case, they integrated the memory controller inside the compute tile. So I just wanted to know, let's say if I'm using Incore's SOC generator, how flexible it is, and how, let's say I want to make a whole change from start, how flexible is this tool to ensure that it meets my requirements?
Right. So I think in my slides I would have mentioned in one place that we are not trying to automate the entire process of SOC design, because every single SOC will have something that is specific to them, right? There might be something that you're doing, that's your secret sauce, and that's your special thing that you may be putting in your SOC, right? So what this lets you do is get to 0 to 80 or 0 to 90 pretty fast. It really depends on the kind of customizations that you're requiring. If what you're doing is standard, then you should be able to do everything, all of that with this SOC gen. If you're doing something that is pretty custom, then today, yes, we do not support that. That's the short answer.
Yeah, thank you. I just have one more follow-up question, if you don't mind. So I just wanted to know whether this SOC generator is compatible with other ISAs, because I saw that you mentioned about accelerators.
Yeah.
And accelerators, the first thing that come to my mind is extensions, like mostly SIMD extensions. So SVE, SME. So these extensions are not exactly mature enough in RISC-V ISA. So RISC-V only has RVV 1.0. And compared to ARM and x86, they are not really that advanced, and they're not mature enough to have a proper performance PPA optimized chip.
Right.
So I wanted to know whether SOC Gen is compatible with other ISAs in the future or currently.
Right. Theoretically, yes, you can do it. But then there are a lot of components of the SOC Gen. For example, if all that you care is the RTL, then yes, you can probably plug in an ARM core and you can get it out. But there are a lot of other collaterals that I talked about, right? And some of them are RISC-V specific. The software stack and all of that is pretty RISC-V specific. So automating that would not be possible. So some subsets of SOCGen can be used for other ISAs, but not everything.
Thank you, Arjun. Thank you.
Sure. Okay.
Hello. Yes. I actually have a question regarding your intake. You guys take in master students also?
Yes, we do. Like I said, all we are looking for is people who are curious to learn and who are motivated enough to work hard, right? We mostly look for basic skills. Like if you've done courses, we would check if your basics are good. And we would ask you questions on whatever you have mentioned on your resume. That's primarily what we are looking for in freshers.
So when does it begin, the intake and all?
I mean, you can apply. We are hiring today. So,
okay. Yeah. Suppose if you apply and, a specific period will start, right?
Yeah, I mean, you can just scan this, send in your resume, and if you qualify, somebody should reach out to you
okay.
soon. Yeah.
So it's immediate?
Sorry?
The intake is immediate then?
Yeah.
Okay.
Okay. All right. If there are no other questions, thank you once again.
Thanks, Arjun. Some logistics announcements. Somebody has lost their credit card pouch. It's available with the media person who's standing behind the stage. You can collect it from him. And for people who wanting to leave early, we just want to make an announcement. At the end of this evening session, we have two IITM professors, Professor Chester Ribeiro and Gopal, who will be providing you details about sharing their work as well as the internship and the opportunities to work with their groups. So they will be sharing the information about that. We would urge you to stay back and not leave early. And some goodies will be given, I think, during the tea break. So please feel free to collect it before entering the session. Over to our next speaker. Sorry, Nitya, Chitra, for taking it up. Slide number 9 has to come up. Thank you. It's a pleasure for me to introduce Chitra to all of you. Chitra Hariharan is a serial entrepreneur and techno-commercial leader coming with rich industry experience with a unique mix of corporate and startups in the electronics and semiconductor domain. Currently, Chitra is heading startup collaborations, university relations, and government affairs at Renesas. She has had 2 leadership stints at Intel and successfully built 4 semiconductor and electronics product startups, being part of the founding team, carrying out technical, commercial, and operational roles. All the 4 startups, Intel Microelectronics, Open Silicon, Concept to Silicon, and Zensoft, had successful exits. I think they'll be very excited to hear from you. Over to you, Chitra.
Thank you, Lavanya. Thank you so much. It's always a pleasure to be here, and that too at IIT Madras, the institution that is extremely close to my heart. I always keep telling either to the professors or students whenever I come to IIT Madras, there is always good and tons of memories that you take it. And I think 2001, when I came to IIT Madras, may not be the first time, but at least in the recent years, I would say the RISE lab was just getting formed, and we could be the people from the industry along with the rest of the other people like Dr. Satya Gupta and Navesh Sharwani. We all were the ones. I was part of Open Silicon, the startup that Lavanya mentioned, and we were the first ones to write the first check for RISE lab, and today RISE lab has become the kind of the North Star, I would say, for multitude of labs that have come across multiple IITs. With that small memory, I'm just beginning here, and then over there, the kind of the accomplishments that have happened, and whenever I get to interact with some of the students, they all say that, I learned so much from this lab. I learned so much from being part of Shakti's team, being part of this team, right? So it's always such a great feel. With that, we will start. I was here just 2 weeks before also for VLSI Society of India's Tamil Nadu chapter inauguration. I actually hold the position as secretary as VLSI Society of India. So this is one organization, if you are all aware of the VLSI Design Conference and VLSI Design and Test Conference, right? This is the organization that has been running this conference for years and years. And Professor Mahabala, who used to be at IIT Madras, he has been the founding member along with Vishwani Agarwal. So I can go on and on about IIT Madras, but this talk is about Viksit Bharat, so we are all in the kind of the journey of making Viksit Bharat 2047 happen. So yesterday you all heard from the former minister Rajiv Chandrasekhar also about if he had one wish, right, he would want to be born again, or he was telling that I should be living in this era of opportunities. At least 20 years later, if I had born, I would be able to witness a lot of advancements that are happening in the field. I carry the same wish as well. So while he was talking about it, I was thinking that, oh, okay, this is the... So the point is, we are all living in the golden era of opportunities. You are all going to be the flag bearers for taking this opportunity forward. And I will just touch upon a few of the things on how I really mean that, this is the golden era of opportunities. Okay. So we have come a long way. You all know this famous picture of how we started the rocket carrying, how it really happened, right? From there to Chandrayaan, right? We have come a long way. So this really shows that, India is on the move, and this is happening at a very foundational level, right? Everything that you touch, be it on some of the drives that are happening, they're all the catalysts to make this drive and then move happen, right? So all these things, I mean, you might be very familiar with Startup India movement, Digital India movement, Make in India movement, and India Semicon mission, right? These are the right movements that are really propelling India's growth forward, right? And then we all know about the digital public infrastructure. This is really happening at the population scale, right? And we all know the success of Aadhaar, UPI, ONDC, and Vande Bharat Express. I'm going to be taking the train as well, so I'm just telling. This train really had made my commute between Chennai to Bangalore literally like you take the Uber from here and then go from point A to point B. It has really become like that. So we all are witnessing the growth of in every sectors that you can think of. And we are today at economy 5th position, holding the 5th position in the economy. Digital payments, we all know that, I mean, we are sitting at first. Data, we are the first people. I mean, we hold the #1 position when it comes to the data consumption. And when it comes to the mobile, I mean, it is the second. And startups, I mean, ours is the startup numbers across the globe, we are holding #2 as the position, right? And railways, ours is the 3rd position. So these are some of the global positioning that really says that we are really on the move, right? With this given, what is happening in the electronics and semiconductor and what kind of the opportunity that we are seeing, right? If you look at the electronics market and semiconductor market, right, we are holding today, $200 billion worth of the electronics is getting consumed, and out of which $40 billion worth of semiconductor consumption is happening just in India. This is just in 2023. So if you look at 2030, this is expected to grow to $500 billion, and on the chip side, it is expected to grow to $135 billion. These are some numbers that I'm throwing just to ensure that the opportunity that you're all seeing in front of you is completely validated. That's the reason for showing all these numbers. So if you look at 2047, this is going to be sitting at $1 trillion worth of the consumption that India is going to be seeing on the electronic side, and on the semiconductor side, it's going to be 810 billion. So this is huge, right? So given this, what can we do? This is going to be constituting to 10.2% of our GDP, and this is going to create at least 10 crore employment, right? So given this, what is the opportunity that we can grab for ourselves? Let's look at the near term. Near term is 2030. I'm picking it up. So semiconductor products and electronic products, they are intertwined. We are all aware of it, right? So the 200 billion number that I mentioned on the electronics side of it, the consumption is going to be growing to 500 billion. Let's assume currently we are sitting at 10%. If you are just grabbing 30%, this means it is 166 billion worth of opportunity we are sitting, right, when it comes to 2030. So on the chip side, it is 40 billion. This again, you project it at the 33%. This is going to be getting to the number of 45 billion opportunity, just the near-term opportunity. So given this is the near-term opportunity, there are multiple areas wherein we are seeing this growth. The growth is #1 in product space, electronics, chips and ICs I spoke about, and manufacturing. We are all aware of the electronics and the semicon side of it, the fab and ATMP, all the announcements, we are all aware how many ATMPs are coming, how many fabs are coming. So this is really the golden era for India on the manufacturing side as well. And on the skill part of it, there is going to be a humongous requirement and humongous growth opportunities that we are seeing, both on the engineering and on the research front, right? So given this, right, there are multiple technology trends that are going to be shaping the India that we are going to be witnessing now. So I'll just touch upon few of the technology trends, and then these are the growth domains that I'm seeing, and then we can go each of the growth domains and then check in each of this, what kind of the product opportunities we have. Okay, so we all know about AML. Yesterday, Kama also mentioned that even IIT Madras, monkey would want to be learning about A and ML, right? Which is very, very true. So AML is going to be the killer app of the decade, but this is going to be touching every growth domain, starting with auto EV, consumer electronics, telecom wireless, medical biotech, energy clean tech, right? And then space and defense. Started the presentation also with the Chandrayaan landing, right? So space, there are multitude of space startups that have happened from the IIT Madras Research Park. Also, Agnikul is one example that I can immediately quote, right? So point is, in all these growth domains, AML is going to be impacting, that we are all acknowledging and then understanding. So over here, what kind of the trends in the chip design that we are seeing? Arjun did talk about the SOC generator, I mean, which is the next click of each of the chip design, how all this automation is going to be helping, and then how the implementation cycle is going to be coming down, right? I am just touching upon the trends in the chip design, right? Over here, security is going to be the biggest mantra. We all know about it. And custom chips, he did talk about it. Custom chips are going to be the emerging trends. I mean, we all have been living in the world of the standard products that's really moving to multiple application-specific integrated circuits and custom chips that are going to be the defining ones for the specific application that you're thinking about. And then the architecture, multitude of architecture explosion that we are seeing, chiplets and advanced packaging, we are all aware, and communication and wireless functionality in every chip is going to be the mantra. And photonics and then the interconnect between the chips, right? And we all know about the vertical integration and the heterogeneous integration that are going to be dominating the chip implementation side of it, right? So with these emerging technologies, right, what kind of the opportunity that this is throwing up for chips and products? This is what I'll just touch upon. So these opportunities need to be turned into business, right? So we all know about UPI. UPI, we have spoken about UPI. We as India hold the #1 position. But we could really turn a business opportunity out of holding the #1 position. That is, if we can create the UPI voice boxes, right? So UPI voice boxes, this just could be implemented with RISC-V processors and small GSM, and you need a speaker. That's pretty much the volume that I have put is a very, very minimalistic volume. But the point is, such simple products could be realized, #1, with RISC-V kind of the architecture, #2, with the available technologies. Okay, so now I would throw another example. So this example is about the e-passport. We all know about passports is getting into the e-passport. So for e-passport, again, RISC-V could play a crucial role. This would need an ultra low power RISC-V version of it. We would need a small passive RF component. And then if this could be implemented in an ultra thin package, we will be able to get the passports rolling out. So the volume expected is more than 200 million, but the point is this is still realizable, and government tenders and things are already in discussion. So the next opportunity that I am talking about is DigiYatra. We all know about the DigiYatra, which is easing the entry and then exit for entry for us in every airport. For DigiYatra, the kind of the small device that we are seeing, right, similar to that, we will be able to come up with the camera-based appliances or the devices. This could be used at multiple places. DigiYatra, I just picked up as an example. It could be at multiple security check places, right? This just could be realized with multi-core RISC-V processor, and a small Android tablet is required. Face recognition technique is required. Over here, I put a very, very minimal volume of 100K. This could definitely go beyond 100K. Okay. So, and the other thing, other application is the drone flight controller. I'm already seeing companies like Ahisa here already, and then we all know about Idea Forge kind of the companies. India-born companies, startups have become IPO already, right, on the drone part of it. So over here, again, there is a potential for RISC-V processor to get used with a small communication module and a security module added. The volume could easily be 100K, and there are, again, applications that are coming just not in the, earlier days, if you look at drones would be either in agri-tech, or drones could be primarily in the defense and other applications. These days, drones are everywhere. You look at any of the entertainment, instead of fireworks, drones are being used, right? So the application areas are also changing and emerging. So this again is a very good use case, and then the product opportunity that I want to highlight. So, and then the next product opportunity is the BLDC fan controller. Over here, again, simple RISC-V processor with a small Wi-Fi, right? The volumes are just more than 100 million, right? So point is, opportunities for product build just with RISC-V are plenty, right? You have a lot of students here. I would really urge you all to think on the opportunities to build the products, and then the ecosystem would be able to support you to build the products. The company ecosystem, the industry ecosystem. We have NXP here. I'm from Renesas. We all can provide you the required reference design kits and boards and help you realize the products. Okay. The other opportunity that I just want to touch upon is the powertronics. So powertronics, the EV, if you look at, I've just given the tear down of the EV. Every part, there is a subsystem build opportunity. So before you get to build the product from silicon, there is a subsystem build opportunity that the companies can focus on, and then they could be the suppliers for the product companies. So if you look at the EV, CCU, motor controller unit, portable charger, inverter, every subsystem could get into a good business case, and then the business opportunity is what I want to highlight here. And then all the UPS, inverters, industrial products, and everything, you would have the similar subsystem build applications. Again, Traintronics, it's another opportunity wherein I'm really hearing that, this is going to be a multi-billion opportunity. This is going to be the 10% of the budget is getting allocated just for enhancing the experience in the train, and then the electronics and infotainment components that would get added to the trains, added to multitude of trains. So point is, India semiconductor mission and then MeitY are in the middle of creating lot of product development ecosystem. So there are humongous incentives that are being given to get the fabs up and running, to get the ATMP plants up and running, to get the product development ecosystem up and running. So just wanted to show that, how many fabs are coming, how many display fabs, and then the compound semiconductor fabs. There are already fabs that are up and running. I'm sure you're all aware, Micron fab, it's up and running. Tata fab, it is up and running. Both in Gujarat and in Assam. All these places, you're going to have multiple employment opportunities as well, right? And I'm sure you're all aware of the design-linked incentive schemes that again are coming from Ministry of Electronics. So over here, you're seeing multiple startups that they're all part of here. They're all part of availing the design-linked incentive scheme. So there is going to be the next DLI 2.0 that is going to be getting rolled out. I think the applications are also being asked for the new startups to roll in. The point is, if you have a good idea, be it on the IP side, be it on the product development side, even if you are a student, you could be part of, you could attach yourself to be part of some incubator, and you could still submit the application and see how your ideas could be realized into IPs or into product. Okay, this is about the C2S program. I'm sure you're all aware, this is the Chip to Startup program. If your college or institution is not part of the C2S program, I would really urge you to go and speak to your management and see whether you could become part of the C2S program. The reason is C2S program provides you the access to all the state-of-art EDA tools that would make yourself ready to embrace the challenges from industry. So you would have access to all the tools from Synopsys, Cadence, Ansys, and all the some amount of the boards and other access, Siemens EDA tools as well. So Chip in Center is the body, that brings all the, if you have an idea that needs to be taped out, you could become part of the C2S programs, and then you would be able to get your RTL, take it forward with all the tools that I mentioned, and then make the tape out happen. There is a fab partnership, there is a package partnership as well. So the infrastructure exists for you to take the idea all the way up to silicon and take the package parts, get into the testing as well. So ensure that, you are the benefit, you or your college gets the benefits of the C2S program. I am from Renesas. I just want to show that, what are the focus areas, just taking one of the MNC as a use case, that these are our focus areas, and automotive, industrial, infrastructure, and IoT. So over here, again, there are plethora of opportunities that exist. I take care of university relations. I do work with multiple colleges as well, and then we provide our reference design kits to your universities, and then you will be able to realize some of the products that you are having in mind through the reference design kits that we are providing. Just wanted to touch upon that. So multiple such companies are doing this, so ensure that, you are availing these opportunities. Okay, gone are the days wherein we used to be telling that hardware is hard. We want to be, yesterday Kama was mentioning that this is the first VLSI event. This is the first event in IIT which is taking 900 plus audience in this auditorium, right? So maybe we are coming out of the era wherein, we have been telling that hardware is hard. It is not true. Hardware is not hard. So get that myth out. You will be able to realize a lot of things just with all the infrastructures and with all the technologies and then things that you are seeing around you. Just treat this as the chip design is nothing like it is like a software design, software code that you are doing, but only thing is the diligence and the amount of care that you need to be doing for realizing the chip is very much huge. That's how I would put it. But don't get the myth out that hardware is hard. I just want to leave you all with this. These informations are all validated. There are plenty of jobs available. So the projection that we are getting from the government and talking to multiple MNCs is 125,000 design engineer requirement is being forecasted for the following 5 years. So by 2030, till 2030, we are looking at the opportunity of having employment opportunities for 125,000 design engineers and 10,000 engineers for all the manufacturing efforts that we are doing across India. Okay. So I think that should excite you all, right? 125,000 is a big number, right? I have not seen this kind of the number when we all had the opportunities. So the package is also pretty good. So I think you all should be pretty excited is how I would say. And with all the infrastructure that I mentioned, ensure that you would be able to do one tape out before you graduate. Okay. So again, on the startup side also, hardware startups, people always say that hardware startups are hard to build. I think we have multiple hardware successful startup founders. I mean, I had founded 4 startups, and then it is not hard. It is not that hard, I would say. You will have to do. It is as hard as building a software startup, I would say, because people think that hardware startup is really hard to build and software startups are easy to build. Both bring their own set of challenges, but get the myth out at least is all I would say. So there are, I did mention the success stories. I mean, Steradian, Idea Forge, Adverb. I mean, there are multiple such hardware success stories are also there. So think about building a startup when the ecosystem is so conducive. I'll just leave you with the global semiconductor ecosystem. So these are the companies that you can kind of think of when you are looking at the semicon as the opportunity, right? So this is manufacturing, product design, IDM, equipment, software tools, and then the IP blocks. Okay. With that, I will stop. If you have any questions, I am available. I mean, we can talk. Thank you.
Any questions? Thank you. Thanks. We welcome our next speaker. Umesh Sisodia is the founder and CEO of Circuit Sutra Technologies, a company focused on SystemC based shift left ESL methodologies. He has 25 plus years of industry experience and worked with semiconductor and cadence before starting Circuit Sutra. Umesh played an important role in the evolution and adoption of SystemC in the industry. He is also awarded by Accelera Systems Initiative for driving the adoption of standards in the Indian ecosystem. Umesh worked with industry leaders to bring an international conference, DVCon, to India, and was the chair of DVCon India 2014, an annual conference being held in Bangalore. Please welcome Umesh.
So good afternoon, everyone. So today I'm going to present about higher abstraction shift left methodologies for the RISC-V ecosystem. So if we see the history of semiconductor industry, so right since the inception, there has been continuous advancement on the multiple fronts, and due to which the chips are continuously becoming more and more complex and more powerful. So because of that, today, I mean, we are able to see the application areas in which the semiconductor chips are being used, which could not be imagined in the past, like artificial intelligence, vision, automotive, etc. So in any chip, the most fundamental unit which goes inside a chip is a transistor. Now, due to the advancement in the fabrication technology, all of us know that the size of the transistor is continuously reducing, and due to that, the number of transistors that go inside a chip, that has been exploding. I mean, the very first chip had maybe a couple of thousand transistors inside it, but today we are talking about multiples of tens of billions of transistors in a single chip. So you can imagine, like, what's the quantum of, what's the size of electronics that actually goes inside a single chip. On the other parameters like memory, on the memory front also enhancements are happening. So we are seeing like more faster memories with higher storage capacity, etc. Another important invention which happened in 1971 was the invention of microprocessor. So after that, any electronic product need not have just the hardware inside it. I mean, it can have a combination of hardware and software. And since then, the amount of software that goes inside the electronic product, that has also been continuously like increasing. So today we have like multiple processor architectures, like we have Intel x86, ARM, and the latest one which we have is RISC-V. So with all these advancements, the chips are becoming so complex that it's not very easy to design these complex chips. The cost of designing such chips is significantly rising, design and verification of this, and the probability of first silicon success is very low. I mean, when you conceptualize a chip, I mean, there are very less chances that the first silicon out will actually fully meet the requirement of the market. I mean, some kind of flaw is likely to get introduced. There could be like functionality issue, or it could be that maybe it's not working fine with the target software application, or maybe like it's not like meeting the requirement of how much power it should consume or what should be the performance, etc. So because of that, I mean, most of the time you require costly respin. So as Professor Kamakoti told yesterday, I mean, it's not a software. Like if your customer finds some bugs, you cannot just release a patch on it. I mean, you will have to do a costly respin. You will have to fabricate the chip again, fix the issue, fabricate it again, and then ship it out. So it's quite expensive to do that. So because of this increasing chip complexity, I mean, there is a requirement for new kind of like design methodologies. I mean, if we see historically, the chip design methodologies have also evolved continuously. And this evolution came mainly in the form of raising the abstraction of chip design. So in the beginning, like we used to design at the component level, transistor, diode, capacitors, etc. And as the complexity increased, there came a concept of gates. So we started designing at the gate level. And then further came the RTL, like Verilog, VHDL, etc. And we designed with that. So this RTL to GDS flow has been in the industry since long time, maybe since 1980s. So with the chips of complexity of today, the RTL to GDS flow alone is not sufficient to design the chips of the complexity of today, and there is a requirement for further raising the abstraction actually. Now today, the raising of abstraction is happening in a multiple front actually. I mean, on one way, people are moving from, so as we see in the Incore presentation as well, people are moving from designing a specific IPs to maybe SoC level, and further even today people are moving to chiplet actually. So that's one way in which the abstraction is raising. The other way which I'm going to talk about is like, I mean, so it requires, so these are like higher abstraction shift left methodologies, so which requires developing the fast simulation models of the system on chip, IP, CPU at an abstraction above the RTL, above the Verilog, using the high level languages like SystemC, C++, etc. So these simulation models can actually simulate maybe 1,000 times faster than Verilog, and these enables certain design operations which are not actually feasible in a traditional RTL to GDS flow. So like we can develop a virtual prototype of a SoC or a system which can be used for pre-silicon software development kind of thing. When we are conceptualizing a new SoC, so we can develop the models which can be used to do the architecture exploration, optimizing the architecture for specific target applications, etc. Or the real design itself we can do at a higher abstraction level. Instead of writing Verilog, we can actually write the functionality in C++ SystemC, and using the HLS tools, we can generate the RTL out of it. And then the most important thing, I mean, it enables to do the simulation at the SoC level and the system level at a reasonably fast speed. So it's not a completely new kind of thing which is going to replace the existing flow. So it actually augments the existing RTL to GDS flow and coexist with that. So it significantly reduces the cost, the time to market, and enables you to optimize the architecture for specific applications. So in short, it enhances the probability of first time silicon success. So the two key trends which are happening in the industry today, one is like designing the semiconductors, the custom semiconductor chips for the artificial intelligence and deep learning. And second is this RISC-V ISA, which is an open standard and customizable. And many times we see a combination of both. I mean, because of the customizability feature of RISC-V, So people are actually using RISC-V to design the custom SoCs for artificial intelligence, etc. So if we talk about artificial intelligence or deep learning SoC, so primarily it requires some kind of custom processing and a specialized SoC architecture. So conventional architectures, when human kind of thing, or conventional processors, I mean, that's not just sufficient. We need to create some custom architectures for it. These kind of chips have some very specific requirements, like requirement for huge data processing, real-time data connectivity for the data coming from various sensors, etc., where the decisions has to be taken in the real time. A huge bandwidth for the on-chip data communication and off-chip data communication. Optimum power and performance is required, and any such chip has to actually work fine with the popular frameworks like TensorFlow, PyTorch, ONNX, etc. So primarily we have to design the chips for like compute for data in motion, which requires like massive parallelism at the data processing level and at the instruction level. Innovative memory architectures are required. So people today are talking about like in-compute memory or tightly coupled memories, etc. And huge memory size is required. And many times like people are trying to accelerate different algorithms inside the chip. So for designing these kind of SoCs, I mean, effective use of shift-left methodologies is very important. So let's say in the beginning, I mean, we can develop a virtual prototype, which is a register-accurate fast simulation model, which can simulate 1,000 times faster than Verilog, as fast as real hardware, and on which you can run your real software. The actual software which is going to run on the final chip, that you can actually run on this model, and it enables the pre-silicon software development kind of thing. And even after the chip is available, even after that, you can actually continue to use it for continuous integration and continuous development of your software stack, which may keep on changing throughout the life cycle of that chip. Architecture analysis and optimization is very important. For example, performance optimization is important. Many times these chips are being used for real time, like decision making, etc., where the performance is highly critical. Power optimization is again very important, irrespective of whether these chips are being used in the data center, where the power consumption is a major expense there, or whether these chips are being used in the edge devices, where they may not have a continuous source of power. And also, I mean, there is a possibility to accelerate various kind of algorithms, neural networks, etc. So where it is highly effective that instead of you handcrafting the Verilog, I mean, the functionality can be described in a higher level language, and using the HLS tool, it can be synthesized to generate the Verilog. So now coming to RISC-V. So RISC-V is an open standard, which is a instruction set architecture, and it's a customizable. So you can actually customize it further, add your own extensions, etc. So which further enables more innovation. But at the same time, it introduces more complexity as well, another element of complexity. So effective use of like shift-left methodologies again become very important, and anyone trying to develop a SoC using RISC-V, I mean, they may also intend to use the shift-left methodologies. So for a RISC-V based SoC, to utilize these shift-left methodologies, the first thing that will be required is the appropriate models of the RISC-V at various abstraction levels. For the virtual prototyping use case, the primary basic thing that we need is a instruction set simulator, which is a fast, functional, untimed simulation model. So in the RISC-V world, I mean, there are some open source simulators available, like we have a Spike ISS, we have VIR ISS from Chips Alliance, there is something called QEMU as well. So these are good enough for creating some basic environment for verifying the CPU, etc. But it's not very easy to use them in a real HDL kind of environment when you want to apply these methodologies at the SoC level or at the system level. So it's very difficult to integrate with the HDL environments and difficult to integrate with the embedded software tools and IDEs, etc. So at Circuit Sutra, we developed a unified SystemC wrapper, which exposes an interface, which we call CST ISS interface, through which like you can integrate any kind of instruction set simulator into it, and it enables these ISS to be used in the SystemC based environment. So many companies, they actually end up writing their own ISS in C language. So for them, it will be quite useful that they can just implement our interface, and with this wrapper, their ISS becomes available to be used in the SystemC based flows. I mean, that's for the starting point. But in future, it can be further enhanced to use in other SDL environments like Verilog or co-simulation or co-emulation kind of thing. That way. And in this ISS, you need not worry about like advanced features like tracing, etc. So these are taken care in our wrapper. So another thing that we did is like we developed a reference virtual prototype of Core-V MCU. So Core-V MCU is an open source SoC from Open Hardware Group, which is not owned by any specific company. So it's open source. That's why we have taken it as a starting point, as a case study. So for this SoC, we developed a register accurate, loosely timed simulation models, which is developed using our own Circuit Sutra modeling methodology, which is based on SystemC. The primary use case for this is pre-silicon software development or setting up the continuous integration, continuous design flow for the firmware. It's developed at a higher abstraction level. So in terms of timing abstraction, we have removed the clock. So there is no clock in it. It's untimed and a loosely timed kind of thing. In terms of interfaces, we don't have to model actual pins, etc. So we actually model at a transaction level for this. So at the transaction level, there are two things in it. One is the SoC bus, which is used for register access or the memory access. So for that, there is a standard called TLM 2.0. So that's what has been used. But for the other interfaces like serial communication, UART, SPI, I2C, etc., I mean, there is no standard as such. So we developed some custom TLM sockets for this. And in terms of functionality, we don't have to model the entire microarchitecture. So we implement only that much functionality which has to be visible to the software. For the CPU model, as I talked about, so we use the instruction set simulators along with the unified SystemC wrapper, which we developed internally. So this SoC also have a eFPGA block. So eFPGA does not have a functionality as in it. So basically, anyone who try to use it, they can actually implement their own IP in the FPGA and use that. So in the simulation model, we developed just a empty stub model for it. So any customer, when they decide the functionality for it, they can actually develop the simulation model for that and integrate into it. In future, it can be further extended for like co-simulation and hybrid kind of environment. So, I mean, RISC-V, it's a emerging ISA. I mean, if we try to compare with other ISA, let's say ARM. So ARM has a pretty robust modeling ecosystem, modeling infrastructure around it. I mean, if we want that RISC-V ISA should really be highly successful, adoption should be fast. So developing this kind of like modeling infrastructure for RISC-V is also very important. So that's what actually we are trying to do in Circuit Sutra. So in Circuit Sutra, as a company, our mission is to accelerate the adoption of these higher abstraction shift left methodologies in the industry. We develop the fast simulation models of SoC, IP, CPU, and system at an abstraction higher than RTL using the high-level languages like SystemC, C++. We are an India headquartered company located in Noida and Bangalore. We also have an office in US, Santa Clara, and we are planning to set up a team there. We are in the business for more than 19 years now, supporting the semiconductor industry since November 2005. We have a world-class modeling team of more than 250 years of combined experience in the ESL domain. I mean, we have seen the evolution of SystemC, adoption in the industry, pilot projects, etc., development of standard right from the beginning, and we have actually participated in this evolution further. We got awarded by Accelera Systems Initiative for driving the Accelera standards in the Indian ecosystem. So Accelera is an alliance of semiconductor companies which is defining the new standards for the semiconductor chip design. Recently, we also got shortlisted by Forbes as one of the 200 companies with the global potential. So perhaps we are the only company today which is 100% focused on these higher abstraction shift left methodologies and which understand all the aspects of these methodologies. like virtual prototyping, architecture modeling, or high-level synthesis. We are supporting the leading semiconductor and semiconductor companies across different domains like automotive, storage, artificial intelligence, deep learning, communication, mobile, high performance analog, medical electronics, CPU, etc. So as an offering, like we have SOC modeling services through which we set up the world-class project teams which work as the extension of the customer's team, either remotely or at the customer site. We also execute the turnkey projects. We have a highly specialized training, which we say SystemC for virtual prototyping, which we conduct for the semiconductor companies and the system companies. This is one of its kind training which goes beyond just the SystemC language, because in case of modeling, just learning the language is not sufficient. You need to understand various abstraction levels, the modeling techniques for developing the models at various abstraction levels. So this is the training which is targeted for SystemC for virtual prototyping. Over the period of time, we also ended up developing a reusable modeling methodology, which we have started licensing, which we call Circuit Sutra Modeling Library, Virtual Prototype Quick Start Packages. So this is primarily useful for those companies who have not yet started with SystemC. They want to get started. They don't have any internal methodology as of yet, and they have not yet decided which tool to use. So in SystemC, the good thing is you can get started without using any tool as well. So this methodology which we have developed internally, this helps the companies to get started quickly with their SystemC modeling initiative, do the proof of concepts, get the working model, set up the design flows with that. And at the right time, once they have realized the benefit of it, so then they can decide the commercial tools like Synopsys Virtualizer, etc. And they can actually quickly migrate to that way. So there are some challenges in this shift left methodology. So it's very clear that these methodologies are becoming essential going forward for any kind of like complex SOC design. But it's not very easy to adopt these. So one of the reasons is it requires a very unique combination of skills, which is a combination of computer science and semiconductors. So there are very few professionals in the industry like who really understand it. The second thing is, apart from just learning the languages, it requires a deep understanding of the abstraction level and modeling techniques. So like even with the high level languages like SystemC, you can develop the models which can simulate as fast as the real hardware, or you can even develop the models which can be as accurate as the Verilog, but then it will be as slow as Verilog as well. So just learning the language is not sufficient. I mean, you need to understand what is the target use case, what will be the abstraction level for that particular use case, what will be the specific modeling techniques used for that. So these are some of the challenges which we are also trying to tackle at Circuit Sutra and help the industry adopt these methodologies. So we also have, various career opportunities in SOC modeling. The primary thing that we look for, so as there are lots of students here, so the primary thing that we look for, any candidate should have these foundation skills, like they should be very good in programming like C, C++, data structures, algorithms, good understanding of computer architecture. And in addition to that, for electronics and semiconductors, they should have good foundation on digital electronics, microprocessors, microcontrollers. So RISC-V can be taken as the starting point. So you can understand RISC-V instruction set architecture. You can go through some reference SOC specs of a RISC-V. So for example, Core VMCU, that's an open source SOC. But you can take any SOC specs which might be available, let's say around Shakti processor or Vega processor from CDEC. So you can go through the specs of some SOC, try to do a little bit of firmware development on top of it, and maybe get some understanding of SDL like Verilog and VHDL. So these are the foundation skills that we look for in any candidates when someone applies at Circuit Sutra. And when someone joins at Circuit Sutra, so we have a very highly unique ramp-up program, like through which we are able to make these candidates experts in the SystemC modeling quite fast. Yeah, so that's all I have in the presentation. So any questions we have? Okay, thanks everyone.
Now we have the next speaker. Shrikant, a seasoned professional in the field of silicon design and architecture, currently holds the position of Senior SoC Architect at Ola Kratrim, where he also serves as the Chief Architect for AI Server SoC. His extensive experience in the industry includes a notable tenure at Intel as Senior Director, during which he led the development of numerous SoCs designed for AI accelerators, desktop, and mobile products. Prior to his role at Intel, he contributed in various silicon design roles at prominent companies such as Texas Instruments, Qualcomm, and ST Ericsson. He holds a Master of Technology, MTech degree in Macroelectronics from Indian Institute of Technology, Kanpur. I think we are all very excited to hear from you. Welcome.
Hello, everyone. Okay, while the slides are up, let me talk about where I'm right now and what we are doing, and then it basically creates a context for what I'm going to talk about. So right now we are at, I'm working at Kratrim. This is, we are building a data center, which is a CSP, which is, fully India made, made in India. And right now we are already hosting a lot of models. So we are, the number of services that we are doing includes even the AI models and stuff. Now, along with the data center that we are already hosting with the existing chips, we are building our own chips for our own data center. And currently, there are 2 generations of products which we are building. The first one is expected in 26, and second one is expected in 28. And once the slides are up, I'll talk about, based on these experiences that we are going through while building stuff for our own data center, why things are what we see, how we see, and how we see that things are, how RISC-V fits into the ecosystem and how things are easier for us to, kickstart the activity in India, right? Okay, so it's up. So the topic is RISC-V in AI accelerators. I think a lot of people have talked about AI. A lot of people talked about RISC-V because this is anyway RISC-V conference. Now, it's the marriage of the two. And we see that there is a huge significance of RISC-V in the AI accelerator arena. And then there are a lot of opportunities too. Now, so this is purely from the hardware design perspective, how they, what are the matching properties of the two and why it is the right time and stuff, right? So now, what is AI computing? Today's requirements are purely from the LLMs and the Gen AI. A few years back, it was CNNs. Now, CNNs are still used, but most of the compute requirements circle around LLMs. In LLMs also, when we talk about it, is specifically transformers. The Gen AI is the diffusion models, and the size and the, the complexity of how things are done. So ultimately, this is based on some pieces of the algorithm which are specifically about attention layers and the dense layers. So whatever hardware we are building is specifically targeted for that. Now, this is the current generation stuff. Now, of course, there is always something new algorithm that will pop up, just like the transformers popped up, right after CNNs were at its peak. We expect that something will come up. We hope it will come up because we want the AI to keep growing, right? Now, the story with LLMs and the diffusion models is that the sizes of the models are extremely varying. Now, when we talk about the model sizes, I'm pretty sure you keep hearing about models of billion parameters to trillion parameters. Now, in terms of compute world, these such a huge, large, order of magnitude variation is extremely difficult to handle. For example, the last generation of, the VLSI growth happened in the mobile industry. Now, if you look at the mobile industry, they are very clear about the range of compute that you are looking at. When you look at a small phone versus large phone, very high-end phone, the performance are different, but it's not the order of magnitudes of 1000x, right? Whereas in case of AI, that's not true. You can have a billion parameter model, you can have a trillion parameter model. That's, a 1000x variation that you have to handle. Now, then there are requirements for training and inference. Training is something which we never did in any of the computing before, any of the computing paradigms before. If you look at signal processing, there is always heuristic stuff, right? We designed something, initial language models were also heuristic. So someone would have done some heuristic analysis, make some models, and then it's always about getting the result out. It was never about making the model itself automated. Now, the training in the AI is completely changing that, and the requirements are extremely high, and they are quite different. So now, but on the flip side, inference requirements are lower than training, but they need to be a lot more responsive, because when you type something in the ChatGPT, you want the answer immediately, right? You don't want to wait for, like, you're talking to your friend and the friend says, hey, wait, let me read up on it and then come back to you. You won't expect that from a ChatGPT. So you want the result immediately. So the compute also requires a lot faster, computation to happen with the latency, which is very short. Now, there is a new thing called context length. That means, you would be able to give a lot of data as an input, and then your models are going to give some answers back. Now, these contexts are very complex in terms of computational requirements, because it's like, you want to give a PDF to the model, and then you ask a question, and then it spits out an answer. Now, for a human to do that, you can understand how much time it will take for you to read a whole PDF and then answer it. For humans, it's perfectly fine, you expect it, but with models, you don't. For models, you would like the answer to be immediate, right? So now, of course, I talked about who is creating the demand, what are the structures of it, but let's look at the structure of these models itself and see what are the components needed in it, right? Okay, so these are two parts of inference, inference and training. The top part is the inference, where you are giving a lot of inputs, and one word at a time is coming out step by step, and you feedback that whatever word has been generated, you give along with the rest of it, and then a new word gets generated. So this is how the LLMs work. Gen AI is a lot more simpler. It's an iterative process, but it will keep generating in a pipeline fashion. Whereas in this case, you are actually generating, with a loop back, right? So any time there is a loop back, we know the latency problems associated with it. The control systems are always complex. Now, in terms of the training, it's again a loop back system, but it's even bigger. The amount of data that you feed in, the amount of processing that is needed to be done in every loop is very large, but these loops can happen for months. So your servers are running for months and months in order to make sure the training is complete, right? Now, the reason why I'm showing this is why I'll show you why the requirements of the hardware will look like, and where we basically are, fitting into a RISC-V into it, right? So the demands of this, based on these models, even though it's a one single small box, that box has a lot of parameters, and we are talking about the weights, that is called the parameters of the model. Now they are all defined in floating point. Now floating point computation is always complex. If you look at any ISA, integers are a lot simpler than floating point operations. But the range is very important. You need a lot of range for the compute, for the training process, as well as the later in the inference. Now, Interestingly, there are different types of computation that are needed. If you look at a general purpose computer which is designed, you actually have conditional stuff, and there are a lot of ifs and elses. There are a lot of, some mathematics that is happening in between. But in terms of AI, it's very, very stringent mathematics happening, right? There is a lot of compute which can be defined as a matrix compute, and then there is a bunch of vector compute, and then there is a bunch of scalar compute. But if you look at the percentage of compute that is needed for matrix is very, very high compared to the vector and scalar. This is one of the reasons why it's very, very slow to run a model on a x86 processor or any general purpose processor, right? You need an accelerator for it. Now, the compute, now on top of it, we are talking about billions of parameters. Every parameter is a floating point number. Now, if you want to store all that stuff, it actually needs so much memory, and then you are accessing that memory continuously. Right? Now, the traditional stuff is all about putting it in cache. Now, try to reuse as much as possible because the data has locality. So now all these things don't work because, as you saw in the previous picture where the model is used, the whole model is used in order to generate one output, and then you need to take that output and run the whole thing again. Now, whenever you do the whole thing again, the whole model needs to be loaded into the memory again and again. So that means cache doesn't work. Now, our current generation architectures are all cache-centric stuff, right? So now what it means is the cache used to solve the bandwidth problems, but no longer the case. Now we need ridiculously high bandwidth memories. And that's where you see HBMs into the picture. Now, models are evolving rapidly. I think I already mentioned that the CNNs were there before. Now they are all transformer-based stuff. You never know what is going to happen. Now it's a huge investment in terms of the chip design, the data center designs, the number of chips that you're going to deploy. Now you don't want to replace them again and again, right? You want the continuity to happen when something new happens. And that is the most important thing. So you want a compute which is programmable, which can adapt to the changes in these algorithms. You want this, the programmability also needs to be done in such a way that it can adapt to anything, something which you have no idea what it is going to be, right? So when CNNs to the LLMs happened, one architecture immediately was able to catch on is the GPGPU architecture. Because it's programmable, the things were able to configure to the new algorithms very easily. Any hardware ASIC which was designed specifically for CNNs, they just couldn't scale, right? Now, the good news with LLMs, even though it occupies lots and lots of memory, one thing which is very interesting with this is the model components are highly parallelizable. And the hardware is, if you have ability to run multiple pieces of workload in parallel, lots and lots of it, it works very well. So that's one of the reasons why GPGPUs work well, right? So the flexibility I talked about already, so if you want something, a hardware, you want to design it, it's very difficult for us if you just do a state machine-based stuff or a kind of an ASIC, you design it, then it just doesn't scale. And so programmability is key. Now, what is the solution for it? Now, you want something where you are able to handle the programmability. You can handle multiple threads. You can use multiple cores. Now, and it has vector compute. It has scalar compute, maybe matrix compute, but of course the ratios are too great. But we need something which can easily adapt, right? And that's where the RISC-V comes in. Now, RISC-V can be that compute, programmable compute for AI accelerator. Now, the good news for AI accelerator ecosystem is there are no legacy limits. Now, if you look at, the mobile world is pretty much with ARM. The desktop and servers are very heavily x86 centric because there is a lot of legacy that exists, and RISC-V to penetrate into those markets, even for ARM and x86 to penetrate into each other's market is very complex, because the software ecosystem and the legacy associated with it is, big deterrent. Whereas AI accelerator legacy is very limited. Now there is a bit of a GPU stuff, but that's extremely proprietary, whatever is, there. So in a sense, it's fresh, right? So any processor that gets into the market has the same, footing. Now this is a great start for RISC-V. Now RISC-V has, was always designed for area and power efficiency. These two things are very, very important when you want to go for multi-threading, because you want smaller cores with lots and lots of cores so that you can run multiple things in parallel. Now that fits very well with RISC-V because it's a very modern ISA. It has all the learnings from the previous ISAs that existed in the market. And so, it has a lot of these things and it is evolving very fast. I think the evolutionarily RISC-V has, evolution has been the fastest up to now in terms of any ISAs that exist. Now, RISC-V can bring standardization to the AI world, because right now people either have their custom process or they have their own proprietary stuff that existed in accelerators. But more and more startups, if they start using it, as well as maybe the bigger companies too, the good news is there is going to be a standardization. Just like AMD and Intel x86, you can have options. This can give options. At the same time, there is a software standardization because of which the programmable part of accelerator can easily be portable. Now ISA advantage is the openness. Now, of course, startups can easily utilize it because the ISA is open, royalties and stuff are lower. There are multiple companies which are working on, making the different cores. And that is great for us. And once along with that, the software ecosystem is also open along with it. And then the more options of software and frameworks integration is happening, which is a great story, because one of the complications in AI compute is the software. People have created a lot of hardware, and some of the presentations before said hardware is easy. But the failure in AI compute hardware is majorly because of the software ecosystem and the framework and making your hardware compatible to it. And that is a big problem today. And now, how can you solve it? By having an ISA which everyone knows, everyone can use, which is open, as well as every company can pick and run with it, right? The entry barrier is lower. So from this perspective, the RISC-V sounds great, right? Now the question is, ultimately we are talking about an accelerator, right? Now accelerator needs some things which are specifically for that specific function, right? Now, first of it is the scalable performance. You don't want to make an accelerator which only works for maybe a cloud, or maybe only for inference, or maybe only for training, maybe only for edge. But you would like the IP to scale and adapt to different functions and different levels of complexity. Now, of course, the smaller cores with the parallelizability, that becomes a lot easier, because you can always size it by dicing and slicing, right? Now, the good news with the AI is, or bad news for hardware engineers, is the speed at which it is evolving is extremely fast. Now we see that people are now saying 2 years is eternity in AI algorithmic development. Now how do you develop? The silicon development cycles are 2 to 3 years from the time your inception to the deployment, and the silicon is getting used by the people, right? So now AI world is moving by the time. Now, so the programmability helps, but generation over generation, if you want to have the same architecture but evolving along with the AI algorithms, you need a ISA also on the processor cores, which can adapt also very fast. And that's an interesting and very good thing with the RISC-V core. Now, if you look at the RISC-V consortium, I think you'll see that there are a lot of things which are happening in parallel with respect to extensions, with respect to some of the feature requirements. Multiple companies can come together, then drive things. And this basically makes life a lot easier in terms of the speed at which you can adapt, right? Now, industry collaboration, I think you have seen multiple companies talking about their own cores also today. There are many companies, and there are software companies, there are support companies which are also looking at the RISC-V cores. So it enables the people like us who are building the chips using the cores to have an option which is fitting the right microarchitecture for the right architecture, right? And if we want a multi-threaded, we can go to a company which is supporting that. Which, if you're multi-core, we can go to companies which are supporting that, combination of it. We want a floating point vectors, which is already at the baseline that is existing. So these are all the things which are available with the RISC-V, and we can easily adapt to it into our architecture needs. Now, on top of it, there is a very big thing that exists in RISC-V is the custom extensions. Now, this is one thing which is very interesting because you always are looking, whenever we talk about accelerators, there is the general purpose compute, and because there are some things which you want to run and control, as well as do this algorithms which are very standard stuff, versus there are some functions which you want to specifically accelerate, right? Now, the custom instructions of RISC-V actually does that extension. Think of it like x86 cores with SSE and not having SSE, right? But these are specific fixed ones in x86, which we already know as extensions. But here, someone wants to create their own extensions because that accelerator needs some specific functions. They can work with those companies or create their own extensions, right? This is a big advantage because there is a baseline architecture which is compatible. And then on top of it, you can integrate these external, additional instructions which you think your specific workload can be helped with. Now, AI also, in terms of scaling, one of the things which is also very effectively happening today is, today there are 70 billion parameter model, 8 billion parameter models and stuff. But you still want to save the memory. So the data type, even though it is floating point, you want to have different data type sizes from FP16 all the way to FP4 these days. Now, these variations are some things which you don't find as a standard part in any of the ISAs today. Now, these accelerators would like to have it. Now, the good news, RISC-V extensions, custom extensions enables you. If you want something, you can basically modify it, implement those things on top of the standard baseline. Now, another interesting thing is the coprocessor interface. Now, of course, this integrates accelerators. If you want some very complex functions, you want to attach it, you can do that too. But there is a standardization potential. Today, there is no standard for RISC-V, but there are companies which have worked on it. They publish their interfaces. Right now, there is work going on. So at least we hope there is going to be a serious standardization that will happen. That will drive the accelerator market a lot in terms of specifically adding some special features. Right? So I'll end with the opportunities for RISC-V. Now, RISC-V cores already are very dominant in microcontroller space today. If you look at the market share, it's fairly large share that it occupies already. Now, there is a potential for excelling in accelerators. We see that for only scalar functions for managing things, that's already getting used. Now we see that it can extend its footprint even further in terms of the programmable compute part of the accelerator. Now, there is a lot of open collaboration that is happening, and I believe and I hope that there is going to be a lot more that is going to happen. And there is lot of opportunity that exists for academia to do a lot of research. I think this is a hub for it. So maybe I'm saying some things which are already done here, but still this is a huge potential for academia to do research, so that the people coming out of the universities already are equipped with it, and we can use it in the industry immediately, right? Now, there is a great opportunity for AI software framework standardization too. Of course, there are always differences you want to have as a chip provider from one to another, but there is a 90% of the work which can be standardized, right? The 10% is the additional work. There are LLVM-based stuff, that is, compiler frameworks which are coming up. RISC-V is playing a good game there. I think, stronger participation both from academia and industry would really, really help in that side. Now, in terms of, extending this impact, right? It's not just about AI acceleration that can help for RISC-V, because once RISC-V enters into the AI accelerators, my strong gut feel is it will immediately get into HPC market, and it can get into networking market, it can get into other accelerator markets like crypto markets and stuff. It's very easy because most of these functions are also multi-threaded, and some of the places where things can, all the features that I was talking about which make it suitable for AI, also some subset of these actually work for some of these, extended function, the workloads and effectively the market associated with those things. Now, India's role, this AI accelerator market is starting now. It's in very early phases. It hasn't even peaked. It's far from peaking. And this is the time to join. And of course, that's what we strongly believe at Krutrim. And that's why we are doing our own stuff. And I think this tech leadership for India can happen if we participate now. And strongly participating in it can help, because getting into a market which is mature is extremely difficult. Because beating someone with all the feature sets available and entrenched in the market is extremely difficult to replace. So this is a great opportunity, because nothing is standardized. Things are growing super fast, and everyone is ready to experiment. And this is the time to enter and take the tech leadership. Now, once we do that, of course, the next step is of course going to be a global opportunity. We have innovation hubs here. The startups, I think I heard a lot of people talking about startups, what we can do, how we can do. And this is a great opportunity. So that enthusiasm and using these things, we expect that it's a great opportunity for India to have a strong footprint. With that, I'll end. Thank you. Any questions? Okay.
Hi, I'm Varun from Shakti Lab. So you talked about vector custom instruction. Oh, the architecture you are going to design for accelerator.
Okay, so when the product comes out, we can open it more. So one thing I can tell you is we are looking at RISC-V, that's for sure, right? And all the points that I talked about are what we were looking at, and that's what we are implementing. But in terms of exactly talking about specifics, I think you have to wait for our final product announcement, which will take a bit of time.
Okay. So, but you talked about coprocessor and vector. So, are you implementing many cores or one big systolic array?
Yes, we are definitely looking at many cores. Because we are working on a server class product which will go into our data center. So, it's only It has to be.
Also, you are going to open source your software, or is it going to be?
We will be part, we will definitely contribute into open source. Now, how much, what parts, that's something which will happen over the time.
Okay, thank you. That's it.
But we definitely would like to participate in the open source community.
Yeah, that was all.
Okay, thank you.
Our next speaker is Gopinathan. He's going to be talking about building expertise in RISC-V product engineering. Gopinathan M. is the co-founder and CEO of Shakra Innovations. He's one of the key team members of the Shakti processor development program at IIT Madras. He was instrumental in implementing the variants of India's first indigenously developed Shakti SoCs across various semiconductor foundries. Recently, he implemented the Iris chip for ISRO with Shakti core that was in the media last week for its successful booting. As part of the physical design pillar for Shakra, the first test chip for Incore semiconductors using TSMC 40 nanometer was done by his team that's awaiting the packaged silicon. He received his bachelor's in ECE from Mada Engineering College and master's in VLSI at SRM Ishwari Engineering College. The Shakti FPGA 48-hour hackathon that was part of this event was hosted by his team. Over to Gopi. After Gopi's talk, we'll take a short break. The original break was planned for about 45-50 minutes, but we'll take a short break and we'll reassemble here around 3:55 to 4 when he'll have the next two academic sessions. Thank you.
Hi everyone, good evening. I will not take much time. I have just 2 to 3 slides. I understand it's late evening, everyone waiting for coffee. Just wanted to quickly get through what we are doing, what we are looking for, what is the contribution of Shakra to this community, to the RISC-V community, what we can do. So myself, Gopi, again co-founder of Shakra. Apart from me, there are 2 more founders, Anand and Koti. Anand is completely on the software stack, building software stack, driver development, and Mr. Kotishwaran is for doing the PCB design, layout, board bring up. Myself on the implementing the design to the fab, handing over to the fab, supporting the packaging. So we 3 joined together, thought like we 3 are inclined in 3 different pillars. What can we bring up about that? We thought like, why can't we bring up a product using RISC-V cores? So that's when we joined up and brought this startup. So what we do? So we have the cores available. So since we are also part of Shakti, so we have the cores available. Shakti cores, as you have seen, like last 2 days, we were part of the hackathon, organizing the hackathon, 48 hours hackathon. So what we did on that was we generated the SoC for the problem statements, and we were able to cater its full-fledged application through the hackathon. Similarly, we also support and whoever is willing, who are the customers willing to generate an SoC, build an SoC, we do customized SoC and do as a service. Especially using, if they wanted to adopt Shakti, we'll be able to assist on that. So that is the first one, SoC integration. Then FPGA verification, yeah. So once the SoC is built, if you wanted to completely verify with all the tests, we have the expertise, we do that. So all these things are services that we do, but what is the product? Yeah, I'll tell you at last that we are working on. So then physical design, yeah, that's my pillar of strength. Handled around 6 tape outs till now. And everything that we handled was from the scratch to, not like one block I handled, it's not like it's the full chip. Everything was full chip that I handled on, which was a very big experience for me until. And next is the software. Yeah, so coming to the physical design, yeah, we recently, Shakra team recently did the tape out for Incore's first test chip, which is awaiting from the packaging house. Hopefully, we'll look into it in next couple of months and looking for its first silicon success. And next, software. Yeah, we do software services for doing driver development, porting operating systems like Linux, RTOS. Yeah, again, for doing the software, we are also doing service for Incore for pre-silicon software support also we do, and we are also doing post-silicon software support for Incore. Board bring up, yeah, we integrate all the components, the chip, and we bring up the board. That's again a pillar of strength. So with all these things, we are developing a product called IoT Gateway, which right now we are on the testing phase. We are planning to bring up a product using any RISC-V core, including Shakti, and it will be soon expected as a product. We wanted to launch it. Before launching it as a product, we really wanted to burn our fingers and get to know what is the challenge in bringing up a product, because that is something bigger picture. Where you will have a lot of problems coming in when from a simple interface, if there is an issue with an interface, how do you deal with it? And for the same, what we got from the hackathon, the learnings that we got from the hackathon that we did for this event was tremendous. And yeah, the learnings that we got for handling a simple PWM, writing a driver code for the PWM, for a stepper motor, and sitting with the participants, and such kind of learnings is as much required for a product engineer to bring up a product. So we are on the process of experiencing all these things. With few more customers also. So, for example, one customer is asking for we are doing an FPGA, customized FPGA with a limited number of peripherals for them to cater their application on that. So we are building as a board, as an application on that, building an FPGA board for them. So basically they have data from a sensor that needs to be collected using their own processor that needs to be burned on the FPGA. So this is one customer that we are right now working with. And we have another customer from IIT Madras itself, a startup from there. Basically, it's an IoT platform again. So all the motors and which are huge, which has bearings with them, they wanted to know the lifetime of the bearings. So basically, with respect to the vibration sensor data that's been collected with the bearings, the data is sent out through the cloud and it has been processed. And through that, we will be able to know the lifetime of a bearing. This particular test case which is a huge market volume that we are expecting to be, because there is everywhere motor. If you see, there is everywhere engines and motors. So this is one place that we are, that is one of the customer that we are working with them. So we do both service and product both together. That is our expertise. Other than that, that is all from my side. We are also looking for interns and hiring peoples also on all these domains. Please feel free to apply. You can visit our website. Thank you. Any questions?
Thanks, Gopi. We break for a short tea and coffee, and we'll come back to listen to two of our esteemed professors of the Institute.
So our next speaker is Chester Ribeiro, Associate Professor, Department of CSE, IIT Madras. He's going to be talking on trusted execution environments for RISC-V. Chester is an Associate Professor at the Indian Institute of Technology, Madras. Prior to that, he was a postdoctoral researcher at Columbia University. He has a PhD from IIT Kharagpur in the area of hardware security. Before joining IIT Kharagpur, he worked as a member of the technical staff at CDAC Bangalore. His area of interest includes security aspects in the operating system, architecture, and VLSI. He is particularly interested in building and analyzing secure systems. Over to Chester.
Yeah, thank you very much, Nithya. It's a pleasure to be here. I'll be talking about some of the work that we are doing at IIT Madras on trusted execution environments for RISC-V. So before we go to that, we'll essentially look at why we need these things called trusted execution. So this is your typical computing stack. You have hardware, the operating system, and then above that applications. And what we see in the arrow on the side is that trust, as we go down from application to the OS and hardware, the trust essentially increases. So you trust the hardware much more than the OS, and the OS is trusted more than the application. Now, the second part of what I said, that is the trust of the operating systems being more than the application, could be actually taken with a pinch of salt, because as we see today, with the operating systems becoming larger and larger, the number of security vulnerabilities in the OS is actually increasing. So we've looked at the vulnerabilities in Linux, the Linux kernel, and we've seen that in And we've seen that in 2024 itself, there were over 1,000 vulnerabilities found in the Linux kernel, right? And the list keeps going on and on. So trusting the operating system isn't the best thing that can happen, because if your operating system is compromised, what it means is that all applications that are running over that operating system is also compromised, right? A compromised OS essentially makes all the applications running over that OS also compromised, right? So what do we do for this? So one solution that has been in the industry and research quite often in the academics as well is the aspect of trusted execution environments, or TEE for short. So TEEs, or trusted execution environments, essentially they create an enclave across the around the application, a sandbox in which your applications can execute. So what does this enclave actually provide you? So this enclave essentially is a region which is not accessible by your operating system. So even though your operating system is compromised because of one of the many vulnerabilities that is present, your application 1 and application 2 get compromised because it's not in the enclave, but application 3 which is in the enclave continues to be safe, right? So we use this enclave, which is essentially hardware enforced, to keep vulnerabilities from the OS away from the application, right? Your application 3 is secure even with a vulnerable operating system. Now, so TEEs have been around for quite some time. There's been a lot of work both from the industry as well as academia to develop TEEs. Intel SGX was one of the early ones. Something which is now present in all your smartphones is the ARM Trust Zone. IBM has similar, AMD has one, and so on. And similarly, in the academia as well, there have been a lot of research papers essentially published on various TEEs designs. Now, also to note, just highlighting that few of these, especially in the recent past, have been based over RISC-V. Now, one limitation, right, or one thing that is common to most of these TEEs or trusted execution environments is the way they operate, right? If I just abstract the entire thing and look at how a typical trusted environment manages memory, it looks something like this, right? So you have, in a typical case, you have your RAM, which is on your left side, and your operating system can access every byte of that RAM. But what a trusted execution environment creates is a partition. So it creates something known as an enclave memory, which is typically encrypted, and all your secrets, all your sensitive code and data are essentially placed in this enclave memory. So now you have two parts of your memory. One part which is essentially your enclave memory, which is not accessible by your operating system, and the other part which is non-enclave memory, where your typical applications essentially execute. So the way to use this trusted execution environments is to take your application, split it into two parts, one which is your secure part, which is the green one on top, and you place this secure part in your enclave, and the red part, which is not so secure, does not have anything very private, can be placed in the non-secure memory or the non-enclave memory, right? So every time you want to essentially design an application, you need to find a way to partition your application into the secure part and the non-secure part, right? And make use of the trusted execution environments only for the secure parts of your application. However, the problem with existing trusted environments is that they are not compatible with legacy application. Now, why is this the case? So legacy applications are applications which have been maybe written like 20 years back or 25 years back, where the concept of enclaves didn't even exist. And in many cases, legacy applications have a very outdated, very complex code basis. There's no proper documentation. The developers may have actually moved on to some other organization. And for a new person to essentially come and work with legacy code, it is extremely difficult. Now, therefore, if I have something which is legacy, taking that legacy application and splitting it into two parts between secure and non-secure and so on is going to be cumbersome. Now, the problem becomes very significant because there are a large number of legacy applications that are present and still running these days. Now, companies do not want to essentially change or go away from their legacy code because that has been working in the field, and that's what is being providing, or their livelihood. That's what's being sold in the market, and they do not want to essentially touch that code, right? So somehow our objective was to create a trusted execution environment for the Shakti processor, which would support legacy applications. So we call this Tesla, Shakti with trusted execution support for legacy applications, right? So the basic concept is, instead of trying to split the application into two parts, secure and non-secure, we place the entire application as it is in the trusted environment, as we see over here. Here, for instance, we are not splitting the application into two components, but taking it as whole and placing the entire application in the trusted enclave, right? How do we achieve this? On RISC-V, we essentially achieve this with a thin layer called the security monitor, which is placed in the machine mode. So your RISC-V, many of you would would know this by now. So you have like, typically have your operating system, which is potentially vulnerable, which it runs in the supervisor mode. And above this, you have your user applications, which run in the user mode. So what we introduce here is a security monitor, which is running in the machine mode. Now, the advantage of having such a security monitor in machine mode is that it is more privileged than your operating system, right? Now, also we, to get this entire thing to work, we also had some modifications to the hardware, to the CPU core, and introduced something called as a CPU key, which is a private key specific for a particular processor. Okay, so let's essentially see how Tesla operates. To start with, we start with the generic code. We take our code, and as we've been done for years, use a compiler to essentially compile that code and generate an ELF image or a binary image, right? So up to here, everything essentially works just as before. You're not modifying the code, you're just taking existing code, compiling it. But what we do later is very Tesla specific. So we create a key known as the ELF encryption key and encrypt the entire binary or sections of the binary to get what we call as an encrypted ELF. Now, along with this encrypted ELF, we also we obtain hashes of each section present in the ELF, and along with the ELF encryption key, we create a final binary comprising of the encrypted ELF, the hashes of each section, and the key that is used for encryption. The hashing essentially ensures that any modifications done to the encrypted image is essentially detected, while the ELF encryption key or the encryption that is done ensures that the confidentiality of the key. So far we have now created an ELF image which is encrypted and has some extra information, right? The next thing is to load this image into memory and then get it to execute. So the second step is you have this executable which is now encrypted, and you want to load this image into memory. So you run your application as you've always done. For example, /a.out in Linux, that would essentially run or start your application. So what your operating system would do as before is start to load pages into memory, right? So it moves to the hard disk or your flash and so on, and loads page by page from your hard disk into your RAM. But notice here that our ELF is encrypted. So what gets loaded into RAM are the encrypted pages, right? And your operating system, when it observes this particular section which containing the hash, it would invoke the security monitor, and the security monitor would then load all of these hashes and the key in a separate memory which is isolated from the rest of the system. So this green part here is the memory present or accessible by the security monitor and the hardware, but not from the rest of the system, not from the operating system, applications, and so on. What the security monitor also does is create something known as an ownership table. Now notice that the ownership table is also green, indicating that this region of memory is also accessible only by the hardware and security monitor. So in the ownership table, we have an EID. EID stands for the enclave identifier, which uniquely identifies a particular page, the owner of a particular page. So for example, if I run a particular encrypted program, it gets an EID, which is something like your PID, your process identifier, but this will identify the enclave, and it uniquely creates an entry in the ownership table connecting a particular encrypted page with the EID, right? So all of this is essentially done with this CPU key. Now finally we go to the execution. So notice now, up to now, that we have essentially loaded your program into memory. We go into the next step where you want to execute it. Now as you're executing your program, right, you're fetching instructions and data from your memory, but notice that there are two additional steps that are needed. First of all, you a change in the processor where the EID is verified or checked for equality with respect to the currently executing process, right? So you can't, for instance, access the enclave of another process. So you essentially check whether the EID of the page that you're accessing is equal to the current EID that is currently executing, right? And as you're loading instructions and data, notice that, remember that it's all encrypted. So when this data passes or enters into the CPU core, it passes through an MEE. So MEE stands for Memory Encryption Engine. So at this particular point in time, when your instructions and data enter into your processor, it gets decrypted and stored into the cache. Now from the cache, as we all know, it gets fed into the pipeline of the processor, gets executed. The results goes back from the cache to the MEE, and when it's stored in the memory, gets encrypted again. So what the MEE essentially achieves is that any data or instructions outside the memory is always in an encrypted form, while inside the CPU, it would be decrypted. So in some sense, Tesla achieves 3 security guarantees for a protected app. So it achieves, with the help of encryption, it ensures that there is no modification or in storage or during the loading of each instruction. It ensures the confidentiality of the data and instructions that are of the program that is currently being loaded. During execution, it uses isolation based on the ownership table to ensure that the OS, or for that matter any other software entity in your system, cannot essentially access the protected application. With the help of hashing that we store in the encrypted ELF, it also ensures that the program is not tampered with, right? But things are not straightforward, because there are a lot of challenges that come across, that we come across when we try to essentially build such a system. Now, one of the biggest challenges is how do you handle system calls. So as we know, when a typical application executes, it makes system calls, and what we have learned is that the system calls essentially result in the OS getting executed, and the operating system services these system calls. So in the past, in the trusted execution environments, for example, the Intel's SGX as well as the ARM Trust Zone, whenever you had this system call, you would essentially exit the enclave, execute the system call, and then get back in the enclave. And that was part of the reason why you needed to partition your application. But here we decided that the entire application should be in the enclave, right? So we need to find a way by which your application can execute, but somehow the system calls made by the application are redirected to the operating system, and the OS is able to access system call parameters to service that particular system call, right? So what are these system call parameters? For example, let's say I have open, file name, and some access policy. So these file names and the access policy, read, write, execute, append, or so on, are your system call parameters. So these are essentially present in the memory of your application, and your OS needs to know how to access it. Unfortunately for us, because your enclave is protected from the operating system, the OS cannot directly access these system call parameters. So we need to essentially find a way to achieve this. Now again, we make use of the hardware. So what we do is modify the way system calls are essentially handled. So instead of directly going from your application to the OS, that is from the user mode to the supervisor mode, we intercept the system call in the security monitor. Now what the security monitor does is that it identifies what system call is present and creates a small window in the application memory, which is now open to the operating system. So what you see here is a small blue region that is maybe a few bytes of memory, which the operating system can access, even though this memory exists in the enclave, right? So for example, if I do an open system call, the file name would be now accessible to the operating system, but not the rest of the enclave. So given this, the security monitor now passes control to the OS. The OS executes or services the system call, accesses the application data like the open file name and so on, and everything goes as usual. Now when the operating system returns, ideally you would want to return back to the application, but in this case, we go back to the security monitor, which is on mission mode, close the window so that the OS no longer is able to access that region, and then return back to the application. Right? So in this way, we are, with the help of intercepting system calls, we are able to service system calls in an application even though the app is within the trusted environment. So, so we've tested this on Shakti C on an RTA700T board with the Linux kernel 5.50. So we've changed both the hardware, we've written the security monitor from scratch. We needed to also modify the Linux kernel to get it to work. So one thing or two things to essentially note over here is that the user application, there have been no changes at all. So what it means is that we can take a legacy app, run it as it is after compilation, of course, in the trusted environment. There are just 17 lines of code changed in the Linux kernel. Now these 17 lines is needed just to identify that this particular executable running is a trusted executable and needs to pass this information on and invoke the security monitor. Security monitor is a bit larger, it's around 419 lines of code, and the crypto library, which is now written in software, is around 258 lines of code. So the hardware overheads, so on average, this is on the FPGA, we had a 15.6% increase in the number of LUTs required, 24.2% registers increased. Now, a large portion of this was in the cache memory, obviously because in the cache memory is where we had this MEE, which could do the encryption and decryption. But another interesting observation is that the data cache had significantly more overheads compared to the instruction cache. The reason for this is the data cache requires both the encryption, but also requires the storage, so you require the decryption plus the encryption, while for the instruction cache, you only have fetching instructions, so you only need to decrypt instructions, right? You don't need to encrypt them again because you don't write to instruction memory. So this is the performance overhead. On an average, we get slightly more than 5% overheads. Some of them, like QSOT in particular, has a high overheads based on the size of the array or the data that is being used. Essentially, it indicates the number of cache misses, because every time you have a cache miss or a page fault, we have a significantly slightly larger overheads. This accumulates, causing a increase in the percentage thing. So yeah, so this was trusted execution, one of the many things that we do to create secure processing cores. The other things are runtime remote attestation. So what we are able to achieve this with this is we're able to run a code and we are able to get the hardware to provide us a valid proof that that code has actually executed, right? So this can be used, for instance, in, let us say, electronic voting machines to prove that a vote has indeed been counted, right? So we have processors for which are resistant to side channel attacks. We have a variant of trusted execution which can support secure I/O. We also support software compartments. Now, software compartments essentially would help us to create small regions. Each region is as small as a function, which can be treated as a sandbox. So your entire program is now made of small compartments, which gives you a lot of security because you're reducing the potential attack area. We also work with unikernels, in particular Mirage. So unikernels are these, at least from the embedded domain, they are pretty new concept. They've been present for in cloud computing for maybe around 10 years or 9 to 10 years or so. But for embedded systems, it's relatively new. It's been essentially helps you create very small lean processors or lean operating systems, and the smaller your operating system is, the safer and more secure it is. So we intend to use these secure processor cores for multiple different applications like FIDOs, EVMs, Bitcoin or crypto wallets, and TPMs. And we're trying to essentially productize this with secure SI technologies. I'd like to stop here with the sponsors for our lab. We've got a few sponsors who have actually supported various different projects within this secure processor course. Okay. Thanks very much. Are there any questions? Yes.
Hey, hi Chester. Yeah,
hi.
Really good presentation. I just had a couple of questions. So the first question is related to the software side. So you mentioned where Tesla's actually most important vulnerability it exposes or it protects against is in the OS layer, right? So the first question exactly is, let's say you have a source code, and in that a specific function is calling some other function. So you have something, a recursive function going on. So in that, if you how many encryption keys would you need? Because each function would be calling another function, and that function might be calling some other function. So would you have a recursive CPU keys being going on, or is a single key enough to protect or encrypt the entire
So that's a very good question. For Tesla, we have one encryption key per application, right? So and that's the design as of now. We do see that there are certain advantage of having multiple keys. Also, like a lot of problems that could occur with compatibility in examples that you essentially mentioned, where one function needs to call another, and if they are actually using different keys, you essentially have a problem there. We don't know how to tackle that as yet. So as of now, like you create one process or one enclave, and the entire thing essentially uses one key.
Okay, thank you. One more follow-up question on that. I just wanted to ask whether this Tesla, whatever you have designed, is susceptible to also vulnerabilities on the hardware layer. So for example, if you have encrypted something, some source code, and when it goes into the microarchitecture of the CPU design, and it's let's say it is hit with a Spectre attack or a meltdown attack, or if you go deeper into that stack, it's hit with a DRAM row hammer attack. So in those cases, how would Tesla be?
Oh yeah, that's an excellent question again. So the assumption we make is like the slide that I had in the beginning, right? So the OS is less trusted than the hardware. So in this particular case, we are actually restricting the trust to the hardware, right? So as of now, we assume that the hardware is trusted, and but the software layers, OS and above, are not trusted. So the current version of Tesla is susceptible or vulnerable to attacks like meltdown and Spectre that you mentioned, and the row hammer. In the future, what we need to do is identify ways to essentially mitigate these kind of attacks as well. The problem there is that once you try to mitigate these channels, right, in the microarchitecture, you immediately start seeing a performance penalty, which is quite high. So certain solutions are present, but they are not the best optimal solutions as yet, right? So some of the other works that we are actually doing is trying to identify or create tools which could detect or identify that this region could potentially have maybe a microarchitectural vulnerability, right? And how do you fix that, right? So that's a different kind of approach we are taking. At some point in time, all of this should kind of collate together and form one solution, but we are still not there as yet.
Yeah, thank you. Thanks a lot.
Yeah.
Good evening, sir.
Morning.
So, during the system calls, you mentioned that from the application, instead of going to the supervisor mode, it goes to security mode. And then security monitor opens up the portion of the application to share the data. Do we plan to use shared memory concepts so that the shared memory can be shared between the security monitor and the supervisor mode, so that you don't open up the enclave, right? Enclave is always protected and accessed by only the security monitor.
Yes. Yeah, that's interesting, because if I do have a shared memory between the security monitor and the OS, it is not the best idea, because you now are completely trusting the security monitor, right? So any kind of sharing between the OS, which is less privileged than the security monitor, could potentially lead to problems. But yeah, I see that that's a possible way to approach it, but I'm not seeing the benefit of it with respect from the security perspective, nor the performance perspective as well. Because what we see over here is just like a very minimal increase in the overheads to just open this particular window and then close it later on, right? So it's just maybe a few lines of code, right? So having the shared memory would require maybe I as of now can't see a possible benefit of that, but maybe we can actually talk, maybe something is there which we can talk, I think, post
Sure.
this.
Thank you, sir.
Hello, sir. Actually, we're talking about unikernels and all. Though, like it's smaller in size, so we have like less security issues, and it can be easily booted. Like, will it be like applicable in like all the processing of Tesla? Like, yeah, when we are implementing, will it be like suitable for processing and all, or should we add other systems to it?
Yeah. So the concept of unikernel is that you want to add in your operating system only the portions that are actually needed for your application. So it's not suited for, let's say, general purpose computing, right? Like for example, your laptop where you want to run different types of applications. So it is not suited for those kind of things. But if you have, let's say, an embedded system, right? Like for example, say a network router, your embedded system is essentially doing only one job, that is performing that one network router application, right? So you don't want to have an operating system like Linux, which has a lot of different functionalities. All you want is an OS which can support that particular very specific application. So the unikernel would be compiled in a way that only what is required for that application to execute would be present, right? So what it means is that if I change my application, I change my router to say a firewall, my unikernel also needs to change, right? But if I use a conventional OS like Linux or embedded Linux, then that same kernel could more or less be used for the other thing as well, right? So you of course need to optimize or reconfigure it, but more or less it's the same kernel. But in unikernel, you would essentially customize your OS for an application.
Good evening, sir. Sir, you mentioned that the key, whatever the key you encrypt, will be stored in the RAM, right?
Yes.
And suppose there's a system shutdown in between the execution of the program. How do you plan on retrieving the key?
Okay. So the RAM is always in an encrypted state. So if you have attacks like the rowhammer or cold boot and so on, you will not essentially get any information about, or like let's say you extract the RAM and place it somewhere else, because the contents are all encrypted, so you won't get any further or any additional information about the key, or for that matter even anything about the enclaves or the security monitor or anything that, right? So it's kept secured because the RAM is encrypted.
Thank you.
Okay, so I think we are done if there's no questions. So thank you, thanks everyone.
Thank you, Professor Chester. We now have the last talk of the symposium. By Professor Gopalakrishnan Srinivasan, Assistant Professor of the Department of Computer Science and Engineering at IIT. He's going to be talking on the road ahead for Shakti and computing paradigms. Gopal received his BTech in Electrical and Electronics Engineering from the National Institute of Technology, Calicut, in 2010. He subsequently received his Master's in Computer Engineering from the North Carolina State University in 2012 and PhD in Electrical Engineering from Purdue University in 2019. He is currently an assistant professor in the CSE department at IITM. His research entails developing bioplausible neuromorphic machine learning algorithms and hardware architectures for energy-efficient computing at the edge. He is a recipient of the Class of 1991 award, which recognizes assistant professors in the CSE department who demonstrate exceptional promise in research. Recently, he was conferred the International Fellows Award by the University of Adelaide, which is awarded to internationally renowned researchers with excellent scholarly record. Gopal also had a distinguished career in industry prior to venturing into academia. He has worked across leading semiconductor organizations in the US like Cirrus Logic, NVIDIA, MediaTek, and Apple as a designer and architect. He subsequently moved to India and joined Mindgrove Technologies, a startup specializing in building RISC-V based SoCs. He currently serves as their lead architect and consultant, responsible for driving the architecture and design of a multi-core SoC for vision applications. Over to Gopal.
Okay, so good evening, everyone. It's always, first of all, it's hard to be the last speaker when people are all tired. So hopefully, I always tell my students, I'll try my level best to not get you to sleep. Hopefully, you'll find some takeaways from this talk. So the title for my talk is, the road ahead for Shakti and computing in general. So in the first half, I'll don my engineer hat and talk about, of course, Shakti means a lot of things to different people. So what we have done, what is in store, to kind of give a glimpse of what we have achieved and what we want to do going further. And then I'll don my researcher hat and talk about some of the alternative computing paradigms that I'm exploring along with my students. And hopefully there's some takeaway and some of you get interested and spam us with emails. Okay, so that's the goal for this talk today. So, so if you look at the GitHub for Shakti, you will find whole bunch of jargons there. You will find an E-class, I-class, and so on. So you have a variety of cores and accelerators on the top. You have a fabric, and you have a bunch of peripherals in the bottom, right? So this is what we mean by the Shakti ecosystem. I think kudos to the team that have put together both the compute cores as well as the peripherals, right? If I were to distill down and kind of talk about what is the effort that is needed to develop an ecosystem like this, right? So it was kind of spearheaded by Professor Kamakoti, current director of IIT Madras, and a lot of motivated students, right? So the entire stack was developed by motivated students like you, maybe their younger selves, and project staff, So essentially, RISC-V, is a specification, right? You Google RISC-V on the internet, and then you'll find two PDF documents, right? One is called the unprivileged spec. The other is called the privileged spec, which Chester briefly touched upon, which gives you the privilege levels and how do you access, right? So now, from the specification, you got to build a hardware that honors the specification, right? So we had a very interesting talk by, Sri Rajiv Chandrasekhar, former Minister of State of Meiti, who mentioned, you got to be building solutions, right? So you have a specification, you got to be building solutions for different classes of applications, right? So this was thought of much in advance, and hence we have all those weird acronyms, right? E-class, C-class, I-class, and so on, which we'll get into. But essentially, architecture is, you have an application, what does the architecture look like? How many stages of pipeline? How many levels of cache, right? What is your memory hierarchy? Now, what are the high performance features you're going to put in? Are they needed or not? So all those are called architectural decisions. So from a specification, you need to be able to understand what your target application is, and by simulations or whatever, be able to come up with an architecture. For this application, what is the architecture of the compute core going to look like? Once you have finalized the architecture for a certain application, you kind of come one level lower which is called the microarchitecture. Okay, now that I know the architecture, how do I go ahead and design the cache controller? How do I design the decoder? How do I design the execute units? How do I pipeline them and come up with various design optimizations so that you can clock it as fast as you could? Right? So from spec, which is our ISA or the instruction set architecture, you came to architecture and see, okay, what are the rectangles and squares needed in your design, and essentially you go to the microarchitecture where you go ahead and build, it's usually called the RTL or register transfer level design, right? And once you have your RTL design, someone has to verify it for you, right? So unlike software, you cannot patch it. If there are bugs, you have to be able to discover your bugs before you send out a chip for fabrication, or at least before the silicon comes back. So this RTL verification is a huge challenge, and tremendous opportunities are available in the verification domain, because it is that hard to make sure that you guarantee you have uncovered as many bugs as you can in the design. So once you have a certain design, you give it to the verification folks, they qualify your design and say, okay, you're good to go. And once you have a verified RTL, you have the so-called physical design teams. They are the ones who take the code, which is written in a higher level language like Verilog or System Verilog or BlueSpec System Verilog or VHDL, and translate them to the actual standard cells and gates and circuits and devices that are at the heart of our silicon. Right? So you write code in a higher level language, it's verified, you have this physical design flow which in itself has varying stages, and finally you have a format for your design. It's usually called the GDS format, which the foundry understands and manufactures your silicon for you. Right? So are we done? No. Okay, so now you send it to your foundry, you're going to get the chip back, you have to figure out how are you going to package it, and you have to go ahead and design the board. For example, any of you who were yesterday, I think Mindgrove Technologies, they demonstrated an actual board, right? So essentially the silicon came back, they packaged it, they designed a board, got the board manufactured separately with all the peripherals and the way to interact with your compute unit, and then you can give your development boards to potential customers. So these are the steps if we were to go from, let's say, RISC-V until you get your development board, okay? And you can count the amount of job opportunities you have just with this one slide. So that is the amount of effort that has gone into creating this Shakti ecosystem. It's just not that you have some implementation, you have to go layer by layer, stack by stack, and then start from spec, go all the way until you have a board like your Arduino and Raspberry Pi that you can actually start using. Okay, so this is the first part of what we have in the Shakti ecosystem. Okay, so what more do we think we need, right? Okay, I have the board. So what are you going to do with the board? So the next important component happens to be your software. So you can have poor hardware or reasonable hardware, but the hardware should work. Okay, as long as you have supreme quality software, any hardware will sell. That's been my learning from years of experience. Okay, so hardware can develop over iterations, but really you get customers and everyone to use it if you have good support from the software standpoint, right? If we take I showed a diagram which has a slew of peripherals, you have to be able to help the users write low-level firmware, create libraries for a lot of their applications, help them develop drivers, and be able to demonstrate your board across a class of applications. It's only at that point that you're actually going to get people to use your development board. Okay, so usually you have two kinds of users. One are ninja systems programmer who want to do bare metal programming and really get complete control over their system software, and then you have the end common normal users like all of us who will be able to want an operating systems to be booted on your hardware, and then they'll develop the user application, which again I think Chester went through the flow. You have your compiler, assembler, you have a binary, put it, the operating systems will kind of create the process for you, and then it executes on the underlying hardware. So either you want to be able to do bare metal programming, or you should or at the same time your chip should have the capability to boot some kind of operating systems, okay, so that you can have end users running on it. So in Shakti, apart from the fact that they were able to go from specification until creating a development board, right? They were also able to demonstrate a lot of applications, including booting an operating system, which was thought to be the kind of work of few ninja programmers. They kind of democratized that and essentially made sure that all of our interns who work with us, one of the first thing they do is kind of see Linux booting, which in itself is a eureka moment for a lot of them. So essentially the success of the Shakti ecosystem, why Shakti is insanely popular among students and startups, is because of the amount of support and documentation and expertise they were able to develop over the years. So this one diagram is kind of a gist of whatever I spoke about until now. So everything from specification until the board to SDK, we have different people in our group who have expertise in different stages of this chip development and programming process. Okay, so let's talk about what popularized Shakti, right? So in the semiconductor industry, I know majority of students, you're only respected as a company or as an academic organization or as a government organization if you have done a successful tape out. You have something on an FPGA, okay. You port something on FPGA, you get an operating system to boot, all is good and done. But if you want to show that you really mean business, you have to be part of a successful tape out where you have the ASIC, put it on a development board and be able to hand it to different users. So you are kind of, anyone who will enter the semiconductor industry, your career progression will be measured by how many tape outs, successful tape outs where you are part of. Okay, that's how anyone in the semiconductor industry, all of us, when I was in the industry, the natural question when you hunt for jobs is, okay, how many tape outs have you been a part of? It's just, it's that hard to get a chip to work, right? For example, Sundar Pichai, who is the CEO of Google, after 7 or 8 years of development, he finally conceded. He's like, building hardware is actually hard, right? Because you cannot patch it. You can have multiple revs, and each rev to the foundry is actually expensive. So it's kind of a unique opportunity to be in any one stage of the pipeline that I showed and be able to have demonstrable expertise. Okay, so the reason why Shakti was insanely popular was because they were able to do tape outs and show that their design actually worked across two different technologies. So in India, we have a foundry in Punjab, it's called the SEL, which tapes out chips in 180 nanometers technology. At the same point, they were able to go to a much lower technology node with the help of Intel and be able to demonstrate their design. So what was already done, and the reason why a lot of us are here is because the successful tape outs of your embedded class and the controller class course. Okay, so what is E-class? Again, to reiterate, Sri Rajiv's point, E-class is supposed to be like your low-cost, microcontroller you will get for like 100 rupees or whatever, right? It's a very simple pipeline. You will probably clock your E-class at very few, hundreds of megahertz, and then to get very simple applications done, at the extreme edge. For a lot of, industrial and IoT and sensing use cases, the C class or the controller class is the workhorse. For example, the board that Mindgrove they demonstrated yesterday, it is built on top of the Shakti C class, which you can potentially clock at gigahertz range in, let's say, TSMC 28 nanometers technology. So essentially, figure out your application, pick which core pertains to the class of application, and then start developing applications. Okay, so this is why, as I said, all of us are here on the back of the success of the Shakti C class in particular. Okay, so what's next in line, right? So we have a couple of tape outs we want to do in the next very few years, and one is called the Shakti I class. So now you started with, let's say, embedded class, you graduated to, okay, you have your high school C class, you are a BTech, okay, now you want to get your MS and PhD, that's your I class. Essentially, you are trying to build a beefy, powerful CPU. So I class is supposed to be a superscalar and out of order CPU. So what is out of order? So all of us have written, I'm pretty sure people are here, have written some lines of code. So what all of these that I have shown here can be clubbed into the umbrella of von Neumann computing. The ISA is mostly sequential in nature. Maybe you can discount Shaktiman for now. Essentially, you write code, you get the binaries, the instructions are there in certain order, your E class and C class will faithfully execute the instructions in the same order as they are in the binary. So what is the drawback of that? I mean, what is the advantage of that? Your design is very simple. What is the drawback? Let's say you have a load and that misses in the cache. Okay, 500 nanoseconds. You wait and do nothing in your CPU, right? So essentially, the I class of the out of order is meant to solve that problem. Essentially, if you have a cache miss or whatever, you let the independent instructions in the pipe make sure that your hardware or pipeline is always doing something useful and just not sitting there idling away. Otherwise, you burn leakage energy. So the I class is supposed to be a beefy, powerful out of order CPU which executes your instructions out of order, and the design of your I class is extremely different compared to your simple 5-stage, because there are things you still have to do in order. With out of order, I'm not going to bore you with all that, but it's reasonably challenging that it's a potential multi-year effort, and we are getting closer to taping out our I class pretty soon. Okay, and again, what is the goal of I class? We want to be in the high performance segment, and right now there's a lot of push from the government to kind of come up with solutions not only in the controller and embedded market, but also kind of dream big and even build beefy CPUs. Okay, and finally, the other project we want to push closer to tape out is this multi-core. So I think it was written by our director, I think Parashakti. I think for any of you who are who believe in divinity, Parashakti is the supreme power, right? For some of you who grew up in the 90s, maybe it's some. And if you are from Tamil Nadu, it's a very popular Shivaji Ganesan movie. Okay, but anyway, whichever way you take it, Parashakti is supposed to be that you have one core, but not sufficient because all of us keep scrolling all the time. You have to be able to have your hardware or system run multiple processes in a very seamless fashion. Okay, so how do we accomplish that? Okay, we go multi-core, right? But the natural question is, okay, I already have the C class core, right? So I just slap some 4 cores together and I am done, right? So obviously it's not that easy, because if you look at this architecture diagram, if you can look at this diagram and figure out what is the problem, right? So if you just had one core, you can have 10 levels in your memory hierarchy. It's very easy to make sure that you have only one recent copy of any variable. Unfortunately, if you slap all the 4 cores together, each of them have their own private caches, and then there will be some level of memory that all of them are going to share. So what is the potential problem? Okay, you took one copy and replicated it n number of times. So the challenge in getting your multi-core to work is that you have to solve this. I mean, it has been solved, but you have to engineer and make sure that you kind of have a bug-free coherence solution. Essentially, you have created a problem because you have created multiple copies of the same variable. Okay, and this is where I came in at Mindgrove. So essentially, I was very happy when I moved back that they said, okay, this is what you're going to do. Oh man, I felt it was very exciting, because usually if you look at coherence and do a Google search, right, one state diagram will be there. I mean, just Google or open any book like MSI, Messi, Moisi, and so on, right? That was my level of understanding when I got started here. Okay, but to actually implement that, it's a huge challenge, and to implement it correctly and make it performant is even a bigger challenge. So as we said, we have students who have done some initial work. They were able to demonstrate it on FPGA. They were able to port over a real-time operating system. But as I said, in this field, you are measured by the tape out. So we have to get it tape out ready, and then the world will notice. Until that point, you have an FPGA, okay, N+1 guy who did something on FPGA. Okay, it's important. It's important for functional verification, but it's in our best interest to kind of make sure that we are tape out ready and kind of demonstrate a multi-core design. So this is kind of something we want to do in the next quick succession. Okay, and then there are a number of others that we want to do, but then let's focus on, of course, Chester already spoke about, the security aspects. So he takes care of the security aspects of Shakti, both at the software level, microarchitecture level, and any levels of the stack. So I think security is secure with Chester, so I'll not touch upon that. He already mentioned that he already gave a good talk, and we'll go on to one of my specializations as well, which is what I spent a good time in the industry trying to build custom hardware accelerators for ML. Okay, so the next question was, okay, everyone was talking about this machine learning has kind of taken up in a very big way. So what is Shakti's solution for that? Okay, so I think a few years back we got started with Shaktiman, right? And how many of you recognize his name? Okay, then you should be as old as me, okay. Because we grew up in the Doordarshan Shaktiman time. So I really like the way our lab presents all these names. Okay. Anyway, Shaktiman is machine learning accelerator. You can fit the acronym somewhere, but it's a machine learning accelerator. So it's a systolic array based accelerator. Since the development of Shaktiman happened, it started development a few years earlier. At that point, most of your machine learning workloads have had the GEM operations or the general matrix multiply operations as the majority of them. If you look at a deep learning model, let's say until the LLM came and swept all of us, you will find that at least 80-90% were all general matrix multiply operations, and that's when Google adopted the TPU design and so on. So essentially, in good wisdom, we started with a systolic array based design. And essentially Shaktiman is an accelerator, so obviously you need a host, so it works with C class as the host. Contrary to RISC, Shaktiman implements a SystemC because it's a custom accelerator. Okay, so you don't need to do RISC in an accelerator. You want the accelerators, the way they work is you give it few configuration information, they should be able to have a DMA to get the data that they need, compute with as minimal information as you can provide, and write the output to the memory. So that is the job of the accelerator. So there is nothing RISC about Shaktiman, and hence, again, that's something we are trying to kind of push closer to a tape out and demonstrate it on practical application. Right now, we have an FPGA version that works, and the unkept secret with these accelerators is literally every month, during my PhD, we used to get a paper about how to build hardware accelerators for machine learning. And then only when I went to the industry, I realized that, okay, you can build hardware. Who gives you the software? I've done my own work using PyTorch, TensorFlow, and so on. So I have a deep learning model. Nowadays, we have a lot of intermediate representations as well. Okay, now I have some custom hardware. It has its own ISA. So who builds the stack? So right now, we are also on the effort to build, by the way, whenever you have your own ISA, you better have the entire software stack with you. Otherwise, no one will use your hardware. Okay, so we are in the process of, solidifying the software stack and also being compatible with, the software stacks for different hardware that we have around us. So I think, again, the accelerator effort, it started a few years back. It's that hard to kind of, first of all, get something to work, design your software, design your architecture, and make sure that we have the entire stack ready before we go for the tape out. So I think we are very close, again, to take Shaktiman to tape out with both the hardware as well as the software stack that we need along with that, right? So this is a glimpse of what are the things we have done, what are the things we want to do. As we said, if you pick machine learning or general purpose, multi-core, in order, out of order, software, low-level systems programming, we kind of have it all, right? So essentially, we are looking for the next generation to kind of take over and kind of take and elevate Shakti to even bigger heights, right? So with that, I'll go on to the next part of my talk, which is something I dabbled in my PhD. I'm still very curious that almost everything that we spoke until now can be clubbed into this umbrella of one-dimensional computing, both from the algorithm as well as the hardware standpoint. So the question I asked during the initial stages of my PhD was, okay, you have deep learning models and so on, right? So can we have alternative computing paradigms, right? So the most energy efficient machine known to humankind is the mammalian or the human brain. Okay, we do a lot of activities, we do recognition and so on. Interestingly, if you think about it, right, the computers are very good at what is hard for us, right? If I say, okay, 2.7548 into 3.5432, how do you calculate? But computers are very good at it. But until deep learning came in, okay, we have to recognize an image. It was insanely hard to build, until we had this deep learning revolution, to build a machine that would recognize and perform well in a task that is like second nature to us, right? So essentially, the goal was, okay, what kind of computing principles can draw from whatever little we know about our brain and build something useful with it. As I said, I'm going to delve into, give you a glimpse to kind of excite you about this field called neuromorphic computing. It's very broad. You can build hardware that kind of honor the neuromorphic computing principles. One example being your in-memory computation. Essentially, in the brain, I don't think we have separate hemispheres to do compute, separate hemisphere to do memory. That's how we build our general purpose CPU. Rather, compute and memory are kind of, tangled and mangled together in a good way so that we are all sane. Okay. So essentially, in-memory compute is one example of how do you build a hardware that honors the neuromorphic computing principle. But what I'm going to talk about is what kind of algorithms you can build, especially in the context of machine learning, if you take some inspiration about, again, whatever little we know about the human brain. By the way, this field was pioneered by a professor at Caltech, or the California Institute of Technology, where when this von Neumann computers were very popular, he took a different approach. He read some neuroscience papers and figured out, how does the cochlea within our ear work? How do we have vision and so on? And he started, instead of saying, okay, I'll write an algorithm, compile it down to a bunch of instructions, he said, I'll build circuits that actually mimic the behavior of how our ears and our eyes work. And he's one of the pioneers of, if you have heard of this thing called the dynamic vision sensor cameras, right? Essentially, where they have a very high dynamic range and useful in a particular class of applications. So why suddenly, as I said, this field was there in the 80s, but then when our computers became very powerful, this kind of was forgotten. Now we are at a point where we are extremely powerful in both algorithms and hardware. There's again, we are going back and looking at the foundational principles that we use to create algorithms as well as hardware. And essentially, it's more relevant now because all of us understand that when you run those LLMs, we burn enormous amount of power and energy, and hence we have to look at alternative computing models so that we can have a sustainable growth in machine learning. Okay, with that in mind, I think I'll point you to a very simple example and then leave at that. Essentially, we should, if we have done any machine learning class, you would have heard about functions like ReLU, GeLU, tan, hyperbolic, sigmoid, and so on. So they are all called activation nonlinearities within your deep learning model. If you look at any of the brain simulations and animations, our brain is well established right now that it computes using spikes or impulses. So you have neurons which are interconnected. We don't send continuous values, rather an event is communicated, okay, whether you have a spike or whether we don't have a spike. So this is a very simple model that we have for a spiking neuron, which is there a lot in our brain. Essentially, we should have the ability to take in impulses or spikes and then produce spikes at the output, and then whatever nonlinearity you have really doesn't matter. Every spiking neuron, there is something fundamental to them that they have to maintain something called the state. State is something that is stored, right? Essentially, it keeps track of the amount of information that has come in and then uses that information that is stored within to produce the output spikes, right? So essentially, the one advantage, if you just think about from the hardware standpoint, is you don't have a MAC operation, right? There's no multiply here. You have binary inputs and usually produce binary outputs, meaning that you don't have multiplies at all, right? You only do additions here. So essentially, you get inherent efficiency in hardware implementation if you are able to, first of all, come up with a spiking algorithm and also have a hardware that exploits all these features. Okay, so I'll kind of, just in the next few slides, give you a glimpse of what can we do with this, right? As I said, most of our information, if you look at an image, right, it is composed of pixels, and pixels are values, RGB values usually, between 0 and 255, right? So if I have to feed that input, let's say to a spiking network, the question is, how do I encode the information using spikes, right? So there are two popular encodings. You say that, okay, you produce enough spikes over a window, and the firing rate over the time window is proportional to your real pixel intensity, let us suppose, right? And it's called rate coding. And the much more efficient way to code it is, okay, I don't care about producing many spikes. I want all my neurons, if at all they spike, they should spike only once, but then I'll plant the continuous information in the relative spike timing difference between the spikes, and then I can plant the real value there, right? As you can see, it's called temporal coding, and temporal coding is very efficient from hardware standpoint because you're able to kind of capture real valued information in the temporal domain without firing a lot of spikes, right? But as you can see, temporal coding is very hard to practically realize, hence rate coding is very popular, but still we have a lot of works going on, and the types of coding you got to use so that they will translate to hardware efficiency, okay? And doesn't matter this slide, essentially there are numerous ways to come up with spiking models, but to give you a glimpse, let's say today you have an ANN, an artificial network like ResNet 20 or VGG 16 or whatever, essentially you can clone and come up with a corresponding spiking model by just changing your activation function from ReLU to, let's say, an integrate and fire neuron that I said, with the concept here being that the integrate and fire neuron, when you do your inference, will produce spikes over time, and essentially we have to make sure that when we clone and get our spiking network, the firing rate of the neuron is proportional to the real value you are trying to encode, right? So this is one application where you have an ANN, you can come up with a corresponding SNN. And why do we do that? Analytically, there have been papers that have been published, including the groups that I've worked in, that you can get, if you can convert your ANN to an SNN, you get some orders of magnitude improvement in the energy efficiency, right? But this was supposed to be an estimate for a long time. So what we have in the lab right now is we are actually trying to build our own accelerator for accelerating an ANN. We are also building an accelerator for an SNN, and we are trying to see, first of all, how does this number 12 translate to if I have the actual hardware. Okay. By the way, when you read papers, if someone says 1000x efficiency, take it with a grain of salt. If someone says 1.5x, 2x, then okay, by the time you actually build it in hardware, that will vanish. So if you have something which is, let's say, 10x or 12x, and you actually implement it practically, maybe we are still trying to figure out whether that 12 will be 10 or 9 or 8 or 7. Even if it's 2, I'm fine. But if you have a paper that says 1000x, okay, I don't know. If you have a paper that says 2x, okay, 10x, okay, we'll try and build and figure out practically when you implement how much energy efficiency you get at the end of the day. So this is again a glimpse of the work I do on the neuromorphic front, apart from the von Neumann architectures I look at. Okay, so I think enough said about Shakti, what we do, what do we plan to do, and there's something more, and also neuromorphic and so on. So what do we need to achieve this roadmap, right? So I talked about a lot of things. So what do you think we need? I gave I class, C class, E class, a lot of acronyms. So what do we need to, if we have to build everything, right? So what do we, come again? Money and talent. Okay, money government is giving us right now. So we need motivated students like all of you who are spending your Saturday, Sunday, and nights together on hackathons and so on. Essentially the goal, the selfish goal behind organizing, apart from the fact that government is giving us money to do this, is to find and scout for talented and motivated students like you who will come and work with us. See, all of us do the talking, right? So all the work I have presented, my students do it. Like I don't sit and code, right? I do the talking. So the work is actually done by the students. So if we want to do more work, we need more motivated students. Okay, so essentially we are right now actually in our lab looking for people with organization knowledge, computer architecture, RTL, doesn't matter which hardware description language, anything, it's okay. RTL verification, you need to know some programming, okay. And obviously, when we start doing more tapeouts, we'll get people for physical design, but we have a lot of projects we want students to work on. And essentially what we do in the lab is, we get students as interns during your, let's say, final year, and whoever, out of 20, 30, will figure out who is motivated, who is not. We usually offer them paid, project positions after they graduate. And some of them, once you become a project staff, you can take courses at IITM. And if you do well in the project, if you do well in the course, okay, you are offered a master's admission. To pursue your master's with research, you can build engineering, von Neumann, you can work with any of us, and to kind of also think about not the next year or the year later, but 5-10 years ahead in terms of security or neuromorphic or whatever, so that you do engineering, you do research, and you're kind of having a very satisfied student life. Okay, so essentially we need students, and please apply. So this was a LinkedIn post a while ago. So there is a web page I'm pointing you to. So it has different fields. If you're interested in architecture, there's a separate application, design, verification, software. There's a lot of work to be done. And let's say you're interested in MS or PhD. Sorry, Chester, you have your email ID there, but please write to me, Chester, and you can look at our websites. I'm still lazy enough that I don't have a website yet, but okay, at least I have a Google Scholar and LinkedIn. And look at the kind of work I've done. So please get in touch with us, please apply. And by the way, we do look at, right? So there are friends at the lab who painstakingly look at a lot of the applications and try to get talent. So please get in touch with us. And why should you work with us? probably the next startup can be yours. Okay, so I think at this point, if you look at Incore, right, a lot of C class was developed by the founders of Incore. I saw Arjun Menon somewhere, Neil Gala, Vinod Ganesan, a lot of folks, maybe I'm missing on people, so Incore. And then Mindgrove, again, who kind of got me back from the US, right? So they were my first employers, literally in India and Tamil Nadu. And they kind of were built out of our lab. And we have Shakra Innovations, which is RISC-V based product engineering. We have SecureWeave, SecureSci, and the Shaktiman I mentioned, that has again, there's a startup associated with that. We have our CEO of that startup as well. And of course, all of you have seen enough of Lavanya, and he's the mind behind Voma and any other startup I have missed, right? So if you want to have a product-based startup, either build chips or IPs or whatever, so this lab is like a playground. If you are motivated, cannot promise you that you'll have a startup, right? But most of the pet projects in the lab have led to startups in the past, right? So if you want to take the unconventional route and kind of carve out a name for yourself, I think okay, we have the playground ready for you. So please get in touch with us. We have a lot of exciting projects, and yeah. So I think with that I'll conclude my talk, and I'll take some questions, and then. Okay, thank you. So any questions that we have? Mm-hmm.
Then till then, how do I check my inspect my application?
I see. So for Shaktiman, I think I can put you in touch with Hemant, and who has this? Right.
Can we implement in FPG?
Sure.
Can we implement in FPG and verify to?
Yep. So I think we have an FPG implementation right now, and then he has a software stack as well. Maybe you can.
Wednesday I'll be coming to you.
Sure. So you can come to the lab, and Hemant is Shaktiman. Okay. So talk to him, and okay, and yeah.
Hello, sir. My doubt is, do you assume brain as a binary system? Because we know all the natural systems are analog based. So based on the spike neural network you said, do you assume brain as a binary system?
So I think, as I said, with whatever little that we know, right, it is known that brain emits impulses. So you could think about it as an analog system, but it does not, it encodes that value using spikes and times. At least a part of the brain does that, right? Essentially, whatever you have encoded in the temporal domain, that's a real value if you were to measure that. But the way brain does it is very efficient. So I think that's the computing principle. If there's one takeaway, it's you plant those analog values in the relative spike timings and be able to learn from them.
There's no information in the amplitude of the spikes.
That's still very debated. I've seen some papers in that regard, and then you get closer and closer to your maybe, right? I don't know if it exists, but if you give amplitude to your spike, it could become your quantized ReLU at some point. But yeah, I think whether it's there in the brain or not, I'm not sure. But there's a lot you can do with just binary information, and then of course you can go ahead and then try to explore that aspect as well.
And one more question. This thing ponders me a lot. Do you feel if you want to develop a system that mimics brain, it should be also trained in the same platform, or the kind of training which we do nowadays?
Yeah, I think I'll take the answer in two parts. First of all, there are people who try to mimic the brain. So they have huge projects where they will build simulators and say somehow I'll simulate a rat's brain, cat's brain. But my approach is that, okay, I want to understand them and abstract out and come up with some computing principles. It could be learning algorithms and so on, which I have looked into in my past avatars. So essentially the goal is to come up with practical applications by abstracting out the computing principles based on what we know. So we don't try to build simulators to mimic the brain, but there are groups that do that, like Spinnaker and a lot of, I keep forgetting the other names, but the approach we take is, okay, these are the principles I know. Can I make my training more efficient? Can I make my inference more efficient? We recently also have a lot of work on fault tolerance, right? For example, people have lived their entire life with just one hemisphere of their brain working, right? So we have a fault tolerance system within us, right? Just because one neuron goes away, suddenly you don't lose all your consciousness, right? So essentially, what can we learn about the fault tolerance? And we have been seeing good results not only from efficiency, but also this fault tolerance that is in the brain, right? So we have been having some works in this regard, and we are getting very encouraging results there as well. So there's a lot you can do with even what you know, but again, we don't mimic and build simulators for that. There are groups who want to analyze that, but somehow might take a little controversial, so I will not do it say it here because it's recorded. Anyway.
So let's say, for example, you want to implement a basic image processing model. According to your point, is it something that should be trained on a current GPU, or the thing we want to create in?
I mean, that's a good question. I have looked at alternative training algorithms, but somehow since backpropagation has come to the fore, anything that you can think of. In fact, Turing Award winner Professor Jeffrey Hinton himself has multiple works looking for alternative training algorithms, right? Because in the brain, I don't think it's like, okay, some part of the brain computes and then it goes to some other part, some error is calculated, and the activation is held on until the error comes back, right? So that is being acknowledged by even the Turing Award winners in the field of machine learning and Nobel laureates as well, right? So unfortunately, the reality that all of them concede is backprop is a very powerful optimization technique, right? So until today, even in the spiking network that we explore, we can clearly see that no algorithm where we read neuroscience literature and try to come up with novel training algorithms, nothing comes close to what backprop can do. So although I've done quite some work, if you look at my Google Scholar on alternative spike timing based training and so on, local learning, reward modulated spike timing based learning and so on, at least until now, until we discover more, nothing comes closer to backprop. So that's the best that we know. So in case you want to build up real application that you want to sell, okay, train with backprop. But with research, I do look at alternative training mechanisms. Maybe someday we'll have the eureka moment and complement backprop, right? But today, that's a very powerful optimization algorithm, and it just works. Even it's very hard to debug your code, right? It'll just work even if you introduce a bug. So,
Thank you, sir.
Hello, sir.
Yes.
Sir, from past yesterday, they said about this is the first time the entire auditorium is filled, and I need to know before this happening what are the events happened and how we keep connected with the stuff is happening in IIT Madras.
Make sure you connect with her on LinkedIn, okay?
Okay, that's one of it. And I am a first year student.
Sure.
And I need to participate in some startups, and
sure.
I need to present myself. So where I can find the startups?
So most of the startups that I showed in the slide, right? Most of them are incubated. Man, why not Shakti? First come to Shakti, okay. But anyway, I think the startups are located in the research park, right? A lot of the times I've seen very motivated kids, they just show up, they just knock and show up. I mean, of course, a lot of the companies have web portals right now, but I've seen people who got internships by just knocking on the door. If they are good, we'll actually screen them. Okay, so I've seen, so you can take a tour of the research park. I think there are 500 or more companies that we have in the research park. You can take a look. They solve a variety of problems across domains.
Where we can find them?
Just go to research park. I think can connect you to someone who can offer a tour. They usually do that. They offer a tour even to colleges, I believe. Right? I think if you write to me later, I can forward you one point of contact there. And they usually give a tour to college students, even school students, by the way. I've seen a lot of school students there.
Thank you.
And then you will know, what are the kind of startups that are there, and it's a great facility that we have an academic institute, and we have a research park that's supposed to work in close collaboration and also productize ideas, right? That's something unique about IIT Madras, I think. So I think you can forward you, but you can just show up there and you'll be able to find that point of contact.
What kind of skill sets are you required?
And you should ask the company. You can talk about what you need for the lab, but yeah, it depends on which company you are trying to aim at.
Okay, thank you.
Hi, so, yeah, I kind of wanted to know, like, how's the work culture in Shakti process? Like, how do you guys, like, a general day of working, like, how would it be if you're a part of the team?
Do you spot people with maroon t-shirts like me?
Yes, I've like talked to a few of them too. But then
so please talk to any of those. I think they can give of course, I can give an answer, but I'll always say good things, right? So talk to the guys in the maroon shirt and they'll be able to give you a better answer. But the long story short, we expect a lot of initiative to come from your end. Right? It's not in your company where okay, there's a boot camp and so on and so forth. So you come, there's chaos, and then somehow you have to learn to swim, and then you'll become whatever. It's up to you, right? So essentially, it's, as I said, it's like a playground. So the more motivated you are, you know who is the right person to ask and get your work done.
So let's
and you
say
can also
like,
hide. I've also seen that
let's say there's like a big project going on, and like you've not implemented, but like gone through a long proceeding of ideas, right? And you've started working on it, but then the person notices a fault. How like likely is it that you guys accept that fault and immediately start working on it, or like what's the like review process of when once the fault is found?
Yeah, I mean we have a system in place, right? So once, I mean initially you will work on something very exploratory. If you get it to work, we'll start doing some serious stuff, and then we have a process. We will try to improve the process, but we do have something.
Okay, thank you.
Okay.
So I'm a first year electronics student, sir. So as you said, there are a lot of projects you are working and you want students. Now suppose in second year I want to join you. How will you judge me? Like I'm first year, if I study I have knowledge. For a basic FGPA prototyping, it got 5,000 to 10,000 rupees I don't have. The least thing I could have is knowledge. So how would you test me? Like I come to you and like I want to join your project. What do you expect from me?
For the benefit of everyone, right? So we have interview process that's tailored for the student. Depends on the level of experience of the student. If a student claims he is very good in Verilog, there are enough people to test on Verilog. If a student claims they know the nuts and bolts of organization and architecture, we can also take care. Student says, okay, I know programming, okay, then probably verification or system development. We have enough people who will grill you on C++, Python, whatever we use. Essentially, we'll grill you based on your interest and what is the kind of work you will do coming here, right? And usually if people mail that I want to do some, that's the mail I get the most. I want to do ML. What should I do? Usually I scare people away by giving a paper and say you read the paper and then let's discuss. So 80-90% I'll not hear back. If people still write back to me, then I think we have an interview process. We'll again start by asking you to present the paper. That's if you want to do anything in ML, right? Because ML is not about just calling some APIs and so if we do some serious stuff on ML, so we also test the student that way.
So it's more of like an interview process. If we mail
there's an interview process, right? Because we have a very limited capacity though. So we have an interview process, but we have had tremendous success with people coming in as interns, project staff, to people who have graduated with their masters and PhDs and almost all startups, right? So most of them came as interns.
So that's what my question. So
the idea, I think the answer that you're expecting is, are we testing on your knowledge? 90% no. We are testing on your learning curiosity and how you face the questions or the problem statements that we give and how you communicate to us. So those are the things that we look at initially. And then we put some hyperboles like that. If you catch it, then you come in.
Thank you, ma'am. Thank you, sir.
We had one more question.
Hi, good evening. I just want to understand for the various class of processes that you're talking about, do you have a plan to roll this out from any fab in India and how soon that would be?
In my understanding, I think the first fab we might actually try out is 45 nanometers from that. I think at least, I don't know if I can share the information. I know some startups who are eyeing that, but when it's time, we'll try to work with the startups. But right now, it's based on availability. So if people can tape it out, we would definitely prefer working with.
As much that the processors are quite impressive in terms of the compute and what they can do, especially when we look at automotive, aerospace engineering, where we primarily come from. Now, getting these processors right now from the US and Europe is becoming very challenging.
Right.
You know, sometimes the waiting time is almost 120 weeks.
Okay.
Now, I'm serious. Like I'm building a communication board on ARINC 429 or a USB 1553 to get a Holt IC. It takes me 120 weeks. You know, unless I sign up for a lot of things where it has to go to the export regime control and all that. So having a processor, we can be closer to what you are doing, you know, could be a tremendous game changer for us in avionics, aerospace, and you know what I'm saying. So especially we are looking at, you know, driver monitoring systems, you know, FPGA-based system, which largely is coming into play right now, where you have system and packaging and all that. We really would need to look these processors to be coming out of India then, you know, so a roadmap there would be very, very critical, you know, for companies to develop solutions.
I mean, on that regard, I think we'll formalize the roadmap because we are trying, as a part of this RISC-V Knowledge Center for Excellence, we are trying to come up with a model where startups or companies can approach us and we support, I mean, we can look at the portfolio, and if they want support, we have already done it for even private organizations, including and also the government ones, where they say, okay, we already have the platform or the SoC, but we want to replace the CPU with one of yours. So we do offer the support right from that point onwards in the
So what's happening is the industry wants to be ahead about 10-15 years, right? So now what's happening is most of these boards or processors which are coming from Taiwan or from China, all the data is going to their server, right? And some of the companies like Tata's and Mahindra and Mahindra, they are not willing to have this data, customer data, local data outside. But today they don't have a choice. And that's where I'm looking at, we can still design a board. That is what we are doing right now. But then it will be still with a chip made out of Taiwan or China, but not made out of India. And how we can fasten that process, to try and get. So is there anything, thought process in that direction I would like to understand?
Two-part there. So one is, I think from being a knowledge center of excellence, we do say that, okay, these are the class of processes, and if you want to engage with us, okay, this is a model. But I do know that some of the big names that you mentioned, they're also in conversation with the startups to kind of have a long, because automotive, I understand, is a...
No, I have a requirement sitting on my table for the last 6 months to give a proposition on SIP, on system and packaging for a driver monitoring system for, JLR. I'm not able to do anything right now.
I see.
Because they want everything indigenized.
I see.
Including, if possible, even design the processor in India. So I'm really clueless at that right now. I'm just looking for some hope. When you showed me the range, it was very, pleasing to see that. But if some timelines can be put, I think that would help us also, when we get back to our customers. So that they can be prepared with the plan, go-to-market plan as to what they want to do, when they want to do. So that way they can build their ecosystem, in terms of data centers, servers, because that would require to map all these vehicles would be moving. This would be very critical.
Yeah, I think for the already ones that we have taped out in silicon, I think it's known that we have it. For others, I think we'll be, we'll try to put together the timeline,
that would be well appreciated.
Because we have gotten the questions from even other private entities, which I don't want to name, and who are very interested in, when is our I-class going to come out, or when is our active.
To one question which I want to generally share with the general public is, my company works for multinational companies, and they are very big names, likes of L&T and M&M. Still, many of the jobs come to us as startups. The reason is that they don't have expertise. And I really appreciate what you're saying. I think what this whole class of students have to do is, if you have to pick up a skill, you have to be hands-on. If you are going to look at an FPGA board, even at your MTech course, I don't think where you will get. The only way to pick up skill on RTL or whatever it is, the fundamental is, and I see that remote possibility even now when I'm meeting, So I think, that's where, a mindset change has to happen across the board, academia, industry, and, for us to get good resource to keep working. And there's no sure shot guarantee like people are asking here, whether you'll give me this, whether you'll give me that, because there's a lot of lagging, On one side, there is a sea of opportunity, on the other side, there's absolutely lack of skill. So I would end, by saying, what Swami Vivekananda said about 100 years back. we don't need qualified people, we need educated people. You know, so I think that's really missing today. I've been 30 years in this industry. I'm still really feeling the pinch of getting good basic resources who can work on this.
Yeah, I mean, software we can, I think we have somehow figured out at least part of it. Hardware has been a mystery because it was done by very few handful of companies, and the training was usually the tape-out training and everything, even until I was an undergrad, was usually done only in very specific companies. You have to join, let's say, Micron or NVIDIA or Intel to get the training, and after that, if you're that good, they'll send you to the US, right, or wherever they are. So Shakti and the startups are a unique place where you can actually experience a tape-out. So if you are in the semiconductor industry, we are slowly trying to create that knowledge center literally. The entire tape-out experience and getting that in an academic institute was kind of unheard of, until, in IIT, not only our group, right, we have analog groups that do tape-outs, been since the late 2000s, I think. So I think that was used to be unheard of, but right now we are trying to democratize that by giving students the tape-out experience so that, they'll be bold enough to take up, semiconductors as well.
So one note I want to end is my request to all electronics to ECE students. Anybody who knows English can learn programming and become a programmer. But not everybody can become an embedded programmer.
Sure.
They need to understand logic gates. They need to understand Boolean. They need to understand flip-flops. And I think if they can give 3 years of their lifetime, I think their life will be made. But let them not get drifted away by software programming and, BPOs. So let's do some hard work, but really create a change in the world, that we can do. That's my only request to all of them. Thank you so much for people like you from IIT doing such a great work here. And we from the industry and actually with academia, we should be able to do much better.
Absolutely.
Thank you so much.
Anyway, I'm just the face, right? So all different color shirts are responsible for the actual. Now I do a little work, but should ask them. Okay, so I think we'll conclude. Do you have one question? Okay. And I really want to thank people.
Hi sir, I am Lakshmi Narayanan, second year electronics student. Usually I like simulation softwares, so I learn it very deep if I get interested in that. And because of that, I am not able to do regular my theory subjects. My theory subjects are affected. I spend more time. So what will you suggest, sir?
Which college do you come from? Let me base my answer on which college?
VIT, sir.
VIT is a deemed. Okay, anyway, so, I've always felt this, right? Maybe you guys can correct me. Most of us, any country we go, we do exceptionally well in courses, most of us, that's a reality. Because we have been trained to crack courses really well. So if you are very interested in doing something useful, somehow I don't think it's very hard to not do well in right? So you have to figure out a way to, I know a lot of guys here who do a lot of additional work, I was blown away by what I saw in hackathons and so on, but I think you should be able to easily, the system that we have, I don't think it's that hard, no. Maybe occasionally, but okay, anyway, I think I still feel you have enough time to do what you want to do, and there is, Professor Kamakoti, there's a karma. Your karma, you have to get a degree. I don't think it's very hard. Figure it out. I don't think it's hard. At least that's my opinion. And that's true, I've seen across the world, right? All of us, you have to kind of get, as Sir said, we have to get all our skill sets and so on. That's very important. Man, karma is there, right? Not everyone in IIT Madras gets to do electrical and CS. I've worked with people in metallurgy and so on. They'll work with me, for a year or so, but they still do reasonably well in metallurgy. Okay. I have more examples, but I don't want to embarrass and find. Yeah.
I don't know why you are undertaking students up to 6th standard should not enroll for any of this. So they will not study the concepts. So you should not take students for internship until then they complete sixth semester. So that will not, because they will not study. They will not study the fundamentals. So you cannot expect any hardware person to come out.
I see. But we do have exception, but anyway, I think yeah, so I think thank you, all for the wonderful questions. You can definitely write to me, connect with me offline. At this point, thank you. By the way, thank you all for showing up to the symposium and making it a success. like to start by thanking, because as to kind of create awareness for this symposium, I think we had to partner with universities to conduct road shows. So at this point, I would like to acknowledge IIT Gandhinagar, IIT Jammu, and IIT Bhubaneswar, who partnered with us for different road shows, and again, people from here, who kind of accompanied and made sure that enough awareness was spread. And we would like to thank our hackathon organizers, NXP Semiconductors, Voma Systems, Shakra Innovations, Redwood EDA, and VSD. And we would also like to thank, CDAC Trivandrum and the Shakti team at IIT Madras to have held parallel workshops on RISC-V based, application development. And we would also like to thank our sponsors, Mindgrove Technologies, NXP Semiconductors, Akeana, Kane Semicon, Circuit Sutra, and CDAC. And at the end of the day, we would like to convey a heartfelt thanks to all the volunteers from IIT Madras and Pravartak who really made sure that all of you were well taken care of. A big round of applause to the the foot soldiers who put in sleepless nights to make this event a success, and also to the team at Pravartak and anyone involved who facilitated the talks, the presentations, and so on. Videographers, photographers, and everyone who made sure that they were patient and cover the entire event. So a big thank you to anyone and everyone who was involved in the event, and my apologies if I missed out on any, but a big thank you to all of you who made this program a success. Thank you.